Hello everyone, very good afternoon. Welcome to Physics Wallah. So today we are doing physics Maha Marathon. So in this Maha Marathon, we are going to complete entire syllabus in one go. Okay, so are you guys ready? Are you guys ready for the session? Hello, good morning. Very good morning. Good morning, my dear students. Minebi, good morning. Amarjit, good morning. Manjot Singh, hello. Good morning, everyone. Very good morning. Welcome to Maha Marathon session. NL channel, good morning. Arshita, good morning. Amarjit, good morning. Ali Hussain, good morning. Niveda, good morning. Very good morning. So today's session going to be very special for you guys. Okay. So because throughout the year, we have learned so many things, right? So how to tackle with our syllabus and how to manage our time, right? So it is high time that we need to concentrate and we have to clear this exam for our future, right? So upcoming professionals. So you guys are the upcoming professionals. So doctors, engineers, and other professions, right? You are the future of India, right? You are the future of India. So nothing but the students, okay? Sahil Kumar, good morning. Pushkar, good morning. Good morning. Pavan, good morning. Yeah, I'll explain, Pavan. I'll explain. So each chapter, how much time it will take, okay? I'll explain the timing. Okay. So please let me know, are you guys ready for this session, Maha Marathon? So in this Maha Marathon session, we are going to complete entire syllabus in one shot, okay? In between, small breaks will be there, okay? So I'm trying to give at least 2 to 3 breaks throughout this session, okay? So maximum, the break duration will be 20 to 30 minutes, okay? Arvind, good morning. Good morning, very good morning. Yes, Ajay Krishna. So in this particular session, okay, listen, first I'll clarify all your doubts, okay? So in this particular session, we are going to discuss a theory part and very important questions and PYQs and numericals part also, okay? So Pratima Kumari, good morning. So Ajay Krishna, I hope your doubt is clarified, okay? Yes, in this particular session, we are going to complete everything, MCQs, one thing, that is assertion and reasoning, okay? So that we need to tackle with that, okay? So that we need to tackle with that assertion as well as the reason, okay? Yes, Ajay Krishna, okay, got it, okay. It's VK, how many hours, sir? Okay, so let me explain. I'll start the session. So in the beginning itself, okay, so it's your time, okay, crucial time, because tomorrow you have English examination, right? So I don't want waste your time, okay? So whichever part we have a doubts or else a confusion, so for that particular session, you can join back, okay? So don't waste your time because you have a next day exam, that is English examination, okay? So don't waste your examination or time, okay? So next one, Vaibhav. Good morning, Shweta Mishra. Namaste. Okay, yes. Yes, I know tomorrow is English examination, okay? So that's what I'm saying. Manage your time properly, okay? So which chapter or which a concept you have a doubt, you can join that particular session, okay? So I'll explain the slots, okay? With respect to time, each chapter. So how much time I'm going to take for each chapter, okay? Good morning, Riyaz Singh. Good morning. Very good morning. Yes. So shall we start? Shall we start our session? So in this particular session, we are going to complete all the chapters. That is all the chapters in physics, okay? In physics, all the chapters in physics, okay? So first of all, topic flow. So first of all, a topic flow you should know, right? So each chapter are interrelated. Each chapter one to one are interrelated. Okay. So first, if we see with respect to charge, okay, with respect to charge, if we start from charge, okay, if we start from charge, there are three state of a charge, right? Actually two. So one is a state of rest. In this particular rest, we are going to talk about electrostatics. Okay, electrostatics. So in this electrostatic here we have two chapters again. One that is electric charges and fields. The next one electric potential and capacitance. Okay. So next one, the charge is in motion. Okay. The charge is in motion. So when the charge is in motion, here we have two types. Okay. One is current electricity. That is the third chapter. Current electricity. Current electricity. Okay. And moving charges, moving charges, moving charges, and magnetism, moving charges and magnetism. And fifth one, fifth chapter. Okay. Yes, Ayush Tagi. Yes, I know that tomorrow is your English examination. Okay. 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 Yes, yes. So for all the boards, especially it is CBSE students, okay? It is meant for CBSE students and it is very helpful for other board students as well, okay? Other state board students also, they can watch this live marathon, okay? It will be very useful for any state board students, okay? So today I'm going to stick on to CBSE board, okay? So here we are going to discuss in detail everything, okay? Every concept in detail. Got it? Okay. Okay, okay. Got it, got it. Yes, yes. Yeah, 22, not tomorrow. Yes. Okay. Fine. Yes, Ajay Krishna, I'll do derivation part. Everything I'll be going to do. Okay. Everything will be covered in this particular session. Okay. Fine. Everything. Everything. Yes, my name is Ashok SK. Okay. My name is Ashok SK. So today I'll be taking Mahamarathon of physics entire syllabus. Okay. Fine. I hope I answered all of your questions. Okay. Now, so fifth chapter, that is magnetism and matter. Okay. Magnetism, magnetism and matter. Magnetism and matter. And the sixth one, electromagnetic induction. Electromagnetic induction. And seventh one, that is alternating current. Okay. AC, alternating current. Abam, what is your question? Abam, what is your question? Yes, dark mirror. Sir, I did not study anything. Yeah, please watch this session. Okay, definitely it will be very helpful. Got it? Okay. Fine. Nandita, when will this session get over, sir? We need to study for English as well. Okay. So after this slide, you'll getting to know. Okay. After this slide, you'll be getting to know which chapter and how much time it is allotted for it. Okay. Sir, can I get above 95 in physics by seeing this lecture? Definitely. Why not? You can. Okay. 95%. Okay. Yes. Okay. Abam, how to not sleep while attending papers, sir? So if you prepared well, Okay, if you prepared well, you can answer those question paper. Okay, so not only question paper, any examination if you consider. So if you prepared well, so you'll not get sleep in the examination all. So you'll be busy with answering that paper. Okay. Yes, Rai Kumar. Okay, sir. PYQs. Yes, sir. PYQs I have added, but I have not mentioned the name. I mean, year of examination. Okay, year of examination. I have not mentioned. I've brought PYQ also. Okay. Yes, yes. SPS Preeti. Yes, definitely. Okay. Kulwan Singh, yes, we are doing PYQs also, but I have not mentioned PYQs. Okay, I have not mentioned it as a PYQs. So just I have bought entire content, whatever it is required for your board examination. Okay. Okay, Avam, all the very best. Thanks for your effort. Okay, you're doing a lot of time. I mean, at least 10 minutes you are there with us. Okay, all the very best for your examination. If you are preparing for examination. Okay. Thank you. Okay, Usha. I'm in 10th grade. Okay. So next year, you'll be in 11th. Okay. Revision are questions. So revisions, content, questions, numerical part, everything will be covered. MCQs, everything will be covered. Okay. Okay, fine. Sir, will you start a J advanced batch? So you'll be getting to know. Please, watch in the community sections where you'll get updates. Okay. Yes, class 12 boards. Yes, so from basics, I'll be starting, okay? From basic to advanced, okay? By this session, you can score more than whatever required, okay? So my target is above 95%, okay? Yes, dark matter, definitely I'll be explaining from the basics, okay? Fine. Yes, 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 okay. So let me complete this particular session, particular slide, so that you'll getting to know which chapter, how much time for, which chapter, how much time I have allotted for it, okay? Yes, complete a syllabus. Kanishka Sharma, complete a syllabus, okay? Yes, CBSE board, okay? So it will be very helpful for other state boards also. Right now, I'm concentrating on CBSE board, okay? If you are concentrating on CBSE board content, you'll be, thorough with your state board content, okay? Got it? Okay. Krishna M. Please wait for 2 minutes. You'll be getting to know. Okay. Yes, Abhishek Patil, Krishna, and Dev. Yes, yes. Yes, Dev. Okay. Fine. Wait for 2 minutes. You'll be getting to know how much time I have allotted for each chapter. Okay. Now, so after charge is in motion, that is uniform motion. Now, if charge is accelerated, okay, if charge is accelerated, so then we have eighth one, electromagnetic waves. Okay, electromagnetic waves. Under this electromagnetic waves, visible spectrum, okay, under this electromagnetic spectrum, we have a visible spectrum. It is the part of electromagnetic spectrum. So from electromagnetic spectrum, we will be having a ninth chapter, that is a ray optics, visible spectrum. Okay, nothing but we are talking about the lights. Okay, light. After studying about a light waves are both athava, or we can say that light exhibits both a particle nature as well as a wave nature, right? So by particle nature as well as a wave nature, we have one more chapter, that is a wave optics. Okay, wave optics. So after completing wave optics, we have 11th chapter, that is dual nature of radiation and matter. Dual nature of radiation and matter. Radiation and matter. Okay. After this, we have atoms. Again, we are going back to the nucleus state. Okay. Yes, Nikhilesh, I'll be starting very soon. Okay. Yes. Usha, yes, I'm from, yeah. Okay, now, atom. After this, I'm going to start with nucleus, okay, nucleus. And the last one, semiconductors, semiconductor physics. So we have a small part of it, okay, semiconductor electronics, okay, semiconductors and electronic devices, semiconductors and electronics devices, okay, fine. So total 14 chapters. Yes, in between, okay, I'm planning at least 2 to 3 breaks. That is not more than 20-25 minutes, okay, got it? Okay, now, so most wanted question, okay, that is how much time it will take, okay. So we know that the first 4 chapter of second year physics, okay, second year physics, that is the 12th grade physics, first 4 chapters are very, very high chapters, okay. High chapters means it has a lot of content in that, okay. So by keeping one thing, that is day after tomorrow you have an exam, therefore I am planning this electrostatics, complete electrostatic 2 to 3 hours, okay, 2 to 3 hours maximum, okay, 2 to 3 hours, fine, okay. Now, so current electricity, it is I am planning 1 to 1.5 hour, okay, 1 to 1.5 hour, and moving charges same 1 hour, okay, and magnetism and matter, so magnetism and matter, it is a 30 minutes, okay, 30 minutes, not more than 30 minutes, and electromagnetics, electromagnetic induction, that is 45 minutes, okay. AC, it is also 45 minutes, and electromagnetic waves, it is a 20 minutes, okay, because a lot of theory involved in this particular chapter, okay. Electromagnetic waves, yes Manu, correct, okay, yes. And here ray optics, ray optics, as it is a very big chapter, so I'm concentrating to complete 1 hour to 1.5 hour, okay. Wave optics, again it is a 45 minutes, again it is 45 minutes, and dual nature and radiation, okay, of radiation and matter, so I am planning it is for 30 minutes, and atoms and nucleus, both 45 minutes, and semiconductor physics, so maximum 30 to 45 minutes, okay. So this is excluding breaks, okay, excluding breaks. So in this particular session, okay, what is the speciality of this live session, okay, speciality. So in this particular session, you will be getting, okay, all the content, all the content means MCQ, numerical problems, derivations, everything, okay, everything. So here you'll be having MCQs, okay, so short answer type questions, and next one long answer type questions. In that, derivations, you'll be having questions, right? Yes sir, are you going to do derivation part? Yes, I'm doing it, okay. So numericals, numericals, and diagrams also, diagrams, okay, diagrams. And the most important thing is, so in this particular session, I'm going to discuss about, analysis, trend analysis, okay, trend analysis, analysis, 3 years analysis, okay. And so I'll be including, means not content, so which are the topics dropped for this particular board examination, 2024 year of examination, okay. So that is a dropped topics, I'll be adding, okay. I'm not discussing, I'll be just including in this particular PPT, okay, dropped topics, so that it will be very easy for you to understand which topic you no need to study, okay. Got it? Yes, I hope, yeah, students, please try to understand. So it is a, we have an instruction, that is PW Physics Wallah English channel, okay. Medium of instruction is English. Please try to understand, okay? I hope you guys will be understanding, okay? Got it? Yes. Yeah. Dev, correct. Usha, yes. Yes, Dev. Okay. Now, so let's get started. Our first chapter, electric charges and fields. So this is our trend analysis, okay? Trend analysis. Fine? Okay. Fine. Okay. I thought, medium of instructions. Okay. I'm really sorry for that. Okay. Miscommunication. Okay, fine. So here a trend analysis. If you see last 3 years paper, okay, last 3-year paper, and here and also means from which topic and for which topic and how many marks is allotted for this particular year, okay. So if you say Coulomb's law, okay, Coulomb's law, if you see 1 mark 2023, 2020 and 2019 across all sets, we have almost, okay, 1 mark 2 questions, 1 mark 2 questions, 1 mark 3 questions. That means 1 mark questions, at least 2 marks will be there based on Coulomb's law and electrostatic force and electric dipole, okay. And based on the 2 marks, that is a short answer type question, at least 1 question will be there, okay. So I'll be discussing this trend analysis only for this particular chapter, and the next upcoming chapters I'll be showing all these details, but after the session you can go through it, okay. So this time is very important for us to all the students are preparing for English examination and they are taking very important time and attending this online classes, okay. Got it? Krishna M. Okay, definitely. Okay, I don't disappoint you, Krishna. Okay, trust me. Fine. Okay. So next one, topic 2, if we consider electric flux and Gauss theorem. So if you see under this particular topic, you are going to notice that is 1 mark question, 1 question, and 2 mark question, nothing. So that means statement, nothing. 1 mark question, that is maybe MCQ or else unit wise they'll be asking, okay. Yes, Dev, I can understand. Okay, now 3 marks, 1, 2. Okay, this is the 3 marks. That is 2020. We got 3 questions, and in 2019, that is a 2 mark. I mean, 2 questions for 3 marks. And 5 marks, you can see 2 questions. Last year, 2023, we got 2 questions for 5 marks. That means 10 marks in this particular chapter. Okay, just imagine how important it is. Okay, yes. Okay, got it? Next. And a deleted topic and what you need to learn in this particular chapter, okay. So you can see, so this is according to the old NCERT, okay. If you are preparing from new updated NCERT, no need to look at this particular slide, okay. If you are using old NCERT, you have to concentrate here. So here I have mentioned page number as well as drop it topics from this particular chapter. You can see electric charge related only activity, the paper strip and making electroscope, and the conductors and insulator deleted only concept of earthing, that is the induction, okay. Induction process, it is removed. Fine. Yes, Adarsh, we will be doing. Okay, we will be doing definitely. Yes. Next, charging by induction, it is a deleted, okay. So all this content is dropped for this academic year, okay. So let's get started with our very first topic, that is electric charge. So first of all, what do you mean by electric charge? Already we know that it is a fundamental property of a matter, okay, which experience magnetic as well as electric effect. Simple, okay. It is a property of a matter. If you consider anything, any material, maybe it is an insulator, a conductor, semiconductor, whatever you consider, in that, okay, this particular charge is part of that material. Got it? Okay. So then this charge, how to define in exam paper, okay. So here you try to understand, it is intrinsic property which is responsible for electric force of attraction or repulsion between object. So this definition also we can write, okay. So or else the first one which I said, that is it is the property of a matter, okay. so which experience both magnetic and electric effect. Got it? And when you see, okay, this charge, whether it is a scalar or vector quantity, okay, so this charge is a scalar quantity because here we are not talking any direction. We are not talking about any direction of this particular charge. Just we are mentioning what is the magnitude along with its unit. Magnitude itself says that it is a numerical value and its unit. Okay. Yes, God bless you, Usha. God bless you. Okay. Yes, Bhumika, correct answer. No direction of a charge. So hence it is a scalar quantity. Okay. It is a scalar quantity. Next one, how many types of a charges exist in nature? Okay. How many charges exist in nature? Yes, answer please. How many charges exist in nature? How many charges? Yes, two types. Can you name those two types of a charge? With example, okay. We know that Abhishek Pali, three types. Actually, two types of a charges. Yes, three subatomic particles. If we consider atom, there will be three subatomic particles, that is a proton, electron and neutron, where neutron is a chargeless particle. So that is the reason we are not considering that as a charged particle. Okay, exactly. Okay, so here we can consider the first one, okay, positive 2. First, I'll write how many means, so 2. 2. The first one positive, the next one negative, that is the positive charge and negative charge. Okay, negative charge. And example, proton, negative, electron, okay, electron. And what are the units of a charge? What are the units of a charge? For a CBSE, if you are preparing for board level, Coulomb, that is enough. Okay, if you are preparing for competitive level, you need to know Coulomb, ESU, that is electrostatic unit. Okay, very good, Abhishek. Yes, Gyan. Yes, Bhumika, correct answer. So here, what are the units of a charge? So SI unit, if I consider, okay, if I consider SI unit, so this one will be Coulomb, is the SI unit of a charge. That is represented by capital letter C. Okay, and this Coulomb, it is related to CJ's unit, that is electrostatic unit. So this electrostatic unit is also called as Franklin. Okay, for boards we don't discuss about this Franklin. Okay, so here if I write the relation between 1 Coulomb, that is equal to 3 into 10 power 9 ESU. Got it? And 1 Faraday, it is a very big unit of a charge, very big. But compared to Coulomb, how much it is? It is 96,500 Coulomb. And what are the dimensions? Yes, Amul Mishra. Yes, ampere second, ampere per second, ampere per second. Let's see. Okay, now what are the dimensions? Dimensions, if we consider, what is the definition of a current? That I is equal to Q divided by T. That is the rate of flow of charge, or else the flow of a charge with respect to time. So here I need this charge, therefore I can write I into T, right? So Q is equal to dimensions of a charge. What is the dimensions of current? That is the A power 1, time, that is the T power 1. Therefore, dimensions of a charge, that is A power 1, T power 1. Got it? Rahul, correct answer. Yes, GAN, it is exact number, but approximate value we are considering 96,500. Very good, okay. Yes, electron volt, it is the energy of an electron. Okay, it is the energy of an electron. Got it? Ampere meter per second. Yes, okay, ampere meter second. You can use this. Okay, got it? Approximation, GAN. Very good answer. Okay, now let's move on to the next topic, that is explain the properties of electric charges. 2 mark question. Okay, 2 marks question. So here first and very important property, that is the quantization of electric charge. What is the meaning of a quantization? Quanta. First word, you concentrate on it. Okay, what is the first word? That is quanta. Quanta means fixed amount of electric charges. If you are charging a body may be positively charged or negatively charged. If you are charging a body, the fixed number of charges will be flowing from one body to another body. Yes, Kanishka saying PYQ will happen. Okay, very good. Manu, very good. Okay, that is a plus R minus NE. So how to represent in examination? Okay, so however we prepare, examination hall, we have to represent actual answer, right? So what is quantization of a charge? So here you can see the fundamental unit of electric charge is the charge carried by electrons, and it is unit Coulomb. E as a magnitude. What is the value of a E? That is a 1.6 into 10 power minus 19. Mr. Unknown, very good. Integral multiple of electron. Okay, integral multiple of electron. So here, what is the value of E? That is 1.6 into 10 power minus 19 Coulomb. So what does it mean? So here if I write Q, okay, here we have equation plus R minus NE. What is this? A plus indicates? This plus or minus indicates a nature of the body. Nature of the body. Okay. Nature of the body. And N indicates it is the integer 1, 2, 3, 4, 5 and so on. Where E indicates a charge on electron, that is 1.6 into 10 power minus 19 Coulomb. Right? So nature of the body. When do we use a positive and when do we use a negative? Right? For example, it is a neutral body. Okay, this is a neutral body. This is a neutral body. From neutral body, if I consider two cases, okay, two cases if I consider. So here only electrons are adding. Here electrons are removing. Transfer of a charge. Okay, transfer of a charge. In the first case, electrons are adding from neutral body. Okay, from neutral body. This is a neutral body, plus or minus, plus or minus, plus or minus. Okay, number of positive charge equal to number of negative charge. So from this particular charge, neutral charge, okay, neutral charge, if you see adding of electron, what will happen? Excess of electron. Okay, in this case, excess of electrons. Excess of electrons. So this Q value will be negative. Okay, excess of electrons. Very good. Okay, now in this removal of electron means deficiency. Deficiency of electrons. So that means the body become positive. So in the first case, the body has become negatively charged body. In the second case, the body has become a positively charged body. Right, Abhishek? Yes. Kanishka Sharma and Sonia Tagi. Yes. Bhumika. Maruf. Yes. Number of electrons. That is integral multiple. Okay. Please change that number of electrons. Instead of that, you can consider integral multiple. Okay. Yes. Entire syllabus. Okay. Shibani. Yes. Entire syllabus. Okay. Mr. Unknown YT. It's clear. Right. Okay. Got it. Now let's move on to the next concept. How many electrons are there in 1 Coulomb? Can you calculate? Already we know that. What is the formula? Right? What is the formula? That Q is equal to plus R minus NE. So they are asking how many electrons. That means N. What is the value of N? So here, ignore about this plus and minus. Just a magnitude I am calculating. Okay. So that means NE. I need N. Therefore, Q divided by E. What is the value of a charge they have given? 1 Coulomb. And what is the charge on electron? That is a 1.6 into 10 power minus 19 Coulomb. Okay, 19 Coulomb, right? So now, here, what is the value of this? 0.625 and this 10 power minus 19. If I shift that into numerator, that in negative terms becomes a positive. If it is a positive, that becomes a negative. Exactly. Okay, now, here 10 power plus 19. So here finally you can write 6.25 into 10 power 18. Electrons. Got it? Fine. Now, how many electrons constitute 1 microcoulomb? Here Q value, how much it is? It is a minus 1 microcoulomb. Convert that into SI unit, that is a 1 into 10 power minus 6 Coulomb. Can you tell me what is the answer for this? Okay. Can you tell me what is the answer for this? What is the value of N? What is the value of N? Yes? Yes, Kanishka Sharma. Okay, so slowly we will accelerate it. Okay, slowly. Okay, now. So here, what is the value? Same procedure you follow, you'll be getting the answer. Okay, now. Here, when electrons are removed, so it is a 10 power 14. So 10 power 14 electrons are removed from the neutral metal sphere, then the charge on the metal sphere becomes. Again, same formula, Q is equal to Ne. So here you need to concentrate on removal. Removal of electrons, that indicates it is a positive. So therefore, it is a positive. Okay, now. So they are asking about, the charge on a metal sphere. Charge that is equal to number of electrons, that is a 10 power 14. Charge on electron 1.6 into 10 power minus 19. So here you can see 10 power 14, 10 power minus 19. That becomes 1.6 into 10 power minus 5. And multiply and divide by 10 if I do it. Because we have to match with this option A, B, C, right? A, B, C, D. So here we have in terms of a 16. Therefore, I'm multiplying divide by 10. So here I'll be getting 16. And this 10 power, if I shift that into numerator, that becomes a minus. Therefore, 10 power minus 6 Coulomb. So finally, I can write a Coulomb charge, that is 16, positive 16 microcoulomb. So right answer for this particular question, that is option A. Option A. Okay, got it? Clear? Yes. Uzma, okay, sorry, because I was busy with the solving numerical. Okay, don't fail, okay? Got it? Now, let's move on to the next question or next concept. Explain the properties of electric charges. Under that, here we have a second one, conservation of electric charges. Conservation means cannot be created nor be destroyed. Simple, okay? Cannot be created nor be destroyed. So in this particular session, if we see this particular statement, conservation of a charge. So total charge of isolated system will remain same. Will remain same. Total charge will remain same. Got it? Okay. Now, here if you see statement, according to the law of conservation of electric charges, the total charge in the isolated system always remains constant. Okay. Always remains constant. But the charges can be transferred from one system to another system such that total charge always conserved. It's like a conservation of energy only. Conservation of a mass as well as energy. Got it? Yes. Meet Mehta, correct. Yes. Abhishek, yes, correct. Rahul, yes, correct. Gyan, correct. Ajay Krishna, exactly right. Okay. Hello Mukesh, welcome to the session. Arush Jain, welcome to the session. Okay. Now let's move on to the next concept. Next one, additive nature of the charge. Additive nature. What does it mean? We can add or subtract charges directly. Symbol algebra we can use. We no need to use that vector analysis. Okay, vector addition, subtraction, it is a very difficult compared to simple algebra, that is addition as well as subtraction. So here, whenever you see charges, you can add or subtract directly without using a vector laws. Got it? So this is the statement that the total electric charges of a system is equal to algebraic sum of electric charges located in the system. If system containing a charges Q1, Q2, Q1, Q3, Q4 and so on, then total charge. So for example, here you see Q1, Q2 minus Q3 plus Q4 and Q5 and minus Q6 and so on. Okay. So what will be the total charge of this particular system? So directly along with the sign we have to keep. That's all. Okay. Along with the sign. What is the value of Q1 plus Q2 and minus Q3? Okay. Q2 minus Q3 plus Q4 and the next one Q5 minus Q6 plus so on. Okay. This is the meaning of this additive nature. Got it? Additive nature. Okay. Now, next one, a system containing charges. Try to answer this question fast. Try to answer this question. A system containing charges 3 microcoulomb, minus 2 microcoulomb, plus 4 microcoulomb and minus 5 microcoulomb. What is the net charge of a system? Yes. Come on guys. Come on. What is the answer for this particular question? That is 3 microcoulomb minus 2 microcoulomb plus 4 microcoulomb and minus microcoulomb. Yes, 0. First answer. Yes. Ajay Krishna, definitely. So as it is a beginning of the session, So just I'm trying to, make you comfortable so that you'll be understanding each and every concept. Got it? Okay. Very good. What we have to do? Just add directly with a sign, okay? Plus 3, minus 2, because all the units, you can see microcoulomb only. Directly I can do it. Plus 4, minus 4. So here you can see plus 3, plus 4, that is a 7. Minus 2, minus 5, that is a 7. Minus 7. So 7 minus 7, that is a 0. Got it? Okay, total charge, it is a 0. Yes? Okay, now let's move on to the next question. Next concept, that is the charge is invariant. Invariant means the charge, the magnitude of charge do not change, whether it is in the state of rest or in motion. Like mass, at rest, it has a mass, while moving also, it has a mass. But when the speed is nearly equal to the speed of light or greater than speed of light, what happens to the mass? Mass going to vary. So we can say mass is a variant property. Okay, mass is a variant property where charge is invariant property. For example, if the charge is moving, okay, charge is moving, QV, if charge is at rest, QS, both are equal. For example, Q at a state of rest, okay, state of rest. So for example, here I consider 10 Coulomb, okay, in motion, whatever the speed of this particular charge, still it is a 10 Coulomb only. So that means charge is at rest, charge is in motion, both are equal. Got it? But what happens to the mass? So mass going to vary. That is m naught. This is a rest mass, okay? This is a rest mass. And under square root minus v square divided by c square, where v is the velocity and velocity only, c is the speed of light. Got it? Okay, I hope it is very clear. Okay, by this property of a charge, that is the invariant property of a charge, we have a 3 sub branches of physics. First one, if charge is at rest, what do we say? It is electrostatic. If the charge is in moving, charge is in motion, we can call it as electrodynamics, nothing but current electricity. If the charge is accelerating, electromagnetic waves. 3, by invariant property of a charge. Got it? Okay. Now let's move on to the next concept, conductors and insulators. Okay, conductors and insulators, just definitions. Just definitions you need to understand. So here I'll be using a simple presentation. Okay, so here plus minus, plus minus, plus minus, plus minus. And here you need to say number of positive charges and number of negative charges. Himanshi, hello, hello. Okay, fine. So neutral. Neutral means the total charge of this body, it is a 0. Okay, total charge of this body, total charge, it is a 0. Okay, hello, hello, hi. Now here conductor means same, it is also neutral, but what is the difference? What is the difference then? What is the difference? Here you can see a negative sign, right? Here you can see negative sign, here 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 negative sign. So in the conductors, what will happen? This one, okay, after the session, okay, let me announce one important thing. So after the session, you will be getting these notes, okay, don't worry. Okay, so there will be a link. If you click on that particular link, you will be getting the notes, okay, notes of this particular session. Got it? Yes. Here conductors, what will happen? These electrons are free to move, So these electrons only, we are calling it as a free electrons. Whereas insulators, here also same arrangement, plus or minus, plus or minus, plus or minus. Here also plus or minus, plus or minus, plus or minus. Here plus or minus. But this negative charge particle, okay, this negative charge particle do not move or do not change its position. What they will do is, just they'll move around the positive charge, just they'll be moving like this, okay, just they'll be moving like this, okay, around the positive charge. Okay, now, so this is all about a conductor. So first of all, what do you mean by conductors? So conductors are materials, okay, through which electricity can flow or else current can flow. Got it? Whereas insulator, in that material, the current will not flow. Got it? With respect to electricity. Now, by the definition, what are conductors? What is the main cause of the conduction of a substance? It is the free electrons that we know. The substance which allow electricity to pass through them easily are called conductors. The main cause of this conduction is due to presence of electric charges that we call it as a free electrons. Okay, so these are free electrons which are free to move inside the material. Note important examples: metals, human, animal bodies and earth are conductors, good conductors. Got it? Now next one, what are the insulators? Which allows the electricity, we call it as a conductor. What if the material do not allow the electricity to pass through them? Then it is the insulator. Simple. Okay, that is the insulator. Examples you can see, not metals, metals like glass, plastic, nylon and wood are the good example for insulators, right? So already I have explained the timings of each chapter. Okay, sprinkle. Please watch that first slide. Okay, you'll be getting to know how much time I'll be taking for each chapter. Got it? Okay. Now, what is electrification? So till now we said that the electrification means a transfer of a charge. Okay. So how do you transfer a charge? What are the methods of transferring a charge? So here electrification is nothing but gaining or losing of electrons is called electrification, or else method of charging a material is called electrification. In this electrification, here we have three types. The first one, that is the friction, second one conduction and third one induction methods. Okay, the last one, induction, it is removed from the syllabus for this particular year. We have a two, that is a friction as well as the next one, conduction. Right? Very good, very good. See, some students are answering all my questions. I appreciate their effort. Okay, may not call their names immediately. Okay, I'll be explaining the content. I may not be able to see all those names, but definitely it is a good effort. Okay, now next one, electrification. What do you mean by electrification? The process of adding and removing of electrons from the surface of a body is called electrification. And the methods of electrification, here we have three types, that is a friction, conduction, nothing but a contact, the last one, induction. So this induction, that is removed. Hope you have seen that dropout topics. Okay, now so here methods of charging. The first one, friction. What do you mean by friction? If I consider one body, okay, another body, so rubbed over each other like this. Okay, so what will happen? So if you do this, your hands will become warm. What is the reason behind it? It is a friction, right? It is a friction. So here heat will produce. Due to that heat energy, the electrons in the metals or else materials, what will happen? The free electrons will go out of the surface, then it will move to the another material. So this method of transfer of electrons, we call it as a friction. Got it? So here you can see, whenever two bodies are rubbed over each other, some electrons from one body is transferred to another body. So for example, if I consider electrons are getting transferred to A from B. Okay, so here a force are applying. Okay, frictional force is applying on two bodies, nothing but rubbed against each other. Then electrons are getting transferred. So here what will happen? So initial mass of A and this one initial mass of B. After friction, what happens? Electrons will transfer. Electrons will transfer means what happens to the mass? Mass of this material is also going to change because there is a transfer of electrons. Each electrons have a mass, right? So along with that mass only, the charges are transferring from one body to another body, right? Very good, Mr. Unknown YT. Very good. Okay, now here after friction, what happens? The first body, if I consider final mass of, okay, final mass of A, what happens? Initial mass of A minus how many electrons are transferred? multiplied by mass of the electrons. What about the final mass of the body B? Final mass of the body B, that will be initial mass of the body B minus plus here, okay, plus mass of electrons after friction, okay. Got it? Okay. Now, transfer of electrons is there. Very good. Okay. Mass divides. Kanishka Sharma. Very good answer. Okay. Mr. Unknown. Mass also transfer. Very good. Okay. Charge transfer through flow of electrons. Very good. Okay. Right. Next one. Example, if we consider glass rod as well as silk cloth. Initially, okay, initial or else before friction, neutral, both are in neutral, right? Both are in neutral. After friction, after friction, what happens? So there's a glass rod, okay, there's a glass rod. After friction, glass rod become positive and silk cloth becomes a negative charged. Why? Because this glass rod has number of free electrons more compared to silk cloth. The same example if we consider ebonite rod. So before both are neutral, after friction, what happens? This ebonite rod becomes a negatively charged body and Cat4 becomes a positively charged body, right? Positively charged body. Because this Cat4 compared to the ebonite rod, it has a more number of free electrons, right? Okay. Now, this is about methods of charging. That is the first one, friction. Now, based on this, here I have one numerical problem, okay? Based on this, I have one numerical problem. Try to solve this, okay? So first question you see, when a piece of polythene is rubbed with a wool, a charge of -2 into 10 power -7 Coulomb is developed on a polythene. Developed means the charges have flown from wool to polythene. What is the amount of a mass which is transferred to the polythene? Simple, okay? So here N we need to find out, right? Because mass if you find, okay, mass if you want to find, you have to know number of electrons are transferred, then mass of each electron, right? So here you need to find out N because you don't know what is N. By quantization of a charge, you can use this relation, right? I am talking about a magnitude, therefore it is a Ne. I want to find out N, therefore here Q divided by E. What is Q? That is a 2 into 10 power -7 divided by 1.6 into 10 power -19. Okay. Now here substitute the values. What is the N value? That is the 2 into 10 power -7 divided by 1.6 into 10 power -19. This is for N value. And what about the mass? Mass of electron, that is a 9.1 into 10 power -31 kg. After solving this, okay, you'll be getting to know what is the mass of transferred electrons. I hope it is clear. Yes? Thumbs up, guys. Fast. Is it clear? Is it clear? Yes, please tell me. Is it clear? Yes? Yes, thank you. Now, let's move on to the next concept, that is conduction. So, friction it is over. Okay? Yes. Friction it is over. Now, here one more method of transferring of a charge, that is a conduction. Charging an uncharged body by bringing it into touch with some other charged material or body. For example, okay, this is a neutral, okay? This is a neutral body. This is a neutral body. And this is a charged body, okay? This is a charged body. Charged body. So here what I will do is, here I'll make them in contact. What happens? It is a neutral and it is a charged body. If it is a positively charged body, okay, if it is a positively charged body, what happens? So this charged body, what will happen? This neutral, from a neutral atom, okay, from neutral atom, the charge will be flowing. Hence, this body is also become charged body, okay? What if both are charged body? Both are charged body. The flow of charges occurs till both the bodies attain same number of charges, nothing but equilibrium. Yes? Hello, Ziddi, hello, good morning. Okay, welcome to the session. Now, so there will be a transfer of electrons, means of charges. Then what will be the final charge on this? And what is the final charge on this? Here we have a simple formula, that is final charge on each sphere, that is Q1 plus Q2 divided by 2. If I consider, okay, it is not a neutral, okay. So if I consider this is a Q2 and this is a Q1, then it will be, final charge will be, that is Q1 plus Q2 along with the units. Very good, very good. Charge divides, very good. Okay. Yes. Yes, you can. Okay. Shabari, yes, you can. Yes, Aditya Kumar, right answer. So condition, what should be the condition for conduction? See, dimensions of both the metal spheres should be same. Means radius should be same, volume should be same. But mass, it's okay. If the one sphere has more mass compared to other one, it is fine. Okay, nothing will happen. But here, this, we are talking about especially about the charges, right? So here mass doesn't matter, but here charges as well as dimensions of a sphere, it is more important. Okay, so if you see condition, the first condition, two bodies should be metallic, okay. Next one, they should have identical size, means dimensions, same radius, and it's okay if they have a different masses. Okay, now here what happens, once I make them in contact, nothing but a conduction takes place, right? Conduction takes place. Yes. Okay. Yes, fine. When they are made in contact, the charges redistribute among sphere till both have a same potential. Potential topic, second chapter. Okay, where we can learn about it. Okay, now let's move to the next concept. What would happen when two oppositely charged objects are brought in contact? Opposite charges. One is positive charges, another one is negative charges, and both of them, what we did? Contact. Then what will happen? There is a flow of charges between those two bodies. What will happen? Finally, equilibrium condition. Equilibrium condition means number of charged particle in this first metal sphere and the number of charged particle in the second metal sphere will be equal. Means becomes a neutralized. Number of positive and negative in the first, number of positive in the second, both will be same. Exactly. Yes. Equilibrium means the same number. Equilibrium. Thermal equilibrium means temperature is same. Okay. And equilibrium conditions, I hope you have learned in work, energy and power first year. Okay. Yes. Got it. So here equilibrium means a simple thing. You see, one has, for example, one has a 10 coulomb. Okay. Charge of a 10 coulomb. Other body has 5 coulomb. So both made into the contact. What will happen? The example, flow of water you consider. One tank has lot of water, say 5 meter height. Another one is 2 meter height. If you open the tap, what will happen? The water starts to flow from that 5 meter height to 2 meter height. Why? Because there is a difference in a pressure. In the same way, here difference in potential. Due to that, the charges flow from higher number to lower number till both the metal sphere gains a equal number of a charge. Yes. Okay. Now, so this is the answer for the question. The charge acquired by the two objects gets neutralized. Next, state and explain Coulomb's law. This is very important. Okay. This is very important. What does this says? First of all, what is this Coulomb's law? So already we are talking about attraction as well as repulsion properties, right? Two like charges repel, two unlike charges attract. Yes, of course. Why? Because there is a force of attraction or repulsion. But that is a nature. But how to calculate how much force acting between them? By using Coulomb's law. Coulomb's law states that the force between two point charges. Point charges means the spatial size of a charge compared to the distance separated by 2 point charges, the distance is more compared to the size of the particles. For example, if see, the size is very small, right? Size is very small. Distance you consider, it is very big. So here we can consider these two are point charges. Okay. The force between 2 point charges is directly proportional to the product of the two charges. What are those? Product of two charges. That is the Q1, Q2 if I consider. Okay. Q1 and Q2, the product of Q1 and Q2, that is Q1 into Q2, and inversely proportional to the square of the distance between them. So if I consider distance between them is a r, okay, so mathematically if I express, that is the force is directly proportional to the q1 and q2, and the force is inversely proportional to the 1 by or else 1 by r square, okay. So here I can write force is directly proportional to the product of charges q1 q2 divided by r square. I want to eliminate this proportional, okay. So what I'll do, I'll consider proportionality constant, that is a 1 divided by 4 pi epsilon naught q1 q2 divided by r square. Here I'll be using, for simplification, this entire term as a k. K is a proportional constant, q1 q2 divided by r square. And don't get confused with a capital letter k, okay, because this small letter k is a constant, okay, and capital letter K, it is a dielectric constant, okay. It is a proportionality constant, this is a dielectric constant, okay. Don't get confused. This value as well as this value will be given in the question. If there is any question based on this topic, that is the force, they will be given a value of that K. Got it? Okay. Very good. Okay. Now, so here, what is this K? What is this epsilon naught? Epsilon naught is the permittivity of a free space, where K is the dielectric constant. And what is the value of a permittivity of a free space? Permittivity of a free space, that is given by 8.854 into 10 power minus 12. Okay, minus 12. Coulomb square, okay, Coulomb square per Newton per meter square. Okay, this is the value, magnitude of epsilon naught. And this K value going to vary from medium to medium. Okay, now let's move on to the next concept. The force between 2 point charges is F. Okay, what is the force between 2 point charges? That is a F. What is the new force when distance between them is half? Can you answer this question? Yes, answer this question. What happens if a distance is reduced to half? Please answer. Yes. Welcome, Ghosh. Welcome to the session. Ajay Krishna. Yes. 4 times. Very good. Manu and I don't think if I pronounce your name right, Agam. 4 times. Yes. Exactly. See, by the statement, force is direct inversely proportional to the square of the distance, right? So here what happens to the R? R is reduced to half, right? R is reduced to half, right? The same value substitute here. 1 divided by R by 2 whole square. So whole square, can I write it as a 1 divided by R square divided by 4? This one, can I shift that into numerator? So finally I'll be having 1 by R square. This is a new force, right? This is a new force. So this is a new force. What about 1 by R square? This is old force. F dash 4 times of F. New force will be 4 times of old force. Got it? Okay. Now let's move on to the next question. Nature of the force. Nature of the force means it depends on what type of a charge it is having. For example, 2 particles having a same charge means positive, positive, like charges, okay? Positive, positive or negative, negative. Positive or positive. Positive or positive or negative or negative. Okay, negative and negative. Same charges or like charges. What happens? Repel each other. And unlike charges means charges can be positive negative pair or else negative positive pair. By this, unlike charges, what is the nature means? It is the attraction. What is the nature of a force? That is the attraction in nature. Attraction. So in between, we have considered it is in a free space. Free space means in an air medium. That is the reason we are writing epsilon naught. What if we keep these 2 point charges in any other medium other than air, like water or else dielectric medium, glass? What happens to the force? So this force, nothing but Coulomb's force, it is dependent on medium, right? Very good, very good. Okay, now let's move on to the next concept. Define dielectric constant. Dielectric constant means, try to understand. So here instead of air, what if I keep, okay, what if I keep a dielectric medium? Dielectric medium K. So if it is the air, okay, if it is the air, For example, if it is a air, what is the force? That is F is equal to, okay, F is equal to K Q1 Q2 divided by R square. That is 1 Q1 and Q2, right? So this K I'll be writing 1 divided by 4 pi epsilon naught, okay? So this is a air medium. What if Q1, Q2 separated by same distance? Distance is same, that is R only. The same arrangement, instead of air, I'll be keeping in a water. Okay, dielectric constant 82. So here I'll be keeping in water. Okay, these two charges separated by same distance, I'll be keeping in water. Okay, I'll be keeping it in a water. So what happens here? You see, this is a dielectric constant K, capital letter K, not a small letter K. That is a capital letter K. What happens? So dielectric constant means, what is dielectric constant? See, dielectric constant is nothing but a relative permittivity between medium and air. So here this one can be written as permittivity of a medium to the permittivity of a free space. Here I need this a medium, right? So epsilon m. So I can write K epsilon naught. So here formula for this case, it will be, okay, medium. So 1 divided by 4 pi in place of epsilon naught. When you use epsilon naught, when it is in air. What if it is in a water? Here you can use epsilon m q1 q2 divided by r square, right? So substitute the values. 1 divided by 4 pi epsilon naught. In place of epsilon m, I can use k epsilon naught q1 q2 divided by r square. Okay, now I'll take a k outside. What are the remaining terms? 1 divided by 4 pi epsilon naught q1 q2 divided by r square. So finally it is original force divided by dielectric constant. So here what happens? Dielectric constant, the force will be reduced by, what is the dielectric constant we have used? Okay, now dielectric constant, just now we have discussed about dielectric constant, that is a ratio of permittivity of a medium to the permittivity of a free space. Simple definition. Okay, simple definitions I am giving. Dielectric constant of a medium is defined as the ratio of a Coulomb's force between 2 point charges placed in a vacuum to the Coulomb force between the same two charges placed in a medium at the same distance apart. Okay, what happens to the force between 2 point charges when dielectric slab is introduced? Okay, here the formula will be reduced. Okay, dielectric slab, force in a medium, that is given by force in a air divided by K, that is the dielectric constant. And what is the value of a K? Infinity for conductors. Please remember these numbers. K is, that is the 82 for water. Got it? Okay, now let's move on to the next concept. Write a Coulomb's law in vector notation and explain it. So original formula, F is equal to 1 divided by 4 pi epsilon naught q1 q2 divided by r square. This is a magnitude. Okay, this is a magnitude. Very good, Shweta Mishra. Okay, now here if I write in a vector form, so what will happen to the formula? 4 pi 1 divided by 4 pi epsilon naught as it is, q1 q2 as it is. Here in place of r, what is the number of q1 and q2? Same numbers you have to write, r square, and here unit vector, that is r1 cap. Or else f1, okay, here also f12, here f12, 1 divided by 4 pi epsilon naught q1 q2. If we consider this as a vector only, then it will be r12, okay, r12 cube, here r12 vector, because unit vector can be written as r vector divided by magnitude of r vector. Okay, so by using these conditions you can write in a vector form. I have used other one, f12, force on a charge 1 due to charge 2. Here they have considered force on a charge 2 due to 1. Both are same. Got it? Yes. Vipul Singh, correct answer. Okay. Yes. Got it? Okay, guys. Now, let's move on to the next concept. That is, state the limitation of a Coulomb's law. So, Coulomb's law limitation. What are the limitations of this particular Coulomb's law? See, here the first one, it holds good for point charges only. At rest, okay, at rest, they are not moving. Both should not move. Any one of the charge is moving, that's fine, but both charges should not move. One should be at rest, or else both should be at rest. But both the charges should not be moving. That is the first limitation. Second one, basically an experimental law. It is a basically experimental law. It is not a theoretical, it is experimental observations. Okay. Now, for the distance less than 10 power minus 15 meter, it loses its validity. Below the value of this, okay, below the value of 10 power minus 15, that is for me, okay, for me meter, FM. So, what happens? This Coulomb's law is not valid. Got it? Yes, Ajay Krishna, correct. Okay, now, it is a medium dependent. Why? See, it is in a free medium. What is the values? 1 divided by 4 pi epsilon naught, Q1, Q2 divided by R square. In a medium, what happened? It is reduced to dielectric constant, whatever a dielectric constant, that much force is reduced, right? So this proportional constant is a dependent on a medium, not like universal gravitational constant, okay, that capital letter G. Okay, now last one, that is, it is not a universal law like a universal gravitational law. I hope it is clear. Okay, now let's move on to the next concept. Define 1 Coulomb or define SI unit of a charge. Here, try to understand, they have asked define SI unit, define, not mention. Mention SI unit of a charge means that is a Coulomb. But define SI unit of a charge means you have to define 1 Coulomb. Remember the formula? F is equal to 1 divided by 4 pi epsilon naught, Q1, Q2 divided by R square. If we replace R as 1 meter, Q1 and Q2 as 1 Coulomb, and F as a some value, okay, what is the value of that F you will be getting after substituting Q1, Q2 and R values? You see, from Coulomb's law, same formula they have used. What are the changes they have considered? Q1, Q2, it is a 1 Coulomb, and separation, that is a 1 meter. And what is the force? That is a 10 power 9 into 10 power 9 Newton. Okay, mathematically. But definition wise, how do you represent in examination? See, charge said to be 1 Coulomb when it is separated by identical charge placed in a air or vacuum at a distance of 1 meter repel each other with a force of 10 power 9 into 10 power 9. Okay, right? Now, for any updates, yeah, students are asking some updates. See, if you want any updates, no, please visit same YouTube channel, and there will be a community section. Okay, in that community section, you'll be getting all the updates. Okay, very good, very good. Okay, got it. Now, next one, 3 charges Q placed at a corners of equilateral triangle of a side L. Find a force on a charge Q placed at a corner. So, what is the shape they have given? That is a equilateral triangle. So, let me consider this is A, B and C. Okay, and the charges, this is a Q, this is also Q, this is also Q. Why? Because they have mentioned it as a Q. 3 charges. Now, what they are asking? Force on a charge placed at a corner, any corner. Okay, equilateral triangle means all the angles are equal, 60 degree. Okay, what is the total internal angle of a triangle? That is a 60 degree. So 60 degree if we consider, okay, let me consider the first one. Okay, this one, force on, okay, here I want to calculate force on Q at C. Okay, at C. That means what is the force? What is the force on a Q due to a charge at a point Q? Positive, ripple, right? Direction of force, this one. What is the force then? What is the force? 1 divided by 4 pi. Instead of 1 divided by 4 pi, I'll be writing K, small letter K, not capital letter K. Okay. Now K Q1 value, that is a Q. Q2 value, that is also Q, divided by what is the length? It is a L, because they have given L square. Okay, now this can be written as Q square, KQ square divided by L square. Now, charge on a Q at C due to charge due to at B. Okay, what is the force? Again, it is repulsion. So this charge is also F is equal to KQ square divided by L square. Now, what is the net force? What is the net force? What is the net force on this charge? You can see net force will be in this particular direction. Okay, vector analysis. So here I can write this one as F net, right? So F net, it is given by F net. You can use F1 square plus F2 square plus 2 F1 F2 cos theta. Use this formula, or else the shortest formula for resultant, that is given by 2F cos theta by 2. Okay, this is the shortest formula. You can use this one or this one. It's your wish. Okay, sir, when will be using this formula and this one? So this formula will be used when F1 and F2 are not equal, and this one you can use when F1 and F2 are equal, right? Here you can observe KQ square divided by L square, KQ square divided by L square, both are equal, therefore I'll be using this one. Okay, now, so simplification, nothing else. Okay, F net, that is equal to 2F and cos 60 divided by 2, right? Cos 60 divided by 2. 2F cos 30. What is cos 30? That is a root 3 by 2. 2 get cancelled, right? What is the answer? Root 3F. Then what about the F value? That is the root 3 KQ square divided by L square. Simple. Very good. Gain knowledge. Excellent. Vipul Singh. Yes, maybe that is the root. Very good. Ajay Krishna. Very good. Okay. Shibani Rudra Paul. After the session, you'll be receiving this entire session notes. Okay, don't worry. Got it? Now, let's move on to the next question. It is clear, right? Yes, this is the F net. Here I'll be writing F net. F net value, that is a root 3 K Q square divided by L square. I hope it is very clear for everyone. Okay. Now let's move on to the next question. That is the superposition principle. Superposition principle, it is related to multiple charges. Till now we have discussed about a force between 2 point charges, right? What if there are more charges, means more than 2 charges, then what is the force between them? And what is the force on a single charge particle due to all other charge particles surrounding on it? Okay, surrounding it. Okay, so for that, here we can use just add. What type of addition? It is a vector addition. Already we know that general formula, that F is equal to K Q1 Q2 divided by R square. It is for F1, next F2, next F3, next F4, like that, so on. So what you have to do, just add vectorly. Vector addition, nothing else. Previously we have done no? Same way. Previously we did no? Same way. Got it? Now, sir, use upper formula please. Yes, you can use. Okay, you can use. So length will become more. Got it? Fine. Next, that is a distributed charge system. Distributed charge system means, till last slide we have discussed about the point charges. Okay, point charges. If I consider one metal, and on that metal the charges are distributed uniformly. Okay, uniformly. So here we have a uniform distribution. Okay, charges uniform distribution. So for that, okay, if charges are distributed on over the length, okay, charges distributed over the length, then so here you can write, this is the lambda and this is the length, and the charges are distributed plus plus plus. Example, I'm considering plus plus. You can consider that is the negative also. Okay, so this linear charge density, when a charge is distributed over a length, is called linear charge density. Okay, now how to define this? Linear charge density, it is given by lambda, and mathematically it is a Q divided by L. Okay, and unit, what is the unit of a linear charge density? Like mass charge density, mass density means mass per unit volume, that is a mass density. Charge density, charge per unit length, it is a linear charge. Charge per unit area, that is a surfacial, or else areal charge density. Charge per unit volume, that is a volumetric density, right? Volume charge density, right? Based on how do you consider, that's how this density is going to change, okay? Now, what is the unit? Unit of a charge, that is a Coulomb, right? That is a Coulomb. Unit of a length, that is a meter, and this can be written as Coulomb per meter. Got it? So, the same charge, okay, the same charge distributed over area, area, okay, this is area, and here the charges are distributed. Same positive charges. You can consider negative charges also, no problem. Positive, positive, positive. So this is the area. Area, right? Area, how do you write? Area, this is, if you consider this is a length and this is a breadth. Length into breadth, what will happen? Length into, okay, area, it is given by A, length into breadth, right? When a charge is distributed over an area, it is given by sigma Q divided by A. This one we call it as a areal charge density. Got it? Now, in the same way, for what if the charges are distributed over a volume, throughout the volume, then. So let me write here unit of this particular areal charge density unit. So same Coulomb, but here per meter square. Coulomb per meter. Why? Area. What is the SI unit of area? That is the meter square. Now, volume charge density. When a charge is distributed over volume. So same way, here you can consider this is given by rho, that is Q divided by V. Q divided by V. But I am telling you, this is going to be very, very important, because this one we are going to use and this one we are going to use in upcoming derivation part. Yes, charge per unit area. Got it? Very good, very good. Okay, now, what is the SI unit? SI unit is Coulomb per meter cube. Sir, here meter per second means Coulomb per second. Here Coulomb per meter square, Coulomb per meter cube. Why? Because this one charge is distributed over the length. Here charges are distributed over the area. Here charges are distributed over the length, where breadth as well as height. That means entire volume. Entire volume. Got it? So this is how. So here you can consider this is a volumetric, linear, as well as areal charge density. Got it? Okay. Now, I don't know if I pronounce your name right, okay? If I pronounce it wrong, don't mind, okay? Gogeta. Is it right? Gogeta? Yes? Okay, charge per unit volume. Right. Now, let's move on to the next concept. Electric field. Now, next concept, electric charges is over. Electric charges completed. Done with electric charge. Very important concept. Done with electric charges. Gogita. Okay, Gogita. Okay, fine. Still, if I pronounce it wrong, don't mind, okay? Hello, Mr. Haz. Hello. Welcome to the session. Okay, Ujjwal. Welcome to the session. Santoshi Chaudhary. Welcome to the session. Okay, now, fine. The first part, it is clear. Electric charges. Now, we are moving on to next topic, that is electric field, okay? Now, field means it is a region, or else a place, or else a location. But with respect to what? It is the electric field. Electric field means with respect to charge. The field around the charge, or else the place around a charge, or else a region around the charge in which electric force exerted. That one we call it as the electric field. Is it good? Yes. Ring derivation too. Yes. Everything we are going to do it. Okay. Manu already answered. Very good. So for example, here I'll be considering a charge. Okay. Here positive charge I'm considering. Okay. So this is the field. This field only we are considering electric field. What does it mean? For example, there is a one charge is there. Okay. What is the force on this charge means? The charge value, it is a 1 Coulomb. Okay. 1 Coulomb. No force because it is out of the region. Now this same charge, 1 Coulomb charge only. Okay. 1 Coulomb charge only. I'm keeping it here. no force is acting on it. Still here, no force acting on it. But once it is inside that region, then there is a force acting on it. Okay, and if it is here, force is acting away from this particular position. So this reason we are calling it as a, okay. Okay, now this is electric field. Now 3D space around a charge in which it can exert a force on another charge. What is the charge here I have considered? 1 Coulomb. 1 Coulomb have considered, okay. Got it? Michael, yeah, we can, but the instructions, it should be in English, okay, that is the problem, okay. So in Hindi, I think there are live marathons are going on, PW platform, you can go and watch it, okay. This is, PW English, okay, yes. Now, so here you can see electric field due to point charges. So this one, easy way, how to define it? Intensity, electric field intensity, nothing but how much of force acting on per unit charge. Per unit charge means on 1 Coulomb of a charge. Yes, optics also, everything will be covered. Okay, now, here the force per unit charge. Try to understand this one, okay? Force per unit charge, force per unit charge. So formula, force per unit charge, force per unit charge. Got it? And what is the force? Coulomb force we already learned, right? What is that? What is that? K, Q1, Q2. Instead of that, I'll be writing capital letter K, small letter, small letter K, capital letter Q, small letter Q divided by R square. Okay. Now, by this definition, K, Q, Q divided by Q, R square. Q, Q get cancelled. What is the answer? K, Q divided by R square. Right? So this Q also can be written as a small letter, or else same, write a force only, okay, force only, and K, Q in place of a small q, that is a 1 Coulomb divided by R square. Okay, this is also a definition of electric field. Finally, electric field, it is given by, okay, small letter K, I'll be using, okay, small letter K only, R square, okay, R square. This is the mathematical formula, and the distance, okay, if it is a 1 Coulomb charge, and distance it is a r, okay, distance it is a r, force will be acting outward. Got it? Now, quant unit, what is the unit? According to the definition, force per unit charge. What is the unit of a force? That is a Newton, symbol N, and what is the unit of a charge? That is a C. Here I can write Newton per Coulomb. Got it? So Newton per Coulomb is the unit of a charge. Unit of electric field. Now, quantity. Electric field is a vector quantity or a scalar quantity? Please answer this. Yes, vector quantity or scalar quantity? Fast. Vector quantity or scalar quantity? Mead Mehta. Exactly. KQ divided by R square, unit is a Newton per Coulomb. It's a vector quantity. Then what is the direction? If it is a vector quantity, what is the direction? Along the direction of force, okay? Along the direction of force. So here, it is a vector quantity. It is a vector quantity. It is a vector quantity, right? And direction, what is the dimension? Dimension, it is a force, right? Force per unit charge. What is the dimension of force? M power 1, L power 1, T power minus 2 divided by charge, that is the 80, right? So here you can write finally M power 1, L power 1, T power minus 3 and A power minus 1. This is the dimension of electric field. Got it? Ankit, welcome to the session. Yes, Shweta Mishra, vector, very good. Ajay Krishna, Meet Mehta, as well as Gogita, vector, yes, correct. Okay, now, fine. So when you write equation, that is the electric field due to point charge, that is given by KQ divided by R square, right? Sometimes we can write it as a KQ divided by R square. Both are right, okay? Both are right. Both are right. Small letter and capital letter Q, nothing but a charge itself, right? Now, here you can see E as well as R means a separation. How it is related? How it is related? E is inversely related to R square. Hence this graph. Okay, now let's move on to the next concept. What are the factors on which electric field at a point due to point source point source charge depends. So remember this formula, K Q divided by R square. It depends on K. Why? That is the 1 divided by 4 pi epsilon naught. Epsilon naught indicates a medium, and Q charge, and R square, it is the separation. So same, use the formula and write the dependent factors. How to write? Here you see the first one, magnitude of a charge, done. Next one, the first one, magnitude of a charge, it is done. Second one, the distance between the point and a charge. Okay, that is the R, and the medium between the charge and the point, that is the epsilon, right? 3 factors. Got it? Very good. AI solve. Okay, solve medium, charge and distance. Exactly. Yes, along F. Correct? Very good, guys. Very good. Very good. Keep it up. Keep it up. Now mention the expression. This is how they'll ask questions. Okay, electric field in a vector form. Just we need to add unit vector to show electric field in a vector form. Just you need to add, that is unit vector, that is R cap. Got it? Okay. Now write the expression for intensity of electric field in a vector form and they explain the terms. Already we done that. Okay, go through this slide. Now next one, find the expression for the electric field due to system of charges by using superposition principle. Superposition principle is nothing but E is equal to E1 plus E2 plus E3 plus so on, right? Addition, vector addition, we have to do it. Okay, now what we have to do it? So same, K Q1 divided by R1, K Q2 divided by R2, K R square, right? R square, K Q3 divided by R3 square and so on. So this is a superposition principle with respect to electric field. Simple. Just addition, vector addition, nothing else. Exactly. E1 plus E2 plus En. Find each electric field and do the vector sum. Super. Okay. AI Sol, correct. Exactly. Kaira, correct. And Shweta, exactly. Okay. Yes. Should we use R cap? Yes. Should not we use R cap? You should use R cap. So here what you need to do is R cap you add. R cap. Okay, R cap. That is R1, here R2 and here R3 cap. Exactly, because it is a vector quantity, right? Very good. Sumati, good afternoon. Welcome to the session. Okay, now let's move on to the next concept, that is electric field lines. What is the electric field lines? So for example, experiment wise, if you see two charges, if they placed nearby, if they get repelled, means like charges. If they attracted, they are unlike charges. But theoretically, how do we get to know if there is electric field or not? By taking imaginary lines in account. Those lines we are calling it as a electric field lines. Getting my point? Okay. Yes. Okay. Positive outwards for a positive charge. Very good. R cap shows the direction. Very good. Yes, I am fine. I hope you are doing well. Now, point charges, negative inwards. Very good. Okay. Now here we are talking about electric field lines. Sometimes I may pronounce it as a magnetic field lines. Okay. Try to understand. In this particular session, I'll be considering electric field for a few minutes. Okay. Now, next one, if you see, these are imaginary lines of a force in an electric field of a charge. Okay. Lines are the path along which a free isolated unit positive charge moves or it tends to move. Okay, positive charge. Positive charge means Q is greater than 0. Nothing but a positive. How electric field lines move? If it is a positive, it is moving away in all direction. Okay, in all direction. Negative charge means Q is less than 0. Negative charge. Okay, so here you can see the electric field lines are radially inward. Here radially outward. Okay, in this particular case, radially outward. And in this case, radially inward. What is the direction of electric field lines? For a positive, it is radially outward. For negative, it is a radially inward. Got it? Yes, my dear students. Yes. Now, Exactly, outward for a positive. Instead of saying outward, please try to say it is a radially outward. Radially outward, okay? Because outward means it may be have any direction, right? Radially outward means with respect to radius. Okay, now let's move to the next concept, that is sketch the electric field lines in case of an electric dipole and two positive charges. Here you can see the cases. Please go through this. Dipole means two equal and opposite charges placed in a minimum distance or else separated by a small distance. Got it? And this is for two positive charges. Two positive charges, what happens to the electric field lines? Two positive charges repel each other by the electric field lines we can represent by this. Okay, here you can see spacing that indicates a, there is no electric field. It is a zero electric field. Okay, now next one, draw the electric field lines of a uniform electric field. So this is the diagram you need. Here you can observe straight lines and direction. So uniform electric field, okay, uniform electric field means direction and magnitude. Direction and magnitude should be same. Then only we can call it as a uniform electric field. Okay, here electric field, right? Yeah, electric field. So this is electric field. Got it? For example, can you tell me, is it a uniform or non-uniform? Yes. Can you tell me, is it a uniform or non-uniform? Yes. Density shows the magnitude. Exactly. Closeness of the field lines shows yes, for unequal charges, uniform. This one, second one. This is the first one, okay? And this is the second one. First one, yes, of course, it is a uniform. And what about the second one? Second one, non-uniform. Manu, I got answers, right answer from Manu. Yes, this one is non-uniform. You see, if we consider a direction, at this point, if I draw one tangent, okay, at this particular point, this is the direction of electric force. And if I take this point, direction of electric field is this point. See, direction is changing, means direction is not constant. If direction is not constant means it is a non-uniform electric field. Yes, Sumati, correct. Yes, sir, it is not uniform. Exactly. So this one, non-uniform electric field. Non-uniform electric field. Now let's move on to the next one. Properties of electric field lines. What are the properties of electric field lines? The first one, remember positive and negative charges. Okay, remember positive and negative charges. So from positive charge, what is the direction of electric field lines? Radially outward. Negative charge, radial inward. First property. Okay, now electric field lines are a geometrically representation of a strength of electric field. Okay, that means more the dense, more is the electric field. Okay, strength of the electric field. Now next one, electric field lines are originating from positive charge and terminate on the negative charge. Terminate. Here you see, use terminate means they do not form a closed loop. They do not form closed loop like a magnet. Okay, magnetic field forms a closed loop, but here they do not form closed loop because they have indicated terminate means end. But in a magnetic field, no end. Bar magnet. I'll explain that in a magnetism and matter. Okay. Now, third one, if you see, electric field lines are always perpendicular to the surface. Yes, if we consider this is a surface. So electric field lines looks like this, okay? Electric field lines looks like this, 90 degree, perpendicular. This is electric field lines. Got it? Now, electric field lines do not pass through the conductor. Why? Because electric field inside, that is the zero. Okay. Now, electric field lines do not intersect. Why? You can see the diagram, okay? You can see the diagram. They do not intersect. Intersect means meet each other, or else you can say cross each other. Two electric field lines do not cross each other because that is impossible. If two lines intersect, what does it mean? That particular point, that electric field has a two direction. It is impossible because electric field is a uniform direction. Okay, direction is uniform. Got it? Okay. Now, they do not form any closed loop because they are terminating. Do not form closed loop. Do not form closed loop. I hope it is a very clear. Okay. Now, someone AI soul. Yes, because at the same point, two direction not possible. Very good, very good. Shweta Mishra, because they don't have a two tangents. Exactly. Okay. Now, next one. Next one. Can two electric field lines intersect? This is what we have discussed. Okay. This is what we have discussed. Intersect question mark. If not, why? No. If two electric field lines intersect, then at the point of intersection, there will be two different tangential direction, which is not possible. Hence, two electric field lines cannot intersect. So that means two different tangential direction. Okay. Intersect means two tangents. Means two different direction. It is not possible. Yes. Two direction will be there. Exactly. Helkins. Okay, don't mind if I pronounce wrong. Okay. Fine. Now, Akash Patak. Never. Very good. Because they are uniform. Very good. Akash perpendicular. So, all the ways we can see. That is right. Okay. Shweta Mishra. Yes. Okay. Right. Now, let's move on to the next question. What is electric field inside the charged spherical conductor? What is electric field? It is zero. Right? It is zero. It is zero. So, this is the right answer. Electric field lines inside a spherical conductor, it is a zero. Okay. Now, next one. Electric dipole. Electric dipole. Last second concept. Okay. Electric dipole. After electric dipole, we have a Gauss law. After that, the first chapter will be completed. Right? Now, an electric dipole is a set of two equal and opposite point charges separated by a small distance. So how? If I consider this is a 2D, okay, separation between 2 point charges, this is a negative charge, okay, if it is not visible, please let me know. It is a negative charge and this is a positive charge. And this setup, we are calling it as a electric dipole. This setup, we call it as a electric dipole. Electric dipole, okay. And mathematically, how do you express this one? It is the product and it is represented by P vector, okay, P vector. And here you can write it as a either charge, okay. Here I'll write either charge, any one of the charge, either charge into separation. So P, either charge means any one of the charge you can consider, a magnitude you have to consider because direction we are indicating, okay. Now, charge into separation, how much I have considered? 2D, right? And what is the unit? Here I'll be writing expression P that is equal to Q into 2D. And unit, what is the unit of charge? Coulomb. What is the unit of a distance? That is a meter, Coulomb meter, okay. Now quantity, it is a vector. It is a vector. Then what is the direction? If it is a vector, it is a negative charge to positive charge, okay. And what is the dimension? Here I'll write dimension, okay, dimension of this one. Charge, that means 80. And length, that is a L. That is a L. Dimension. A power 1, T power 1, L power 1. Got it? Very good, very good. Kanishka Sharma, ALT, correct. AI soul, negative to positive. Exactly. And unit is cm, that is a Coulomb meter, not a centimeter. Okay. Keep that in mind. Gugeta, alt, ALT, that is also fine. You can write that also. Okay. Very good. Manu, P is equal to Q into 2D. Wonderful, wonderful, guys. Okay. Now, let's move on to the next concept. Electric field due to any one of the derivation, pakka for board exam. Any one of the derivation. One is equatorial, another one is axial. Okay. Now let's try to understand. Electric field due to electric dipole on axial point, that is a point on the axis. For example, here if I consider, okay. So here I want to calculate what is the electric field. What is the electric field? So let me consider this is a point P. Okay. Point P, no, because you'll feel that is a dipole. I'll be considering point point X also I'm considering. Okay, let me consider X, point X, okay. Now, distance is 2D and dipole, it is negative charge and this is a positive charge. In the diagram, I should show what is the direction of this dipole, this one. So here I can represent this one as a P vector. Got it? Okay. Now, here derivation part. Are you guys ready? Are you guys ready? Derivation part, 2 derivations, 5 minutes. 2 derivation, 5 minutes. Okay. Very good, very good. 2 kp divided by r cube, that is right. Okay. Sir, where will we get the PDF of this lecture? After this session, you'll be getting through the link. Okay. under the same video, you'll be getting a link. If you click on that link, it will direct it to a PDF file. Okay, now, yes. So from the center of a dipole, okay, from the center of a dipole, here I'll be considering center of the dipole. Here I'll be considering center of the dipole. Here electric field, okay. Now, the length of this as R, okay, length of this is R, okay. Now, length from negative to this point, negative to this point, how much it is? It is R, and this is D, right? This is D, and this is also D, right? Now, so this becomes R plus D, okay, R plus D, and what about here? From here to here, R minus D, R minus D. Is it clear? First arrangement is clear? Okay, very good. Tulsidas, thank you very much, sir. Welcome, welcome. Okay, now, next one you see, this electric field due to positive charge as well as negative charge. Which one is greater? The electric field due to negative charge or electric field due to positive charge? Which one is greater? Please tell me fast, fast, fast. Fast, I'm waiting. Yes, come on, boys, girls. Yes, the result will be, 2 kp divided by r cube. That's what we are going to derive it. Okay, fast, fast, fast. Yes, which one will be greater? Electric field due to negative charge or electric field due to positive charge? Look at the distance. Which one is near? This is a positive charge. It is a near. Therefore, electric field due to positive charge is greater. So this one I can consider E positive, and electric field away from the point, right? Away from the point, and negative charge towards the point. Okay, so this is E negative. You can see length I have considered less. This one is maximum. Why? Because the magnitude is more, because E is inversely proportional to the separation, right? Remember? Very good. Hindustani in positive. Exactly. Shweta Mishra, that is not negative, because the negative charge you see from this point, it is too far. Okay. Now length is more. Okay. Now let's consider total net electric field. Net electric field at X, that is given by electric field due to positive charge minus electric due to negative charge. Sir, why negative? Why negative? Because you see the direction, positive direction, that is the electric field due to positive charge along plus x axis, and electric field due to negative charge, that is the negative axis. Therefore, it is a opposite in direction. In vectors, opposite direction, it is represented by negative sign. Getting my point? Okay, that's fine, Shweta Mishra, no problem. Okay, it is a learning process. Don't be sorry. Okay, now electric field, that is equal to E positive. E positive means what is the value? KQ divided by R square. But what is the length? It is R minus D whole square. And E negative, okay, E positive, let me write KQ divided by R minus D whole square. Negative KQ divided by, what is the distance from here to here? From here to here, that is R plus D. R plus D, right? So here you can just ignore this, because already we have written. Now simplification, nothing else, simplification. KQ, take it out. And simplification, this one, R plus D, cross multiply it. R plus D whole square minus R minus D whole square divided by R minus D whole square into R plus D whole square. Now A plus B whole square, what will be the answer? Simplify that. A plus B whole square. A plus B whole square, KQ, divide, KQ bracket off. A plus B form, okay. A square plus B square plus 2AB minus A square, B square, and this one 2AB, right? Now this one, A minus B and A plus B, that can be written as A square minus B square. But already squares are there. Can I write this one as R square minus D square? Okay, R square minus D square whole square, right? Yes or no? This is in terms of A minus B, A plus B. What is A minus B and A plus B? A square minus B square. Already there are powers. Therefore, R square minus D square power 2. Okay. Mans is saying, hello, welcome to the session. Okay. Now, let's simplify again. E is equal to KQ. Here you can see. Okay. Here you can see R square, D square get cancelled, and 2RD and 2RD, right? That can I write it as a 2 into 2RD. Okay, 2RD divided by this one can be written as r square minus d square whole square. Okay, now next slide. E, net electric field, that is equal to kq. What is the bracket? That is 2 into 2rd divided by r square minus d square whole square. Okay, so simplification, further simplification, that E is equal to kq. Okay, and what if, okay, what if this one rearranging, okay, rearranging k q, okay, this one q into 2d. I'm grouping these terms, okay, 2d. Okay, remaining part, that is 2 into r divided by r square minus d square power 2. Okay, now here let's consider distance. Okay, distance for r is much greater than 2d, the separation between dipole, right? Therefore here I can write it as a k. What is the value of this one? Dipole, right? What is the value of dipole? Here I have written, yes, q into 2d. The same thing I have written, q into 2d, k p 2r divided by, if it is a greater than 1 means you can consider d, okay, nearly equal to 0. Okay, nearly equal to 0. That means it is a very small. You can ignore it. Okay, you can ignore it. So you can ignore it. So here a power 2. Okay, so 2 kpr divided by r power 4. Here you can see r and r, 1 r get cancelled, 2 kp divided by r power 3. So finally electric field 2 kp divided by r cube. And what is direction of electric field and dipole moment? Both are parallel, right? Yes. Okay, now let's move on to the next concept, that is equatorial line. Fast. Will you do this? The same procedure. Will you do this? Please let me know. If you can do this, we'll move on to the next question. Okay. Yes. Are you able to do this equatorial line? If you say yes, we can move on to the next concept. Okay. Yes, Manu said yes, Ajay, yes. So what is the final expression? I'm writing final expression so that you can do it. Okay. Perpendicular, that is equal to minus kp divided by r cube. Okay. So a perpendicular, nothing but equatorial, that is kp divided by r cube, r unit vector. Okay. So here you can write this equation. And what is the direction between E, perpendicular, okay, opposite, anti-parallel to P. So how? Direction wise if you see, the direction of negative charge, this one, due to positive, this one, and net electric field will be this direction. Okay, this is net electric field. Okay, so now you see direction of this is a negative. Okay, so this is a negative charge and this is a positive charge. Okay, this is a positive charge, and here direction of a dipole from negative charge to positive charge, this is a dipole and this is electric field. How they are electric field, and here a dipole opposite. So this is electric field and this is dipole opposite, therefore negative sign. Got it? Okay. R cap, it is a unit vector that shows the direction. Okay, fake or not. Okay, that is indicates the direction of electric field. Okay, now let's move on to the next concept, that is electric field due to electric dipole. So important note, electric field is parallel to the dipole moment in case of an axial point. Okay, what is the point? Axial point. Next one, so electric field is anti-parallel to the dipole moment in case of equatorial line. Okay, equatorial plane. Okay, relation if you see, okay, E parallel or else E axial, it is given by 2 kp divided by r cube, and E perpendicular, that is the equatorial line, that is minus kp divided by r cube. Okay, so compare the both the terms. Okay, here k, p and p, r and r cube and r cube, So what is the extra? That is the 2. If we take the ratio of E axial divided by E equatorial, you will be having minus 2 divided by 1. Got it? Yes? Okay, very good. Now let's move to the next concept. Dipole in uniform external field. Dipole in a uniform external field. Okay, what does it mean? So here a negative Q and here positive Q. Okay, and the length again here 2L I'll consider. Okay, 2L. 2L I'm considering. So this is the dipole. And what is the direction of a dipole? Direction of a dipole, that is a negative to positive. It is in an electric field, uniform electric field. Okay. Now, let's see. It experiences a torque but no force. Exactly right. Let's check out how. So, on a positive charge, what is the direction of a force? On a positive charge, what is the direction of a force? Along the direction of electric field. And that F, it is given by QE. If we consider a direction, that is along a plus I cap. Okay. Now, along a negative, on the negative charge, if we consider negative charge, this is along negative x-axis, right? F net, that is equal to same QE only. What is the direction? Minus I. So net force, if we want to calculate net force on a charge, that is given by, this is due to negative charge and this is due to positive charge, and the positive charge plus negative charge. If you substitute, what is the value of a positive? That is a QE I cap plus QE minus I cap, and here you can see QEI minus QEI. So finally it is a 0. F net is a 0. Always it is a 0. Very good, very good. Almost everybody is answering. I'm very happy. Okay, what you guys are doing, I'm very happy because you are spending quality of a time with me, and I am respecting your quality of a time. How much it is possible, that much I'm giving clear content for everyone who is attending my classes. Okay, F will be 0. Always 0. Okay, always 0. Always 0. Then what about torque? What do you mean by torque? If anybody from IC SE background, okay, not SSLC or the state board or CBSE students, class 10 students. If you have studied ICSE, okay, 10th class, machines, okay, first concept, force concept will be there, equilibrium concept, dynamic equilibrium, static equilibrium, everything will be there, where you have learned this torque. Torque is nothing but force into perpendicular displacement. Okay, force into displacement. What type of a displacement? That is a perpendicular displacement. Torque, it is given by tau, that is equal to, okay, force into perpendicular displacement. D perpendicular displacement. Okay, now again, this is a displacement. This is a dipole, that is negative charge, and this is a positive charge, and length 2L. And direction of a dipole, that is a negative to positive. Okay, now what will happen? Here electric field is there. Okay, electric field, that is a E. Electric field, that is a E. Okay, now, so perpendicular distance means first we have to identify force. Force I have identified, this is a force and this is also force. And with respect to electric field, what is the angle? That is the theta. Theta, right? And perpendicular distance to the force. Here force is there, perpendicular distance. Here force is there, perpendicular distance. Therefore, try to understand this concept, okay? Perpendicular distance. Any force you can consider, okay? Either force into perpendicular distance. Here I want this distance, okay? Here I want this distance or this distance, okay? This is a perpendicular distance. I want perpendicular distance. Which trigonometric function I have to use, okay? Which trigonometric function I have to use? See, I need to have this value. I have a theta. Therefore, which trigonometric function I can use? That is a sine. Sine theta, okay? Sine theta. Sine theta is given by perpendicular by hypotenuse. Perpendicular, that is D perpendicular, and hypotenuse, that is a 2L. And cross multiplying, you will be getting D perpendicular, that is equal to 2 times of L sine theta. Okay, substitute here. Okay, substitute here. So torque, that is equal to, what is F? That is a Q. Already we know that F is equal to QE. F is equal to QE plus I. And here F, due to negative charge, that is a QE and a negative I, right? negative I, and this is a positive I. Either force, any force you can consider into, okay? And what is the perpendicular distance? That is a 2L sine theta, right? So here you can see I'll be grouping 2L into E sine theta, okay? And here you can see Q into 2 times of a length, okay? Or else you can consider it as a distance D also, okay? So 2L, what does it mean? It is a momentum, sorry, dipole moment, okay? Sine theta. So this tau, that is a PE sine theta, this is the torque on a dipole. This is the torque on dipole. Got it? Okay, got it? This is a scalar form, okay? Vector form if you want to write, okay? Vector form. That is P cross E. P cross E. This is a vector form, okay? Got it? Fine. Now, answer these questions, okay? Answer these questions. Expression, it is done, okay? Expression, it is done. And unit. What is the unit? It is a Newton meter. Newton meter. And quantity, it is a vector quantity. It is a vector quantity. Vector. Okay, got it? I hope it is clear. Yes, yes. Okay. Now, next topic, that is a special case, maximum torque and minimum torque. So when we see the formula, okay, when we see the formula, torque, that is equal to PE sine theta. Sine theta, okay. So if electric field and dipole, okay, electric field and dipole, if I consider electric field and a dipole, this is a dipole. Let's consider this is the dipole, okay. This is a negative Q and this is a positive Q. And this is a dipole and electric field. What is the angle? What is the angle? 90 degree, okay. So theta, if it is a 90 degree or else perpendicular, okay, perpendicular. What does it mean? P perpendicular to E. Then PE sine 90 degree, sine 90 degree. Tau is equal to P. What is the value of a sine 90? That is the PE. Sine 90, it is a 1. Therefore, a torque is a PE. That is the maximum case. That is a maximum case. Okay, that is the maximum torque will be produced. And the torque is minimum. What if I consider a dipole along the direction of electric field? What if I consider dipole moment along the direction of electric field? So here I can consider P dipole moment is parallel to the electric field. That means theta is 0, parallel or anti-parallel. Theta are 180 degree, okay? Theta are 180 degree. Anti-parallel. So what will be the value? Tau is equal to sine 0 or 180, that is gives us 0 itself. Therefore, torque will be 0. Torque will be 0. Yes, very good, okay. 0 or 180 degree. 0 or 180 degree. Parallel or anti-parallel, okay. In a uniform electric field, net force is 0. Torque is may or may not be 0. Stable equilibrium, it is a 0. Unstable equilibrium, it is a not 0, right? So this is stable as well as unstable equilibrium concept. That is for commutative level, not for the board level. Ignore it, okay? Now, next one, what if I consider non-uniform electric field? Both force as well as a torque, it is not equal to 0, okay? So what happens? There will be some values, okay? Got it? Yes, Aryan, what is your question? Please tell me. What is your question? Yes. I was explaining the content. I could not notice your comments, okay? Please mention your doubt, okay? I'll be answering your question, okay? Now, let's move on to the next concept, that is work done in a rotation of a dipole in uniform electric field. Rotation. So I'm telling you, this first chapter is very big, okay? Very big compared to second, third, fourth. It is very big, okay? So after completing this chapter, next chapters will be very easy because this is the basic or foundation for the next chapters. Got it? Yes. What is the maximum torque? Means rotation. Torque nothing but a rotation. So how fast, how this rotation will be maximum? For example, this is the uniform field, okay? This is the uniform field. If I hold a dipole in the same direction, do you think any rotation will happen? No. If I hold like this, electric field is in this direction, what happens due to the force acting on a dipole, what will happen? It is bent, nothing but turn. Getting your point? If it is a maximum point, it can bend more or turn more, right? So if it is a less, bending or turning will be less. That is the maximum torque and minimum torque. Okay, very good. Okay, now, so initial position, okay, dipole was initial position at a theta 1, okay, initial position. So what I have done is, dipole was like this, okay, uniform field. This is the uniform field. I am applying some force or else work done. I am doing a work done in this dipole to rotate like this, okay, rotate like this. And what is the work I have done on this dipole to rotate it? That is the concept. So after work done, it is rotated by theta 2. Got it? This is dipole, okay? This is dipole. And this is electric field. What you have to do is, so as this dipole is rotating, theta is changing. Also, electric field is uniform. As the theta changes, what happens to the work done? Will be constant or variable. As theta variable, W is also variable. Nothing but work done is also variable. So here, as theta vary, okay, as theta vary, W, that is the work done also vary. So therefore, what I will do is, a small work done I'll consider. Small work done, that is given by, okay, work done for formula, what is the formula? Fs cos theta, right? Do you remember? Fs cos theta. Generally, we write Fs, right? Fs. So in the same way, here in place of F, here I am writing torque. Torque is a constant. And in place of S, here a displacement, okay, linear displacement. Here angular displacement. It is a d theta because that is also changing. Now, dw that is equal to torque. What is the value? Pe sine theta and d theta. So now what you have to do, total work done if you want, what is the limits? Theta 1 to theta 2 and dw. Apply the limits, integrate it, okay? What is the value? Pe is, it is a constant, Pe sine theta into d theta. So finally, you will be having Pe outside. What is the integration of a sine? It is a minus cos theta. Limits theta 1 to theta 2. So finally, minus Pe, I'll take it out, okay? Minus Pe, I'll take it out. What is the value? That is cos theta 2 minus cos theta 1. Cos theta 2 minus cos theta 1, right? So what if I consider this dipole is rotated perpendicular to the electric field? Theta 2 is a perpendicular to the electric field. What is the value of this theta 2? Theta 2, if it is a 90 degree, okay? If it is a 90 degree, what is the value then? W is equal to minus Pe, bracket of this, okay, 0, minus cos theta. Theta 1, it is a theta, okay? Then, so Pe cos theta. Pe cos theta. This is the derivation of work done. Then potential energy. So potential energy it is given by, okay, potential energy. So generally work done it is given by minus of initial potential energy, final potential energy minus initial potential energy. Okay, so here I want potential energy, final minus initial, negative term, negative sign I'll transfer to the left hand side. It will be negative work done, right? So finally, so negative work done, that is UF minus UI, that is equals to minus W. So this one, change in potential energy, I'll be writing like this, okay, minus Pe cos theta. Or else, this change in potential energy, I'll be writing potential energy that is equal to minus Pe cos theta. Work done, Pe cos theta. Torque, Pe sin theta. Don't get confused between these three formulas. Okay. Radius of the Gaussian surface enclosed charge is aft. How does electric flux through the Gaussian surface? Next concept that only. Okay. It does not depend on a Gaussian surface. Got it? Okay. Very good. Very good. Let's move on to the next concept, that is a flux concept. So we are in the last part of our first chapter. Now, it is measured of amount of electric field lines passing perpendicular to the surface. Okay. So these are the electric field lines. Okay. So let me consider this is electric field lines and area. This is area. okay, area vector. Now here you can see it is a measure of amount of electric field lines passing perpendicular to the surface. Perpendicular. What if there is an angle? What if there is an angle? So flux can be written as, okay, flux can be written as, electric flux can be written as EA, okay, EA cos theta. Okay, so I hope you know that dot product of two vectors and cross product of two vectors. So dot product, it will be AB cos theta and cross product AB sin theta. Don't confuse with these two terms, okay? Right? So phi, that is equal to EA cos theta. And cos theta, it is just a angle between E and A. And here, unit of E, that is electric field, that is a Newton per Coulomb. And area, that is a meter square. Right? What is the SI unit then? SI unit expression here I am writing again. Okay, here expression is flux is given by EA cos theta, right? EA cos theta. Now, here quantity unit is for electric field, it is a Newton per Coulomb, and area, it is a meter square, and here nothing. For cos theta, it is nothing. Therefore, I can write it as a Newton meter square per Coulomb. Okay, this is the unit. Got it? Now, here quantity, it is a scalar quantity, no direction. Scalar, no direction. It is just a scalar quantity. Okay, maximum flux, maximum. See, maximum flux when E and A are parallel to each other. E and A is parallel to each other, right? Parallel to each other. So here flux is flux maximum. When it will be maximum? When theta is 0 degree. Then flux will be maximum, that is EA. If you substitute parallel, okay, E and A are parallel to each other. And minimum when theta is 90 degree and flux will be 0 when E perpendicular to A. Got it? And here a negative flux and a positive flux. Here not only a 0, it can be considered as a 180 degree also. Plus or minus E. Plus EA and minus EA indicates, here you see, plus indicates it is the outward flux, negative indicates it is the incoming flux. Okay? Yes? Got it? Right. Next one. The electric flux through closed surface is 0. What do you mean by that? Means electric flux entering and leaving are equal. Entering as well as leaving equal. Got it? Okay. So that is the meaning of this electric flux closed loop. It is a 0. That is the meaning of this particular question. Next one. In which orientation the dipole placed in a uniform electric field is stable and unstable? This is for when dipole parallel to the electric field, that is a 0 degree. Here you can say theta is equal to 0 degree. Nothing but P is parallel to the electric field. And this one, P is anti-parallel, okay? Anti-parallel to electric field, okay? So next one, state and prove Gauss law in electrostatic. Last concept, okay? It will take 10 minutes, okay? It will take 10 minutes. Now, what is the statement? Gauss law states that the total electric flux through any closed surface in free space is equal to 1 divided by epsilon times of a charges enclosed by that surface. And here, this flux does not depend on shape of a Gaussian surface. Okay, it does not depend on Gaussian surface shape. Got it? Right? Now, this is the Gaussian surface and here I have considered positive charge. Okay, here consider positive charge. What will be the electric flux? Outward, right? Outward. And one electric field I am considering. Now, at this point, area it is always perpendicular to the surface. Area it is always perpendicular to the surface. Here I can write A and here it is a E. And what is the direction of E and A? Parallel, therefore theta is equal to 0. Right? Theta is equal to 0. Now, here you see, prove phi is equal to integral of E dot dA is equal to Qi divided by epsilon naught. Right? Right? So, we have to prove this, okay? How to prove? Let's see. See, Gaussian surface. Gaussian surface. Here I have a positive charge Q and electric field from positive charge, it is away from it. Okay. So here you can see it is a perpendicular to the surface, right? And area vector perpendicular to the surface. And here A as well as E both are in the same direction, therefore theta is equal to 0 degree. Okay. Now, so here, first of all, if I consider integration d dot ds, okay, ds, this can be written as in a scalar form, that is a ds, that is equal to cos theta, right? This cos theta, it is a 0. Cos 0, it is a 1. Therefore, integral E dot ds, right? ds nothing but dA also you can write, okay? Let me write a ds is nothing but dA, area of the surface, okay? Area of the surface. Now, so this electric field, okay? This electric field reduced to, electric field already we know that, right? What is the value? KQ divided by, if I consider radius of this surface, okay, radius of the surface as r, okay, radius of the surface is r square into dA. So finally, this is KQ, okay, KQ divided by r square. Radius of the sphere is also same, constant, therefore I'll take it outside. Integral of dA. That means what is the total area of the loop or else the surface? KQ divided by r square into dA. What is that dA? That is area of the sphere. Area of the sphere. That is equal to KQ divided by r square into 4 pi r square. Right? 4 pi r square. So this is and K can be written as 1 divided by 4 pi epsilon naught Q divided by r square into 4 pi r square. Here you can see r square, 4 pi get cancelled. So finally you will be having Q divided by epsilon naught. So phi, that is equal to integral E dot ds, that is equal to Q divided by epsilon naught. Is it clear? Is it clear? Right? Yes. Okay. Now, tell me, are you able to do this? Okay, charged wire. Are you able to do this? If yes, we can move on to the next topic, or else we can start solving this question. Yes, are you able to do this? Charged wire? Yes, Ajay Krishna, yes. Next. What about others? Come on, boys. Please tell me. Are you able to do this? Okay. Yes, solve. Okay, simple. See, this is charged wire, okay? This is charged wire and this is lambda. Okay, this is a positive. This is, what does it mean? This is linear charge density. Linear charge density. Linear charge density. And here I have considered dotted line. What does it indicate? It is a Gaussian surface, okay? Gaussian surface. What is the surface here? Cylinder, okay? Here, cylinder. Therefore, here, what is our question? Dirac expression for electric field. So, integration, okay? Phi, that is equal to integration EdA, that is equal to, okay, Q divided by epsilon naught. So, here Q, by linear charge density, what does it indicate? Per unit length. Okay, let me consider this is the length of this wire. Okay, this is the length of the wire, and here this one can be written as Q is equal to lambda L, right? So here I'll be reducing that equation to lambda L divided by epsilon, and integration you see EdA cos theta. Now flux, let's consider a flux through this surface, flux through this surface, and flux through this surface, okay? So you see, electric field, it is always away from the point, right? It is always away from the point. If I consider positive x-axis, okay? Electric field is along the direction of positive axis. And here you see, this one and this one, there is no electric flux, okay? If I consider this is phi 1, and this is phi 2, and this is phi 3, here phi 1 and phi 3 is equal to 0. Why? It is a perpendicular. Flux is given by EA cos theta. that theta value, it is a 90 degree, right, with respect to electric field. If it is a 90 degree, cos 90 it is a 0. Therefore, flux through that, it is completely 0. So in this particular case, the flux through this second surface only, it is a valid, right? So if I consider this one, okay, so what is the direction of electric field and area vector? Area vector here you can consider that is A and this is E. So what is the direction? Theta is equal to, again it is a 0 degree, right? A 0 degree. So here you can write integration E dA lambda L divided by epsilon naught. And E is a constant and integration of a dA. Integration of a dA lambda divided by epsilon naught. And here you can see E value. E as it is, what is the area of this shape? What is the shape of cylinder? Area of the cylinder, that is a 2 pi r L, right? Substitute the value 2 pi r L, that is equal to lambda L divided by epsilon naught. Here you can see this L get cancelled. Remaining values, that is E is equal to lambda divided by 2 pi epsilon naught. Okay, this is the value. This is the value. In other form also you can write, okay, no problem. In other form also you can write. So multiply and divide by 2. If you do it, okay, multiply and divide by 2, if you make it 2 pi epsilon naught, okay, 2 into 2, 4. So 2 lambda divided by 4 pi epsilon naught into this R also, right? R comes into the picture. So here R. So you can see this term, okay, 1 divided by 4 pi, that is a K. 2K lambda divided by R. This is also correct. So finally, electric field due to this straight wire, that is equal to lambda divided by 2 pi epsilon naught R, or E is equal to 2K lambda divided by R. Both are correct, okay? Both are correct. Got it? Now, let's move on to the next question. Yes, at least this one. Are you able to do this? Yes? Yes, I'm doing it very fast, okay? Kanishka Sharma. Yes, 2K lambda divided by. Yes. Okay. Are you able to do this? Ajay Krishna saying yes. And what about others? Shweta Misra, 2 pi. Yes, yes. Okay. Got it, got it. Okay. Let's move on to the next concept. A sheet, okay. So here it is let's consider this one has a homework, okay. Homework. Try to solve it. Practice. And here you see. So here sheet is there, okay. So from the both side, there is an electric field. This is a conducting sheet, okay. Due to this sheet, so electric field due to positive charges away. Due to positive charges away. And area, this is the Gaussian surface, okay. Area is also on the same direction. Here also electric field and area, same direction, okay. So first let me consider the first one, okay. Integral dA cos theta, okay. So that is equal to Q divided by epsilon naught, okay. Q divided by epsilon naught. Now, here as surface charge density, okay. This is the surface charge density. Surface charge density, it is given by Q divided by area, right? Charge per unit area. Charge per unit area. Very good, very good. I got answer. Kanishka Sharma. Got it, okay. Two. First one. See, what is the angle in this particular case? It is a 0 degree. This side and that side. So here you can write a dA, right? dA plus integral dA, that is equal to Q divided by epsilon naught. And here you can write 2 times of, okay, dA, that is equal to Q divided by epsilon naught. So here E is constant. I am taking it out. dA divided by Q, sorry, is equal to Q divided by epsilon naught. And what about this area if I consider, okay? 2 times of E, Q divided by epsilon naught, okay? So here what I can do is Q divided by 2 epsilon naught. This is the one form, okay? This is the one form in terms of a charge. In terms of a charge density, if I write, okay, in terms of a charge density, it will be, okay, it will be, this is A, right? This is A. And here divided by A. Now, so here, in terms of a charge density, Q, how can you write this? Q is equal to sigma A. That is sigma A. Here you can replace it. Sigma A divided by 2 epsilon naught A. So A get cancelled. So finally, you will be having sigma divided by 2 epsilon naught. Sigma divided by 2 epsilon naught. Is it clear? Okay. Yes. Very good, very good. Thick sheet also. This is a thin sheet. Okay. Very good, very good. Now, let's move on to the next concept. Numerical part. Numerical part. First one, it is based on a torque. Okay. So, 2 or 3 numericals are there. Okay. Are you guys ready? Are you guys ready? Let's see. An electric dipole is placed an angle 30 degree with an electric field of intensity 2 into 10 power 5 Newton, Newton per Coulomb. It experiences a torque equal to 4 Newton meter. Calculate the magnitude of a charge on the dipole if the dipole length is a 2 centimeter. So what is the formula we can use? Torque. Torque that is equal to PE cos theta, sorry, sin theta, right? PE sin theta. So just substitute the values. Torque it is a 4 and dipole length they have given magnitude of a charge. Okay. So here P I can write it as a Q. Okay, Q into length. Dipole length. Okay. And dipole length L. Next one, you'll be having question, sir. Previously you have used 2D. Yes, of course you can use 2D also. What is the E value? 2 into 10 power 5. Can you comment your answer? That is, if I start a poll, 1 second. I'm not able to see poll. Here it is. Yes, 45 seconds. Let's see who's going to answer this question now. And what about the sine 30? Sine 30 it is the 1 by 2. Okay, 4 into Q into 2D. In place of a 2D value, it is a 2 into 10 power minus 2 centimeter. It is there, therefore convert that into meter. So 10 power 2 into 10 power 5 into sine 30, it is a 1 by 2. Okay. Now, here you see 2 and 2 get cancelled. 2 ones are, 2 twos are, and remaining that a Q is equal to 2 divided by here 10 power 2, 10 power plus 5. How much it is? 10 power plus 3. And shift that into numerator. Okay. Shift that into numerator. 10 power minus 3 coulomb. This can be written as 10 millicoulomb. 10 millicoulomb. Is it correct? 2 millicoulomb, not 10. It is a 2 millicoulomb. Okay, sorry. 2 millicoulomb. So right answer, that is option C. Okay, let's see whoever answered this question. It is stopped. Okay. Show the result. That is which option? Option C. Try to calculate this one. Try to calculate. Yes, so nobody used this pole. Try to use that pole also. Okay. Now, here you see a spherical conductor of radius of 10 centimeter has a charge of a 3.2 10 in 10 power 7 coulomb minus 7 coulomb distributed uniformly. What is the magnitude of electric field at a point? At what point they are asking? 15 centimeter. Therefore, electric field it is given by KQ divided by R square, right? So use the formula. K it is a 9 into 10 power 9 into Q value. How much it is? 3.2 into 10 power minus 7 divided by R square. That is a 15 centimeter square 2 times. 15 centimeter square 2 times. Therefore, how much it is? 9 into 10 power 9. Okay, 10 power plus 9. Okay, so plus 9 minus 7, that is a plus 2 into 3.2 divided by 15 into 15, 10 power minus 4. Okay, 10 power minus 4. So here you can see simplification, easy simplification. So 3, 32, okay, 3 and 3, 5 and 3, 3, 5. And here you can see 32, okay, 32 into, or else 320 I'll make, okay, 320 because 10 power 2 is there, okay, and 5 into 5, that is a 25 into 10 power minus 4. So if you see that, around you will be getting 1.28 into 10 power 5 Newton per Coulomb, okay, 10 power 5 Newton per Coulomb. That is option E. Got it? Okay. Now, let's move on to the next concept. Hollow insulated conducting sphere is given positive charge 10 microcoulomb. What will be the electric field at the center of the sphere of radius is a 2 meter, okay. So here hollow means there is no charges, okay. Charges will be on the surface. They're asking Insulated conducting sphere. Insulated conducting sphere given positive charge, hollow. Here you need to note down the point, okay? Here you need to note down the point. So sphere 10 microcoulomb, therefore there is no charge. Q is equal to 0 inside. Therefore, what will be the answer? That is a 0, option A. Got it? So try to solve this question, okay? Homework, try to solve this question. So answer will be this one. Try to solve this one, okay? Now, second chapter. We are in the second chapter. Almost we have started class at 11, right? And 30 minutes for explanation. What is the importance of this marathon, right? Everything, okay? Yes? So Ajay Krishna, sir, lunch break. Okay, take, how much time you need? Tell me, how much time do you need? How much time? Yes, fast, fast, fast. So only one chapter we could complete. So we should be very fast. 10 minutes, 10, 15 to 20 minutes. Okay. Okay. Okay, fine. Let's take 20 minutes break. Come back soon, okay? So, timer. Yes. So after this, we can continue. Okay, two chapters. Again, two chapters, small break, 10 minutes break. Again, we can continue. Okay. Okay. Have a lunch, have a food, and come back. Got it? Okay. Hello, 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 hello. Good afternoon. Good afternoon, my dear students. So I hope everybody had their food. Okay. I'm good. I'm good. Ragged Army. I'm good. Jai now. Good afternoon. Good afternoon. Ragged Army. Raged Army. Okay. I'm good. I'm good. Hi, Kanishka. Hello, Kriti. Good afternoon. So let's set for 2-chapter target. So within the same time, let's try to complete 2 more chapters. That is electric potential and capacitance, and second one electric current. So after 2 chapters, let's take one more short break. Okay. So after that, moving charges and magnetism, magnetism and matter, and the next one EMI. So next 3 chapter. After that, AC and electromagnetic waves. Like that, 3 chapters or 2 chapters will finish it off. Okay. So are you guys ready? Yes. Are you guys ready? So let's get started. So here you can see. So by miss, my mother tongue is coming out of my mouth. Okay. Because few of my students, they are commenting. Okay. So they are asking, how are you, sir? Okay. Don't mind. Right. Okay. So if you see trend analysis of 3 years, okay, trend analysis of 3 years, here we have, electrostatic potential and equipotential surface. So here you can see the, number of questions and number of marks. And the second one, dielectrics and capacitance. Here see the marks distribution. Please go through that, okay? Ragul M. Okay. So my mother tongue is Kannada. And here, chapter names you can see deleted or dropped topics from this particular chapter. Here you can see the first one, energy stored in a capacitor, deleted only derivation part. Okay. Deleted only derivation part, and exercise 2.1 to 2.36. Got it? Okay. So let's get started with the second chapter of a first concept, electric potential. What is this electric potential? The work done per unit charge to bring from infinity to a reference point is called electric potential. Electric potential difference, that is between 2 points. Okay, don't get confused. Got it? Okay. Yes, Kanishka Sharma, yes. Yes. So here it is defined as the amount of work done per external force to bring a unit charge from infinity to that point. Okay. What does it mean? See, it is the amount of work done, right? To bring, okay, amount of work done. So potential means, okay, so potential means amount of work done per unit charge to bring from infinity to a reference point, reference point. Okay. So this is, we call it as a electric potential. Got it? So by watching one short videos, Raj Pandey. Okay. So if you have not yet started, please go through the one short videos. That will be helpful for you. Okay. Yes. Manu sir, where in Karnataka? So Bangalore. Okay. Now, next one, second definition we have for conservative force. Okay. The negative work done by conservative force to bring unit charge from infinity to point in the presence of other charge. Okay. So here we have a 2 derivation based on external work done as well as conservative force. External force as well as conservative force, we have a derivation part. Okay. So we can do it. Okay. Okay. So now here also same definition. So this one, work done. Okay, electric potential is nothing but work done per unit charge only. Work done per unit charge only. It is a conservative work done, but it is a negative work done. Okay, same infinity to that point, reference point. You can call it as a reference point. Reference point. Okay. Then what is the unit of this electric potential? Okay. What is the unit of electric potential? What is the unit of work done? That is a joule. Okay, here I'll be writing. So that is a joule and this is a coulomb. So we can write it as a joule per coulomb, that we call it as a volt. So generally we represent as a volt as a V. Okay, quantity, that is a scalar quantity, not a vector quantity. Got it? First slide, it is clear. Yes, Jaino, that is the correct answer. Okay, now let's move on to the next slide. Electrostatic potential difference here between 2 points. It is not with respect to infinity. Why do we consider infinity point? Because at infinity the potential will be 0 because the distance too much, right? So electrostatic force will be 0 at infinity. We have seen separation is inversely proportional to the force, right? Force is inversely proportional to the separation. More the separation, less is the force. So hence force will be 0. Hence potential will be 0 at infinity point. Got it? So electric potential means the potential between 2 points, okay, reference points, that we call it as a electric potential difference. Same definition, but instead of infinity, just use 2 reference point. Okay, Shweta Mishra, good afternoon. Welcome to the session. Now, here with respect to potential difference, okay, so potential difference, that is delta V. We can write it as a V final minus V initial. Final potential minus initial potential, okay, that is equals to, work done per unit charge, okay, work done per unit charge only from one point to another point, point to point. I'll write point to point, okay, one point to another point. So point to 1 and point to, I'll write, okay. Example, A to B or B to C, C to D, like that, okay. So most important to do derivation. Sir, formula must important to do derivation. So if you follow this marathon, that will be very helpful for you, okay. Got it? Now, so next one, it is also same. So delta V, V final minus V initial, that is for conservative means minus work done, okay, conservative force. This is external force, okay. Work done by external force. This is external force, okay. Now, so here also 0.1, 0.1 to 0.2, 0.1 to 0.2. Here you can consider reference as A to B. Got it? Okay. So same formula, same units. No change. For potential, we consider reference point as infinity, but potential difference between 2 points. Got it? Okay. Now, let's move to the next concept. While defining the electrostatic potential due to point charge, the reference of a unit positive charge moving from infinity is considered. Why? What is the reason? Already I have explained. Why? Because electrostatic potential infinite, 0 at infinite, long distance. Okay. Now, next one, potential due to point charge. It is defined as the amount of work done by external force to bring what type of charge? Unit charge from infinity to a point, a point. So let me consider this is infinite. So this charge is brought to A, and from A, okay, from A point to point B. Let's consider this is point B and distance dx, okay, and separation between, now charge is, okay, to bring this charge A to P, okay, separation between P2 and Q, that is a R, okay. So infinite to this point. Why this point? Because this electric charge has a field, right? Once it enters the field, we need to apply external force to bring this charge to here, okay. Which point? Towards point P. Got it? Okay. Now, here what you need to do is, so as it is moving towards a point P, this dx, nothing but, here if I consider this is R and this is x, and total from A to charge Q, Q1, that is a x. If I consider, see, work done, okay, small work done, I'll consider. Small work done, A to B, okay, work done in moving Q2 from A to B, okay, dW, that is equal to F dx, right? So why? By the formula F dx, okay, F is cos theta, general, okay, general formula, it is a F is cos theta. So here cos theta value, So here cos theta, it is the 180 degree, or else the distance is reducing. So see, as it is moving towards the Q1, the distance x, okay, distance is x, as it is moving towards the point P. What is happening to the distance x? It is reducing, therefore a negative dx. Okay, now dw, that is equal to f value, already we know that k, okay, q1, q2 divided by x square into dx minus dx. And here they have mentioned point charge, therefore q1, q2 value, it is a 1 coulomb. Therefore here I can consider q1 as a q, okay, q1 as a q, our reference. Now kq, because q2 becomes 1 divided by x square minus dx. Now, so this dx, take it outside, kq, okay. Next one, dx divided by x square. Till here it is clear? Till here it is clear? Very good, very good. Shweta Mishra and I don't know how to pronounce it. OMGANGVAR. Okay, now let's move on to. See, here we need total work done to move from A to point Q, or sorry, point P to, okay, till point P, we have to move it, okay. So now, if I want the total work done, I can consider what is the limits, okay. First, let me write a dw, limits x is equal to 0 to x is equal to r. X is equal to 0 to x is equal to r, okay, limits. Now, so simplification, nothing else, okay, simplification. So kq dx divided by x square. Now, further simplification, kq bracket of integration, if I take this x square into the numerator, what does it becomes? It is a x power minus 2, right? X power minus 2. Now, so here what will happen? X power minus 2 plus 1, minus 2 plus 1. Already negative sign is there, right? Negative sign is there. So 0 to r. Okay. Now simplification. So here minus 2 plus 1, it is a minus 1. Take it out. Already it is a negative sign is there. So therefore it is a kq divided by 1. Okay. Already 1. So this one I can write it as x power 1. So r 0. So finally, work done, that is equal to kq bracket of 1 divided by r minus 1 divided by 0. Therefore, this term becomes a infinite, that is a 0. Okay. So now finally work done, that is equal to kq divided by r. Okay. Now by the definition, potential work done per unit charge. Okay. What is the work done q2 value? That is 1 only, right? So here potential due to point charge, work done means kq divided by r. This is a derivation of a potential. Got it? Okay, kq divided by r. Very good. Kanishka Sharma. Saurabh Jaiswal, good afternoon. Good afternoon, good afternoon. Radhima, good afternoon. Sir, why physics we have English exam day after? Yes, I know. But according to the schedule, we have to move on, right? So anyhow, if you have any concern, means any doubt, you can attend this session, or else study or prepare for your next examination. Okay, fine. All the very best. Okay, now this is about a point charge. Now let's move on to the next one. Potential due to system of charge. So this is Q1. Okay, example I'm considering. Example, this is Q1 and this is Q2 and this is Q3 and this is Q4. At this point, okay, at this point, what is the potential? What is the potential at P? What is the potential at P? What we have to do is total potential at P, okay, that is equal to V1 plus V2 plus V3 plus V4. Simple, and so on. So, and we know that V is equal to KQ divided by R. So, by this, you can write VP KQ1 divided by R1, distance from here, R1, R2, R3 and R4, like that, okay. Now, plus KQ2 divided by R2 and KQ3 divided by R3 and plus so on. So, this is how you can calculate, okay, right. Next one. electric potential due to a system of charge. Okay, system of a charge. Okay, this is due to dipole. Okay, so here spelling system of charge, it is not a system of a charge, it is electric dipole. Electric dipole. Electric dipole. Fine. Now, so I want to calculate potential at this point. Okay, potential at that point. Okay, now what I have to do is first consider this is a negative and this is a positive. From point, okay, from point here to here, okay, here to here, and from here to here, point, okay. Let me consider this is a point P. Now, this one I'll consider it as R1, this one I'll consider it as R2, and this is R, position vectors. Fine. Distance from here to here between dipoles, that is a Q, 2D, okay. Now, potential, total potential at a point P, okay, point P, due to positive charge plus negative charge, okay. Potential due to positive charge as well as a negative charge. Potential due to positive charge, what is that? KQ divided by R1 plus KQ, okay, because it is equal and opposite charges, right? Equal charges. And this one, it is a R2. Now, simplification, KQ divided by R1 minus KQ divided by R2. So, take that KQ common outside. So, remaining it is the R1 minus 1 by R2. So, simplification, take the LCM. What will you get? R1 minus R2 divided by R1 into R2. Right? Got it? Now, here by, okay, this one, separation, if I consider that separation much greater than 2D, R1 nearly equal to R2. Okay, so this formula will be reduced to Vp, that is equal to KQ, okay, KQ, and here this is negative R1 R2, okay. So here this one becomes R1 minus R2 divided by R square, okay. So now, why it is not equal to 0? R1 minus R2, why it is not equal to 0? See, here we have, I'll explain, okay. Let me consider this. Now, KQ divided by R square, remaining R1 minus R2. What is this R1 minus R2? See, if I take, okay, if I take one circle, okay. Second. If I take one circle, it looks like this. Only circumference. Okay, arc I'm considering. Okay, arc I'm considering. So let's consider it as a straight line. Let's consider it as a straight line. Okay, let's consider it as a straight line. Fine. Now, so here what happens is, it looks like a triangle only. Okay, it looks like a triangle only. And this one angle, and here it becomes a base, right? It becomes a base and becomes hypotenuse, and this is perpendicular, right? By trigonometry. Okay, now here this is R1, okay, this is R1, and what about this one? This is R2. You see the separation, okay? R1, okay, this is R1, right? This is R1. This is R1 minus, this is R1 minus R2, okay? Now, we need this value, okay? So here, how to calculate this value? By using cos. Cos theta, it is nothing but base by hypotenuse. Base is R1 minus R2 divided by hypotenuse, that is a 2D, right? 2D. So here, I can consider it as a, so cos theta into 2D, that is equal to R1 minus R2. So substitute here, Vp KQ divided by R square into 2D cos theta. Okay, so here Q and 2D, grouping them, okay. Q into 2D into cos theta divided by R square. So Vp, that is equal to Kp cos theta divided by R square, okay. Now, this is about potential due to a dipole, okay. Now, next one. Shivam Mishra. Namaste, namaste. King of Future, hello, good afternoon. Ajay. Okay. Next. Okay. Okay. Yes. Next one. This is due to a dipole only. Electric potential due to system of charges. So electric due to system of charges, already we have done that. Again, it is a little print mistake. Okay. Yes. What is the potential we got due to dipole? That is Vp, that is equal to Kp cos theta divided by r square. Okay. So for axial line, okay, that point, what we have considered, that point, if it is on axial line, for example, here, if I consider the point is at this point, okay. So what is the theta value? It will be 0, right? So for axial line means the theta will be 0 degree. Now, Vp becomes Kp divided by r square, or else this side also it is possible, right? So for 180 degree, theta is equal to 180 degree, that Vp, that is equal to Kp divided by r square. It is a negative sign. Why? Cos 180. Yes, after this equipotential concept will start. Okay. Yes. Now, what about equatorial line? Means perpendicular at this point. Okay. What is the angle? It is the 90 degree. So cos 90, theta is equal to 90 degree, and this potential due to dipole will be 0. Got it? Okay, simple. So just, once if you practice, everything will be easy. Okay. Everything will be easy. Now let's move on to the next question. Electric potential due to thin charged spherical shell or solid conducting sphere. Okay, conducting sphere. So here no derivation, just we need to know. Okay, this one I'll explain after equipotential. Okay, after equipotential. Yes. Okay. Yes. Done with this? Now, what is the potential at a point which is at a distance of 9 centimeter from a charge, point charge 1 Newton, 1 nanocoulomb, okay? So potential that is equal to kq divided by r, right? So what is the value of k? That is a 9 into 10 power 9. What is the charge? That is a 1 into 10 power minus 9 coulomb divided by r, that is a 9 centimeter, that is a 10 power minus 2 in terms of a SI unit, okay? Okay. Yes, Kanishka Sharma, correct answer. And Shweta Mishra, yes, exactly. Okay. Sir, will we get a full marks if we write a same derivation in exam for yes, full marks. Okay. Now, but you have to mention what is K, what is P, what is theta. Okay. You have to mention it. Okay. Now, so what is the value? V is equal to 9 get cancelled. So plus 9 minus 9 get cancelled. And this one, 10, this 10 power minus 2, if I shift that into numerator, it becomes a plus 2. Therefore, 100 volt. 100 volt. In the same way, can you calculate this one? Can you calculate this one? What is the answer? What is the answer for this? How much of work is done in carrying a proton between 2 point charges of potential difference 10 volt? Yes, what is the answer? So sprinkle Ajay Krishna, Kanishka Sharma, exactly right. Okay, 10 power 2 or else 100. Okay, any one can write. Okay, so both are correct answer. Right. So here work done. What is the work done formula? I mean potential formula. It is the work done per unit charge. Okay, work done per unit charge. Here what we need to find out how much work. So work in terms of a work, that is a V into Q. So work done, that is equal to V is 10 and V is Q is how much it is? Proton. What is the value of a proton? What is the charge on proton? That is nothing but E. 1.6 into 10 power minus 19 Coulomb, okay? 1.6 into 10 power minus 19 Coulomb. So W is equal to 16 into 10 power 19 joule, okay? So this is the required solution. Got it? Now, let's move on to the next question. Find the potential at a point P due to charge of 4 into 10 power minus 9 Coulomb. Located it. Take it as a homework, okay? Take it as a homework. Or else please mention the answer. So same formula, KQ divided by R. K value, you know that 9 into 10 power 9, and the Q value they have given 4 into 10 power minus 9 divided by R. How much it is? 9 centimeter, therefore 9 into 10 power minus 2, and find the answer for this, okay? Find the answer for this. Let's move on to the next question. Equipotential surface. You see the word, okay? Equipotential. Equi means equal. Potential means, already we have learned what is potential means. It is the work done per unit charge in a moving from infinite to reference point, or else between 2 points. Okay. Now, here you see equi means equal, or same potential surface. The surface on which the potential remains the same at every point is called equipotential surface. Example, surface of a charged conductor. Surface of a charged conductor. Exactly. Sprinkle 400, correct. Manu 0. Once check, okay. Once check the answer, okay. Shivang single. See, any state board students, including CBSE students, this session will be very helpful, okay. This session will be very helpful. Got it? Now, exactly, Shweta, 400, exactly, 400, correct, Shweta Mishra? Yes. You'll be having instructions on the hall ticket, okay? VD H boss, okay? H boss. Kannada actor, H boss. You're a fan of H? Okay. See, whatever the instructions given behind means backside of the hall ticket, just go through it. We'll be getting all the information, okay? Got it? Now, see, surface of a charged conductor. See, point charge. How the equipotential surface looks like. For example, at this point, at this point, at this point, at this point, what is the potential? Same. Now, next consider at this point, at this point, at this point, same potential. At this point, at this point, at this point, at this point, same potential, because it is the same surface. So potential will be same. On this surface, potential will be same. Likewise, all the surfaces having same potential, or potential, that is nothing but electric potential difference. Here electric. Okay. Now, here for a linear charge, okay, if we consider at any point, okay, at any point, okay, this side or this side, potential will remain same. At the same time, for this also, potential remains same. Okay, this is for plane uniform electric field. Potential of uniform electric field. This is for linear charge. Okay, this is for linear charge and this is for uniform electric field. So here, simple thing is they'll ask diagrams, not a concept. Definition though easy, right? So here, practice the diagram for a point charge as well as a linear charge as well as uniform. Next one, electric dipole. Got it? Okay. Now, next one, properties of equipotential. First one, electric field is always normal to the equipotential surface. Why? What is the reason? So why it is normal? See, for example, if I consider a charge, okay, charge Q. If I consider a charge from this point to this point, if I move this charge, what is the potential on this particular surface? Potential, it is 0. Therefore, work done, it is given by Q. For example, this is point A and this is point B. Okay. So potential at A, potential at B minus potential at A. So what is the potential? It is a 0. Therefore, Q into 0. Therefore, work done equals to 0. By work done formula, Fs cos theta, right? If W is equal to 0 means 0 Fs cos theta. Therefore, 0 that is equal to cos theta. So when cos theta is equal to 0, when theta is 90 degree. So this one only we are calling it as a perpendicular or normal. Getting my point? Okay. Good afternoon. Good afternoon. A few students are joining freshly. Okay. Good afternoon. Welcome to the session. Now, two equipotential surfaces can never intersect. For example, if I consider, see, this is one surface and next one, this one. Okay. Say this is a 4 volt and this is a 6 volt. At this point, okay. At this point, if I consider 4 and 6, at a single point, two potential. Is it possible? It is not possible. See, it should have a 4 or else a 6, not a 2 values. So that is the reason we say two equipotential surface can never intersect. Got it? Next one. Because two normals can be at intersecting point, which gives a two direction of electric fields at the same point, which is impossible. Also in terms of a potential also you can see. Now work done in a moving any charge between any 2 points on the equipotential surface is 0. Already I have explained this. What is the equipotential? Because it is a work done is 0, right? That is the third point they are saying. Work done in a moving charge between any 2 points, equipotential surface is 0. This one only. Okay. Now the potential at any point in a equipotential surface is same and hence the potential difference is 0. Potential difference 0. Right? Next one. Next one. Give the condition for equipotential surface in terms of direction of the electric field. See, electric field is always perpendicular. Why? Electric field is always perpendicular. Okay? To the surface. Surface. Because work done, it is a 0. Got it? How much work is done? This is very important question, okay? How much work is done in a moving charge of a 20 microcoulomb on equipotential? Can you mention the value? Surface between 2 points is separated by 10 centimeter. What is the potential? What is the work done? How much work done in a moving a charge 20 microcoulomb on a equipotential surface between 2 points separated by 10 centimeter? Yes. Equipotential due to dipole. No. That is for electric field. By miss, I have told, okay? It is not with respect to dipole. It is with respect to electric field, okay? Yes, 0. Ajay Krishna, right. Samarth, right. Okay, very good, very good. Now, here you see, it is a 0. 0. Why? Work done that is equal to moving that charge 20 microcoulomb, that is VB minus VA. VA is equal to VB, right? Equipotential means same potential. When VA is equal to VB means what is the value of this? 0. So hence work done is 0, right? Is Earth an equipotential surface? Yes. Draw equipotential surface, okay? Draw equipotential surface, yes. This is for dipole, okay? Diagrams, please practice. This is for point charge, that is Q. And this is like charge, okay? And this is for uniform electric field. Please practice these diagrams, okay? Please practice these diagrams are very important. Got it? Okay. Now, let's move on to the next concept. Potential due to thin charged spherical shell. Okay. This also have to move little down. Relation, where it is relation? Okay, let me here only I'll consider relation between electric field and potential, okay? That is nothing but E is equal to minus dV divided by dr. Okay, dV divided by dr. 1 second, I'll show you that. Yes, this one only. Yes. See, work done by conservative force. Work done by conservative force. That is Fs, okay? Fs cos theta, original formula. With respect to equipotential, what is the work done? That is the work done moving a charge, okay? Moving a charge Vb minus Va. For example, Vb minus Va. this is A and this is B. Okay, now that is equals to F as it is. What is S? This difference, that is a dr, and a cos theta becomes a 0, that is a theta is 0 because electric field as well as a potential, okay? So it is opposite direction, so sign will come, we'll see, okay? Now, next one, this one can be written as dV, that is equal to, okay, that is equal to, so here negative sign comes into the picture, I'll tell you why, okay? Now, FDR, FDR. So here, conservative force, right? Conservative force, negative sign, okay? Negative work done. So here you can see F means, okay? Let's consider Q into dr, okay? Now, so Q get cancelled. Finally, you will be having E is equal to dV divided by dr with a negative sign. With a negative sign. What is this a negative sign indicates? The electric field is in degrees in potential. Okay, degrees in potential. Negative sign indicates degrees in potential. This direction is in degrees in potential, means higher potential to lower potential. Higher potential to lower potential. Getting my point? Okay, very good. Wonderful, wonderful. Okay, so a lot of students are commenting really awesome. Okay, so accurate answers they are giving. I appreciate their effort. Okay, now electric field moves high potential to low potential. So here electric field high potential to low potential, that is a negative sign. What is the meaning of this negative sign? Means it is electric field is moving high potential to low potential. Next one, electric field is inversely proportional to the spacing between equipotential surface, that is nothing but dr. Okay, dr. Next one, electric field is perpendicular to the equipotential surface. Already we know that. Okay, so next, so here constant. Okay, constant. Next, yes, one second. So that's sphere one. We'll do that. Okay, we'll do that. Yes. So here equipotential surface with respect to spherical shell. Okay, now, so spherical shell, there is nothing. Okay, only outside charges are there. Outside charges are there. Now, so for the first point, if we consider V, okay, general point, if I consider V is equal to KQ divided by R, right? KQ divided by R. So here if I consider, this is the radius. This is the radius R, capital letter R. And here I'll be considering 3 points. One outside the surface, external point. One on the surface, another one is inside surface. Okay. So you can see inside this spherical conductor, electric field will be 0, right? Electric field will be 0. When electric field is 0, by the previous condition, what is that? E is equal to minus dV divided by dr. So if it is 0, dV divided by dr, 0. That means V is constant. V is constant, right? Therefore, for inside, V is equal to KQ divided by R. For on the surface, V is equal to KQ divided by R. But outside one, okay, outside one, KQ divided by R. So this point, it is the R. Okay, and this is also R, that is equal to R. And it is R less than R, still you will be getting R only. So what is the potential inside spherical shell? Means it is the same as at a surface, okay, potential at the surface. Is it clear? Okay, now, next one. Potential energy due to two charges. Electrostatic potential energy of a system of a charges is defined as work done to move a charge from infinite to their present configuration to constitute the system of a charge. What does it mean? So freshly I draw the diagram, okay. See here I'll be considering one charge, okay. So here I'll be considering one charge. So at this particular point, okay, at this particular point, potential is V1. Okay. So this point, one second. This one, okay, Q, it is moved from infinity to a point A. A point A. Okay. So due to this, point P, okay, point B, there is a potential, I'll call it as a V1. V1. Now what I will do, second charge, okay, second charge Q2, and this is first charge. So here, this charge from infinity brought here, okay, due to this external potential, or else potential due to a Q1, what will happen is, so work done, due to this Q, there is an electric field, right? So in the electric field, this Q2 has to brought from infinity to this point B. So we have to work done, right? So that is Q2 in a field of electric field, that is a potential V1. So this one can be written as Q2 due to V1, that is a KQ1 divided by separation. If I consider R, you can consider it as a R. So finally, it is a KQ1 Q2 divided by R. So this is the potential energy. Why? Because it is a equal to change in potential energy, right? Infinity, it is anyhow it is 0. So that can be written as K Q1 Q2 divided by R. Are you guys understanding? Yes? It is complete revision session. Okay? Yes? Okay. Yes. Next one. Potential energy due to charge in the presence of external field. External field. For example, if I consider Q1, okay, Q1, and this Q1, due to this Q1, there is a potential. Means Q1 is there, and due to there is a potential at a point B. This is point A, and this is point B, and here potential is there. Q2 is bringing from infinite to this point. What will happen? First of all, work done on Q1. What happens? Q1 and V1. And work done on charge 2. So first, it has to bring in this particular field, right? This Q2 has to bring the field due to Q1. Therefore, there are two work done is happening. One against electric field. Another one is presence of a Q2, right? So here, Q1 V1 plus Q2 and V1, right? Q2 and V1. So finally, you can write W2 Q1 V1 plus Q2, and here K Q1 divided by R. So finally, you can write K1 V1 K Q1 Q2 divided by R. So this is the expression for external source. Now, next one, potential energy due to system of charges. What you have to do is total potential, that is equal to U1 plus U2 plus U3 and so on. So here I have just written W, that W is equals to potential energy itself, okay, by the definition. Okay, now electrostatic of a conductor. Properties. The first property of an electric conductor. The first one, inside conductor electrostatic field is 0. Already we have seen from first chapter. Second one, on the surface of a charged conductor, electrostatic field lines must be normal surface, okay, normal to the surface at every point, okay, every point, because work done is 0 on equipotential surface, okay. Next one, the interior of a conductor can have no excess charge in the static situation. That is also correct. And the fourth one, electrostatic potential is constant throughout the volume of a conductor, has the same value as inside on its surface. The last one. Okay, last one. Okay, last one, surface, spherical shell. Already we have derived the equations, right? So surface as well as inside, potential will remain same. That is a KQ divided by capital letter R, not the small letter r. Outside point, it is the small letter r. Got it? Okay. Now, next one. What is electrostatic shielding? Shielding. Electrostatic shielding means, if I consider a conductor, inside a conductor, closed conductor, what is the electric field inside it? It is a 0, right? It is a 0. Now, here you see, the field inside the cavity of a conductor is always 0. And it remains shielded from outside electric influences. Okay. So that means electric field inside this shield is 0, okay, that is electric field is 0, and this is shielded from outside electric influence, means this is a shielded, blue color one you can see, right? It is shielded from outside electric influences. This is known as electrostatic shielding. This property is used in a protecting sensitive instrument from outside electrical influence. Like when you are talking, okay, not right now, not now, okay. So maybe 5 or 6 years back, I don't know if it is possible right now. So when you are talking, okay, on the phone, if you bring any electrical instruments, okay, nearby your phone, it looks like, something disturbing, means a signal will be go off, right? Or else, while going up in a lift, when lift is closed, close the door, what happens inside? There will be no network. What is the reason? Because electric field inside that closed loop, cavity, that entire lift platform becomes a closed loop. It is a cavity, it becomes a cavity. Therefore, electric field inside that, it is a 0. Got it? So that we call it as a electric shielding. Okay, electrostatic shielding. Got it? Now, so next one, mention the uses of electrostatic shielding. Already we have no. That is designing TV cables. Next one, to protect the instrument device which are sensitive to the electric field. Got it? So these are the simple applications. Polar and dielectrics and polarization. So these terms you may have heard in a chemistry very well, right? Polar, okay, dielectrics, polar and non-polar dielectrics, right? So here dielectrics means it is a non-conducting substance, okay, non-conducting substance, and there are two types. One is polar dielectric, another one is non-polar. Polar means the two negative and positive charges, okay, they are separated, the centers are separated, hence they have, all right, okay, polar dielectric. So this is a positive and this is a negative. The center of these two atoms have a separate centers, okay. The center of these two atoms have separate center or location. But in non-polar dielectrics, what happens? This is a positive, means at the same negative, so centers are coincided, okay. And this one, if I apply electric field, okay, electric field, or else ulta, electric field, so here it looks like this, okay, positive and negative. But here if you apply electric field, there is no change, okay. So hence here negative and positive, hence these two have electric dipole, permanent electric dipole, okay. Polar dielectrics have a permanent dielectric, okay, electric dipoles. Next one, non-polar dielectrics, they do not have permanent dipole moments, okay, electric dipole moment. Got it? Now, so what are dielectrics? Give an example. Polar. The polar dielectrics are those in which the centers of a positive and negative charge are separated, even when there is no external field. Such molecule have a permanent or intrinsic dipole moment. Example of a polar molecules are HCl. Example you should remember, it will be helpful in chemistry. HCl as well as the molecule of water, H2O. Okay, now, next one, what are the non-polar dielectrics? The non-polar dielectrics are those in which the centers of a positive and negative charges coincided. These molecules do not have permanent or intrinsic dipole moment. They do not have a permanent dipole moment, okay. Example for non-polar dielectrics, that is oxygen and hydrogen, O2 and H2, okay. Now, next one, electric polarization. When a dielectric is placed in external electric field, the dielectrics develops a net dipole moment. The electric is now said to be polarized. The induced dipole moment is acquired per unit volume, is known as polarization. Okay. For the linear isotropic dielectrics, P, susceptibility, electric susceptibility, it is the product, okay. Dielectrics, that is a linear isotropic dielectrics. This P, dipole moment will be, it is the product of electric susceptibility and electric field. And I mean, it is the strength of electric field, okay. Now, the next topic, that is a second one, okay. Polarization deleted. Yes, Ajay Krishna, polarization is deleted. By miss, it is came into the slide, okay. It is an error from DTP, okay, no problem. We can ignore it, polarization, yes, okay. Now, next one, capacitance and capacitor. Next half, okay, next half of the second chapter. So, numericals and theory, kitne question aate hai? Already have given, PPT, the first slide of every chapter. So, marks distribution and deleted portions, okay, please go through it, okay. Now, the first one, capacitor and capacitance. What do you mean by capacitor? Capacitor is the device which stores the electric charges. And the property of a capacitor, that is a capacitance. Okay. Any material, if you provide a potential difference, okay, more number of charges will be accumulated or else stored. Okay. More the potential energy, means not potential energy, potential difference, more will be the charges will be flowing or else accumulated. Right? Got it? Now, here the capacitance of a conductor, it is the ability of a conductor to store a charge on it. Okay, charge on it, okay. Give me 1 minute, okay. I'll complete this slide and I'll watch your comments, okay. So if you have any doubts, you can ask me. Now, capacitance of a conductor is the quantity of a charge required to raise its potential by 1 volt. Okay, 1 volt. 1 unit means 1 volt. And expression, what is that expression? Capacitance, that is equal to Q divided by potential difference. Or else you can write a Q divided by V. Both are correct, okay. Unit, capacitance, unit of a charge, that is a coulomb. Unit of potential difference, that is a volt. Therefore, coulomb per volt, that is equals to farad. Okay, that is equal to farad, and that is given by F. And the symbol of a capacitance, okay, symbol of a capacitance, this one, okay, symbol of capacitance, this one. Like resistor, we have a particular symbol. Capacitance, we have a particular symbol. Okay, so this is definition of a capacitance of a conductor. Yes, motivation docs, sir, numericals nahi band hai, please help. I am doing it, okay. Wherever it is necessary, I am doing it, okay. You please go through the, previous, means already I have done first chapter. You please go through it, you will get to know whether I am doing the numericals or not. Okay, now. Define capacitance of a capacitor. Already I have defined. Okay, capacitance of capacitor is defined as the ratio of a magnitude of a charge present on the either conductor. Either conductor means, if I consider this is a capacitor, okay. If it is a positive, this is a negative, whatever, or else both the positive, okay. Now, and this is a mathematical formula. C is equal to Q divided by V. C means capacitance, Q means it is the charge on a capacitance, V is the potential difference applied. Okay, and SI unit of a capacitance, that is a C, already I have explained in the previous slide. Okay, I have explained in the previous slide. Now let's move on to the next concept, capacitor. So dependent factors on a capacitor, types of a capacitor. So hold on to this concept, okay, capacitors, dependent factors on a capacitance. After deriving the derivation, you'll get to know on what factors this capacitance of a capacitor depends, okay. Yes. Types of a capacitor. So here you can see parallel plate capacitor, spherical capacitor and cylindrical capacitor. For our syllabus, we have a parallel plate capacitor. We have a parallel plate capacitor, okay. So let's move on to the parallel plate capacitor. What do you mean by parallel plate capacitor? Capacitor with the two identical plates, parallel plates, separated by a small distance, and the space between them is filled by a dielectric medium. See, these are the parallel plates, okay. This is the one plate and this is the one plate. They arranged in a parallel manner, okay, parallel to each other. Now, here, electric field between these plates, okay. So already we have learned electric field due to thin sheet. Do you remember? Electric field due to thin sheet, that is equal to sigma divided by 2 epsilon naught. Do you remember? Due to positive, for example, if I consider this point, okay, at this point, what is the electric field? If I ask, what is say? From this point, due to positive charge, it will be moving downward. Due to negative charge, still it is a downward, right? Still it is a downward. So both are having the same direction. Therefore, I can use net electric field, that is given by sigma 2 epsilon naught plus sigma 2 epsilon naught, that is equal to sigma divided by epsilon naught. So electric field given by E is equal to sigma epsilon naught. Now, potential difference of a plates of a capacitor. E is equal to dV divided by dr. Now, what is the value we got by E? Sigma divided by epsilon naught, that is equal to minus dV divided by dr, right? dV divided by dr. But here I'll consider, okay, this one I'll consider distance between two parallel plate capacitor as a d. Got it? Now, so right now we need a potential difference. Therefore, cross multiply it. How much you'll get? After cross multiplying it, minus dV, that is equal to sigma divided by epsilon naught, okay, into dr. So now on integration, so what is the values you'll be getting? That is integration, okay? It is a minus integration V minus VB. For example, this is A and this is B, okay? VB minus VB dV, that is equal to integration from 0 to d, means from 0, what is the total length or else the total distance between two parallel plates? That is a d, and sigma divided by epsilon naught into dr. Or else in place of a dr, I can consider this as a x, okay? This as a x is equal to 0 to x is equal to d. This one I can use it as a x. This one as a x. Got it? Okay, now. So further simplification. See, after integration, what do you get? VB minus VA, that is equal to sigma divided by epsilon naught, and here distance d, right? A distance d. So finally, that VA, what is the value? VB minus VA and negative. Negative I take into inside the bracket, what will the values, okay? Minus and minus, minus and minus plus. Therefore, this one becomes VA minus VB, that is equal to, and here sigma d divided by epsilon naught. Sigma d divided by epsilon naught. Okay, now here this one potential difference, right? So capacitance, by the definition, we can say Q divided by V. Nothing but in place of a Q, what do we have? Q. Okay, let me consider Q. Divided by, in place of a potential difference, this is nothing but potential difference only, right? So sigma d divided by epsilon naught. Shift that into numerator. Q epsilon naught divided by sigma d. And this Q can be written as in terms of a areal charge density, that is a Q divided by area. So Q, if you want, okay, if you want the Q, you have to take sigma A. So sigma A epsilon naught divided by sigma D. Okay, sigma and sigma get cancelled, that is areal charge density, and capacitance, okay, capacitance, it is given by A epsilon naught D. Okay, A epsilon naught D, where A is the area of the plate, okay, area of the plate, and D is the distance or the separation between two plates, and epsilon naught is the medium in between the two parallel plate capacitors. Okay, Kanishka Sharma, which one? Please tell me. Yes, dielectrics lab of value 6. Okay, I'll tell you. Which one? Kanishka, which one? Sigma D, yes. Q. Already we have converted that electric field into areal charge density, right? Shweta Mishra, yes, correct. And after substituting sigma, you'll be getting A sigma, A epsilon naught. Okay, now. Parallel plate capacitor. Okay, you see, first here, if you want capacitance, first what you need? First charge you need. Next one, potential difference you need. Charge you have. Due to this surface charge density, you'll be getting to know. That is given by Q divided by V, where V is the potential difference. Potential difference, how do you calculate? By the relation electric field and potential difference, right? As the distance vary, electric field is also varying, right? So that is the reason we are using E is equal to minus dV divided by dr. dV divided by dr. Okay. So first of all, electric field between the parallel plates, first we have to calculate. Then by the electric field and potential difference relation we can use. Therefore, after using this electric field between the parallel plate capacitor and the relation between potential difference and electric field, using this relation we can calculate what is the potential difference. Now we have a charge density, that is the areal charge density, and a potential difference. We can find out the capacitance. How? By the definition, C is equal to Q divided by V. C is equal to Q divided by potential difference. How much we got it as? Sigma D divided by epsilon. Substitute, simplified. You got the answer. A epsilon naught. Yes, that's what I'm doing, right? Okay. Kush. Hi, Kush. Welcome. Okay, already I have repeated. I think you got it, okay? No. Capacitor and resistor. Yes, bridge you can make, okay? But purpose is different. Capacitor bridge you can make it like resistor only, okay? But purpose is different. Yes, okay? Now, next one. Yeah, see this. Factors affecting capacitor. The first one, area of the plate. Next one, separation between parallel plate capacitor. Next, medium between plates. What if I use in place of air? Initially, we have considered air medium, okay? What if I consider dielectric medium other than air? How this capacitance going to vary? Okay, let's see. Here I have used dielectric constant, that is a K. Okay, dielectric constant, that is a K. So here if I use this one, so K it is given by, okay, that is epsilon medium to the epsilon free space, nothing but permittivity of a medium to the permittivity of a free space. That is the definition of a dielectric constant. So here capacitance it is given by, okay, capacitance it is given by A epsilon naught divided by D, right? So this is original one. So new capacitance, what will happen if I use medium in between the plates? So this one further reduced, A divided by D. In place of a epsilon m, can I write it as a K epsilon naught, K epsilon naught. Therefore, here K A epsilon naught divided by D. What is the value? So here C dash K, what is the value of this? Already we have done this, okay? That is A sigma divided by D. This is the required solution. Got it? Okay? Simple? Yes. Very good, very good. Very good. Kanishka Sharma got the answer. And tech is changer. Okay, I got 98 percentile in this attempt. Good, congratulations. Okay, now, next one. What happens to the capacitance of a parallel plate capacitor when the separation between its plates is reduced to half? Simple. What is the formula? C is equal to A epsilon naught divided by D. So C inversely proportional to the D. What happens to the capacitance? Okay, D changes to D by 2. Okay, then C changes to C by 2. Simple. Inversely proportional. Okay, doubled means it should be numerator, right? It should go to the numerator. 2C. New capacitance divided by 2C. So if you substitute the values, okay, A epsilon naught, okay, D by 2. So A epsilon naught divided by D into 2, that is a C dash, okay. This is the formula. No. Thickness it is not required, okay. That is for competitive level, okay, not for the board level. Got it? Very good. Sprinkle, Kanishka Sharma, very good, very good. Now next, move on to the next question. The capacitance of a parallel plate capacitor, okay, in a air, okay, is 4 microfarad. When the medium is introduced between the plates, the capacitor becomes 12 microfarad. What is the value of a dielectric constant? So they are asking K value. What is the relation? New capacitor, that is a capacitor in medium, K capacitor in air medium. So capacitor in medium, how much it is? 12 microfarad, that is equal to K, and a capacitor in a air medium, that is a 4. So K is equal to 12 divided by 4, that is a 3. No unit for a dielectric constant, okay? Keep that in mind, okay? Got it? Okay. Now next, move on to the next question. when do we say that two capacitors are series? Now, derivation part, series and parallel combination. See, this is a series combination of a capacitor. If I consider only two, okay, let me consider only two. This is okay. So definition of a series combination. Two capacitors are said to be in series when they are connected end to end, one after one. Then that combination we call it as a series combination. And on applying potential difference across the combination, the charge on each plate of the capacitor is same. That means charge remains constant. That do not change. Got it? Now, derivation part. So here capacitor 1 and this is capacitor 2. And derive an expression for effective capacitance of a two capacitor means this capacitor reducing to effective capacitance, that is CS, series, okay? Now, so here I have a battery, okay? Here I have a battery. Now what happens? Current will flow. Potential difference across C1 and potential difference across V2. And here you need to understand what is the charge in a series combination. Charge will remain same, right? According to the series combination definition. And which is going to be changed? That is a potential difference. So potential difference, if I consider, okay, potential difference, okay. So potential difference, total potential difference V1 that is equal to V2. And V, by the definition of a charge, capacitance that is given by Q divided by V, that is a potential. And in terms of a potential difference, I can write a Q divided by C. Same way, here you have to do it. So in terms of a total potential difference, that is a V by the battery. It is divided into two forms, V1 and V2. That is across capacitor 1 and capacitor 2. What I'll do, here total charge Q divided by C, S. Because it is the series combination, right? Next one. In the same way, Q divided by C1. Why? Total charge will remain same. Charge will remain same, but potential difference vary. Now, Q divided by C2. And here you can consider Q taking out and remaining C1, 1 divided by C1 divided by 1 divided by C2. So here finally, Q divided by CS, Q divided by Q into 1 by C1 plus 1 by C2. Now, you can observe this Q get cancelled. Finally, okay, I'm writing it here, okay. Finally, 1 divided by CS. What is that? CS indicates it is the effective capacitance in a series combination. S means a series combination, okay. Series combination, that is equal to 1 divided by C1 plus 1 divided by C2. Now, or else you can write this one as a C1 into C2 divided by C1 plus C2. Both are correct, okay. This is the required solution, series combination. Now let's move on to the next question, next concept. When do we say that two capacitors are in parallel? See, these are the two capacitors, okay. Capacitors C1 and C2. Two capacitors said to be in parallel if they are connected across the same two terminals. See, A and B, okay. What are the terminals? Capacitor 1, one end connected to A, another end connected to B. Capacitor 2, one end connected to A and another connected to B. That means only 2 points. Okay, only 2 points they are connecting. Now, so that the potential difference across each capacitor is same. In this particular case, parallel combination, V is constant, but series charge is constant. Okay, now let's consider parallel combination. Here I have a Q, this is a C1, capacitor 1, this is C2, capacitor 2, okay. Effective capacitance of a two capacitor. So this is reduced to this form, okay. C1, okay, this is CP, I'll write as CP. Why? Effective capacitance in a parallel combination. Therefore, very good, very good. Okay, students, I'll tell you one thing. If I do not see the comment section and if I do not respond to your questions or query, please wait for some time, okay? Because I'll be busy with, explaining in the content. And if you feel bad, don't feel that, okay? Don't feel bad, okay? So we have to learn. Here we are to learning. We are here to learn something new, right? Let's learn. Got it? CP. Now, in a parallel combination, charges, okay, charges may or may not be same. Voltage across each capacitance remains same. So here charges are varying. Therefore, Q1 plus Q2, Q1 plus Q2. So by the definition, Q divided by V. So here in terms of a Q, Q that is equal to CV, right? So total potential, if I consider that is a V, potential difference V, and total capacitance is CP, right? CP, V, that is equal to C1 V, C2 V. Why I'm not writing V1 and V2? Because in a parallel combination, right? In a parallel combination, potential difference remains same. Therefore, Cp that is equal to, okay, Cv, Cp, Cv. Here V is constant, therefore C1 plus C2. And here V get cancelled, Cp that is equal to C1 plus C2. Directly you can add in a parallel combination. And remember, resistor as well as a capacitor, opposite in nature. Means, just remember series combination of a resistor R1 plus R2 plus so on. I know that it is deleted from the syllabus, okay? It is deleted from the syllabus, okay? Ignore it. But just, comparison. And a parallel, that is R1 into R2 divided by R1 plus R2. But in a capacitor in parallel, that is C1 into C2 divided by C1 plus C2. But in a series, C1 plus C2, ulta. Got it? Very good, very good. Okay. Now, next one. Energy stored in a capacitor. No derivation, it is deleted. Already I have showed you the deleted or dropped topics. Therefore, energy stored that is equal to half CV square. By the definition, we can rearrange it, okay? By the definition of a capacitance, you can rearrange it, okay? Rearrange it. Okay, now, energy density means energy. I told you, no, the capacitor is to store our charges. Capacitor, okay? In case of this capacitors, this electric fields, okay? Electric energy density, that is a charge density, electric energy density. So that is given by 1 by 2 epsilon naught E square. So energy stored in the form of electric field. Energy stored in the form of electric field. No derivation is required. Just a final expression you need to remember. That's all. Okay. Let's move on to the next concept. Mention uses of a capacitor. Used to store electrical energy, used to store charges. So this is what we have learned, right? This is what we have learned. And used as a filter that we are going to learn in a AC. Full wave rectifier, okay? AC chapter we are going to learn. Got it? Okay. Now, next one, used as a potential divider. Used in a radio circuit for tuning. Used in generation and detection of electromagnetic waves. This is also in electromagnetic waves we are going to learn. So that means we have two applications in 12th grade. Okay. And these two are, we have not, okay. This first one is also, we have used, no, electrical energy, right? Yes. Some numerical part, let's do it. A 900 picofarad, pico means 10 power minus 12, okay? Try to answer this question, okay? Picofarad is charged by 100 volt battery. How much electrostatic energy is stored by the capacitor? Just now we have solved question, right? I mean derivation, not derivation, just expression. CV square, right? Capacitor, how much it is? Here you can write, that is 1 by 2 into C, that is a 900. Pico means a 10 power minus 12, okay, minus 12. And V, that is 100 into 100, 2 times, right? So here you can see half of a 9, that is a 4.5. And here 20, here 20, here 20. Total 60. 10 power 6 into 10 power minus 12. So electrical energy, that will be 4.5 into 10 power minus 12 joule. Sorry, 6 joule, okay? This is a 6 joule. 6 joule. Okay? Now, let's move on. Okay, second question. Take it as homework, okay? Take it as a homework. What happens? Battery and connect to another 900 picofarad capacitor. What is the electrostatic energy stored by the capacitor? See, here a parallel combination. Parallel combination means what happens? Charges will be divided. When charges divides, what happens to the energy? That is also divides, right? So, do that. Next one. Three capacitor of a capacitance 9 picofarad are connected in a series. Series, okay? Series. What is the total capacitance of the combination? See, series means CS 1 by C, 1 by C, 1 by C, right? Because 3 identical. So that means 1 by 9 plus 1 by 9 plus 1 by 9, right? So 1 by CS that is equal to 3 divided by 9. That means 1 by 3. So CS that is equal to 3 picofarad, right? 3 picofarad. Get your point? Okay, everything we are doing it. Just you need to pay attention. That's all. What is the potential difference across each capacitor of the combination connected to a 120 volt? So capacitance value, it is the equal, right? 9 picofarad, 9 picofarad, 9 picofarad. So potential difference divides equally. Therefore, potential difference across each, okay, total potential divided by 3. Because 3 capacitors are there, equally divides. Therefore, VT divided by 3. So each capacitor that is equal to 120 divided by 3. So how much it is? Voltage across or potential difference across each capacitor, that is 40 volt. 40 volt. Got it? Okay. Now let's move on to the next concept. If a parallel plate capacitor with the air between plates, each plate has an area 6 into 10 power minus 3 meter square. The distance between the plates is a 3 millimeter. Calculate the capacitance of a capacitor if this capacitor is connected to a 100 volt supply. What is the charge each plate of the capacitor? Here we need to calculate what is the charge. Okay. So here capacitance formula. Capacitance, it is given by A epsilon naught divided by D. And capacitance definition, that is a Q divided by V, right? Substitute here. Q divided by V, that is equal to A epsilon naught divided by D. And here you need a Q, therefore A epsilon naught V divided by D. Substitute the values, that's all. Okay. So Q, that is equal to, what is the area? That is 6 into 10 power minus 3, okay, into, what is the epsilon naught value? 8.854 into 10 power minus 12. It is a constant, okay. Now, next one, voltage. Voltage, how much it is? 100 divided by, okay, divided by D, distance means separation between the plates, that is a 3 millimeter. Therefore, 3 power minus 3, okay, 3 into 10 power minus 3. So, 3 ones are 3 twos are. So, remaining calculated Q is equal to, so let's make it as a 9 approximately. So, this will become 2 into 9, 18 into 10 power minus 3 into 10 power. Okay, this minus 3 get cancelled. Here you can see. Okay, this 10 power minus 3, 10 power minus 3. Now, here into 9 already calculated, and here 10 power minus 12 into 10 power 2. This 100 can be written as 10 power 2. So finally, you are having 10 power minus 10 Coulomb. Or else, Q is equal to 1.8 into 10 power 9 Coulomb. Or Q is equal to 1.9 nano Coulomb. Got it? All three are correct answer. All three correct answer. Got it? Okay. Yes. Rhythm gamer. Sir, what is TIR? Class 10. That is a total internal reflection. Ray optics, it is there. Okay. We can discuss it. Got it? Okay. Now let's move on to the next topic. 12 picofarad capacitor is connected to a 50 volt battery. How much electrostatic energy is stored? E is equal to of CV square, right? CV. E is equal to of C, it is at 12 into 10 power minus 12 because picofarad, and 50 volt I can write as a double. Okay. So calculate it and get the answer. Okay. Now. Yes. Now finally we are in third chapter. Finally we are in third chapter. We are in third chapter. Okay. We are in third chapter. So after completing this chapter, okay, we can have at least a 15 to 20 minutes break. Got it? Okay. Now, I'm telling you, the first 3 chapters are very big chapters. Okay, very big chapters. And next you see, after 4th chapter, you see, half an hour, 40 minutes, half an hour, 40 minutes, one chapter. will be eliminated from our task. Okay, now current electricity. So trend analysis, you can go through it. Okay, I don't want to waste your time as well as mine. Okay, already have given questions across all the sets. Okay, and here are the topics, and next one, deleted topics. Okay, deleted topics also have given. Please go through it without confusion. You have to prepare for your board examination. Okay, now let's move on to the topic, that is the electric current. What is this electric current? It is the rate of a flow of a charges, right? It is the rate of flow of charges. In a conductor, what is the reason behind a current? If anybody asks you, the reason is a free electrons. Okay, free electrons. So here you can see electrons will be flowing. Okay, electrons will be flowing in one direction. Electrons will be flowing in one direction. Electrons will be flowing in one direction. So this rate of flow of a charges, we are calling it as a, for example, this is area of cross section. Okay, area of cross section, we are calling it as a electric current. Got it? Okay, now expression. What is the expression for this current? First one, instantaneous current, that is a dq divided by dt. Next one, that is q divided by t. Okay, next one, graphical presentation is there, but for your board examination it is not required. It is only for competitive level, graphical presentation. Got it? Okay, unit. What is the unit? Unit of ampere. And I want Shweta Mishra. Correct answer. I am keep on observing that Shweta Mishra as well as yes, Gogita and one more Akash, I forgot his name. Okay, 10 to 15 students, we are very interactive. Okay, please continue that. Okay, now unit. What is the unit of a charge? That is a Coulomb. And what is the unit of a time? That is a second. This one can be written as Coulomb per second. This only we are calling it as a ampere. Okay, should be written with a small letters. Okay, ampere. So that is can be written as capital letter A. Quantity, it is a scalar quantity. Okay, scalar quantity. And dimensions of a current, that is, okay, dimension of a current. So if I write dimension of a charge, okay, this is AT. And okay, directly I can write A, no? TT get cancelled. So dimension of a current, that is A power 1. Okay. So even though the electric current has a direction as well as a magnitude, we do not consider it as a vector quantity because it do not follow vector law of addition. Okay, generally we can call it as a tensors. Okay, we can call it as a tensors. Got it? Now, next one. Come on. What is 1 ampere of a current in a conductor? So just remember the definition, Q divided by T. So 1 coulomb of a charge flowing through a conductor in a 1 second, that flow of electrons, we call it as a 1 ampere. 1 ampere is the current when 1 coulomb of a charge, okay, flows through a conductor in 1 second is called a 1 ampere. Got it? Okay. Yes, Ajay Krishna. Yes, you are the one. Okay, Ajay Krishna. Shows the direction but does not follow vector addition. So generally higher order tensors. Okay, when you go to higher studies, no, there you will be learning about the tensors, first rank, second rank. Okay, when do we say even some physical quantity follows direction. They have a direction as well as a magnitude, but still we don't call it as a vectors because they do not follow vector law of addition, one of the reason. And rank of a tensors, it depends on a rank of tensors also. Okay, it is not there for your syllabus. Don't scratch your head. Okay, just ignore scalars and vectors. That's all. Scalars means it is expressed as a magnitude, that is a numerical value along with unit, and vectors expressed as a both magnitude as well as a direction. That's all. Okay. Yes. Cricket fan. Sir, you are Tamil. Okay. Now, so this is the definition of 1 ampere of a current. 1 ampere of a current. Now, let's move on to the next question. How many electrons per second constitute a current of 1 milliampere? So here we have a current of how much it is? 1 milliampere. So 1 milli can be written as 10 power 3 ampere. Therefore, I is equal to, okay, I is equal to Q divided by T. Right? What they are asking, how many electrons? By quantization of a charge, can I write it as a Q as a NE divided by T? I need N value, therefore, I can cross multiply it, I into T divided by E. I is how much? 10 power minus 3 into time is 1 second because they are asking per second, and E is 1.6 into 10 power minus 19. Here you can write it as a 0.625 into 10 power minus 3. This 10 power minus 19, if I shift that into numerator, it becomes a plus 19. Therefore, N is equal to, what is the value? This is the 3 and a 16. So I can write 6.25 into 10 power 15 electrons. 10 power electrons. Okay. Got it? Now, state Ohm's law. We have learned this Ohm's law from foundation level also, right? Exactly, sprinkle. Sprinkle, just one saying, exactly, right answer, right answer, right answer. Ajay Krishna, correct answer, correct answer. Okay, very good, very good. Yes, very good, very good. Now, here you can see this Ohm's law. We have learned this Ohm's law statement from the foundation, right? 10th grade. So what does it state? See, there's a potential difference applied across the ends of a conductor is directly proportional to the flow of a current at a constant temperature and physical conditions, right? Same statement you can write, okay? So no need to break your heads, okay? So this is the statement at a constant temperature and physical conditions, that should be there, okay? Yes. Now, next one. Resistance. Resistance means it is the property of a conductor which opposes a flow of current. It is the property of a conductor which opposes a flow of current. What about conductance? Resistance is reciprocal of a conductance. If resistance obstruct a flow of a current means, it is opposing flow of current means, what about conductance? Conduct the electricity. Means it supports the flow of a current. Opposite. Very good. I is equal to, no, V is equal to IR. Okay. Jashwant Singh. It is not I is equal to RV. It is the V is equal to IR. Got it? Okay. Very good. Very good. Yes. So Ajay Krishna allows, very good. Okay, fine. Imanshu, international definition of 1 ampere. Yes, I have used that. Okay. See, this 1 ampere, chapter to chapter vary. In a parallel, force between two parallel conductor, okay, current carrying conductor, the definition of 1 ampere going to change. In electrostatic, we have a different definition. In current electricity, we have a different definitions. Okay, but unit is same. Okay, unit of a ampere. Okay, definition also. Okay, now resistance, it is defined as the amount of opposition offered by the conductor to the flow of electrons. That means flow of a current within the conductor, ratio of a potential difference between the ends of the conductor to the current. So by Ohm's law, we can say V is equal to IR, right? Then what about resistance? That is V divided by I. Simple. Okay. Then what is the unit of resistance? Unit, that is ohms. Okay. Now, 1 ohm definition. See, so 1 ohm of, see, resistance of a conductor is said to be 1 ohm when 1 volt of a potential difference applied across the conductor and 1 ampere of a current flows through it. That is the definition of 1 ampere. Exactly. Yes. Opposes flow of current. Yes. Okay. Now, see, this 1 ohm is nothing but 1 volt of a potential difference applied across the conductor and 1 ampere of a current flows through that. So that means 1 volt per ampere. Got it? Now, next one. Resistance of a conductor depends. So, resistance, it is given by rho L divided by A. Okay. So, R means resistance of a conductor. Rho means nature of the material or resistivity of a material. That indicates what type of a material it is. Whether copper, whether aluminum, whether tungsten, whatever it is. Okay. So, that rho indicates it is the nature of the material. Got it? Out of, I'm not getting your name. Sir, I want these notes. Where to get? After this session, you will be finding the link below the same video. If you click on that, you will be getting the notes. Okay. Don't worry about it. Yes. So this one, L means length of the conductor. Okay. Length of the conductor means, if I consider, okay, if I consider this is a conductor, this is the length of the conductor, and this is the area of cross section, and material made up of means whether it is a copper, aluminum, or any other material, that is the indication of a rho. Okay, now, so here you can see by the formula you can note down that length is directly proportional to the, resistance is directly proportional to the length, area, nature of the material, and temperature. Temperature you'll be learning about in few seconds, okay, because that is very important. This is the basics, okay. These are the basic things, okay. Now let's move on to the next concept. Resistivity. Resistivity means it is the resistance of a conductor of unit length and unit area of a cross section. Unit length, unit of area of cross section means 1 meter of length and 1 meter square of area of cross section. Then we can consider it as a resistivity. And few people like, sir, I didn't understand. See, simple. R is equal to rho L divided by A. So what is the resistance? Resistance when length, resistivity is nothing but when length is 1 meter, area is 1 meter square. Okay, then what are the values then? 1 divided by 1. So that means resistivity is nothing but resistance only. Okay, see, the resistivity of the material is defined as the amount of opposition offered by the conductor to the flow of electrons of a unit area of cross section and unit of length. That means 1 meter square and 1 meter length. Got it? Okay. Now, resistivity depends on nature of the material of the conductor. Next one, temperature, and next one, presence of impurities. Okay. This one you are going to learn drift velocity. Okay, drift velocity, current, as well as conduction relation. Okay, where you will be learning about this. Yes, very good. Next one, case 1. So drift velocity, okay, case 1. See, conductor means, okay, if I consider a conductor, first of all, do you know what is the conductor? It is nothing but a wire, okay. Yes, Shweta Mishra, correct. Okay, now here you see, conductor means a wire, normal. Where do we see in our house, okay, household circuits? Those wires only we are calling it as a conductor. But once you open that insulation, means a rubber wire, okay, rubber on the copper wire, you remove it. Inside that you can see wires, right? That wires only we are calling it as a conductor. And making it as a zoom, okay, make it as zoom. Zoom it. That looks like this only, okay. So now that wire is not connected to a battery. So electrons in a conductor will be arranged in a random direction. Okay, one is moving in this direction, one is moving 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 this direction, that direction. So average velocity, they are moving, not at rest, free electrons only, they are moving. But you can say they are moving in a random direction. Random direction means what is the average initial velocity, okay? Average velocity when it is not connected to a battery. 0, because velocity depends on a directions also, right? So they are in different direction. Average velocity of all these electrons, if I consider, that is a 0. Got it? Okay, are you getting my point? What happens if I connect one battery across the terminals, means ends of the conductors, okay? If I consider this side one and this side one, and this side it is a positive, okay? This side it is a positive and this side it is a negative terminal. So battery it is connected. So what happens due to the battery converts electrical energy, means from chemical energy to electrical energy. And due to that battery, what happens in the, okay, in the inside material, okay, inside material, electric field will be developed. Electric field will be developed. In what direction? High potential to low potential, right? Now what will happen? Electrons, okay, electrons start to move from, okay, electrons start move from, okay, here I'll consider less number of electrons, because if I use maximum numbers, no, it looks odd. So that is the reason I'm using less number of electrons, okay. Now, here electrons will move towards positive terminal, towards positive terminal, towards a positive terminal. And due to electric field, the electrons are flowing from low potential to high potential due to electric field. And they are moving with a uniform direction. Means unidirection, not uniform. That is a unidirection. Means same direction the electrons are flowing. So when the electrons are flowing in a same direction, then current will be flowing. And what will happen, electrons start move from negative potential to positive potential due to electric field, and these electrons starts colliding each other. Due to that, heat will be produced. Okay. So this is about, about electrons at an atomic level. And here you need to know, sir, what is the average velocity of this? When the battery is not connected, we can say that it is a 0. Then what is the case when the battery is connected? So here you can consider, okay, see, first of all, definition. When a conductor is connected to a battery, the electric field developed in a conductor. Each electron experiences the force. All electrons experience an acceleration, and hence they start moving towards a positive terminal, but they keep on colliding. Clear? Okay. Definition of drift velocity is done. Okay. Now, drift velocity. So first, okay, here already it is connected, okay, connected to a battery. Fine, connected to a battery. Here you need to know initial velocity. Initial velocity means when the battery it is not connected. First of all, if I want to calculate drift velocity, first of all, I need to know what is the drift velocity. The average velocity of all the electrons moving towards the positive terminal of a battery is called drift velocity. Means from negative potential to the electrons started moving towards a positive potential, right? Correct? Okay. Now, here, what is the velocity? Is our question. According to equations of motion. So, initial velocity is 0 because initially they are arranged in a random direction. Gone. So, remaining part, V is equal to ut, right? Sorry, at. U is equal to at. Now, what is A? Acceleration. So, F is equal to ma, right? F is equal to ma. And we know that F means in a electric force, okay, electric force. That is given by QE, ma. By the definition of electric field, okay, this is by the definition of electric field. I want A. Therefore, QE divided by m. This is the acceleration. Substitute here. For velocity of one electron. So, as it is an electron, I can use this Q as a E. Therefore, here I can consider this one, okay. Acceleration EE divided by m T1, okay, for the first electron. Second electron, EE divided by m 2. Why E is common? Because charge on electron, it is same. Electric field for all the electron, it is same. Mass of the electron is also same. Here m is mass of the electron, is the electric field, is the charge on electron. And T1, it is the time taken by the first electron, and the T2, time taken by the second electron, and so on. What I'll get? Vn, that is EE divided by m, that is Tn. Okay. Now, according to the drift velocity, average means V1, okay, V1, V2 plus V3 plus so on divided by n. This is the average velocity. By the concept, first year we have learned how to take average and all, right? So here just substitute the values. So drift velocity, I'll be naming it as a Vd, okay? V1 value, how much it is? EE divided by m T1, electric field, okay? Everything is a vector quantity. That is the velocity and electric field. Now, EE divided by m T2 plus so on. EE divided by m into Tn, all divided by n. So what I have to do? So take EE divided by m common. Drift velocity, EE divided by m common. Remaining T1 plus T2 plus so on Tn divided by n. Okay. And this one I can write it as a Vd, that is equal to E divided by m tau. This is, okay, this is a drift velocity where this tau indicates, okay, where this tau indicates relaxation time. Relaxation time. This is relaxation time. Got it? Okay. Now let's move on to the next concept. The average time of a collision for all the electrons is called relaxation time. Already we know that relaxation time tau, that is equal to T1 plus T2 plus T3 and so on divided by n up to Tn. Okay. And unit, that is the seconds only. Relaxation time. Okay. Number of electrons. Okay. Time taken by all the electrons. Okay. Seconds. Okay. Seconds only. Now, mobility. Mobility means it is related to moving charge particle. Mobility, mobile, move. Okay. So electrons moving per unit electric field. Electrons are moving per electric field. We are calling it as a mobility of electrons. Therefore, here I can define it as a drift velocity attained per unit electric field. Okay. What does it mean? So here mobility is given by mu, that is equal to drift velocity per electric field. Here you can further simplify it as E divided by ME into tau. So here you can see E get cancelled, and so mobility, it is given by E tau divided by M. Mobility is independent of electric field. Okay. Got it? Two formulas. We can use any one. Okay. So let's consider unit. What is the unit of a drift velocity? Meter per second. Okay. Meter per second. And what is the unit of electric field? That is a volt per meter. And if I shift that meter per second to the numerator, it will become meter square. Okay. Per volt a second. So this is the unit of mobility. Okay. Unit of mobility. Now let's move on to the current density. Current density. Density means it is a number, right? Maybe mass density means mass per unit volume. Charge density means there are three types. And here we have a current density, means with respect to area, how much current is flowing through it. With respect to area, particular area, how much current is flowing through it perpendicularly. Okay. So that is the definition of, current density. The amount of current passing perpendicular through the area of a cross section conductors. Okay. Section of a conductor is called current density. And it is given by, current density, it is given by J vector, okay, current divided by E vector. Or else you can write I is equal to J vector into A. This is dot product. Therefore, I is equal to JA cos theta. All these formulas you can use. Okay. This is I. Okay. All these are current. Okay. And this is area. This is area. Right. And unit of a current, that is the ampere, and unit of area meter square. So here you can write ampere meter square is the unit of current density. And dimension. So dimensions, if I write dimensions of current A and dimensions of area L square, I can write A power 1 L power minus 2. This is the dimensions of current density. Got it? Okay. Now, very good, Kanishka Sharma. And how about Gugita? Okay. I think you are answering in the beginning, right? Your interaction was very good. I don't know what happened. Yes. Okay. Correct. Very good. Let's move on to the next one. Current, drift velocity, and resistance, resistivity, and conductivity. This derivation is very, very important. Okay. First, derive the relationship between current and drift velocity. Okay. Current and drift velocity. So generally, current, it is given by Q divided by T. Right. So I is equal to Q means that is given by according to the quantization of a charge. Okay. According to the quantization of a charge. Okay. That is given by NE. I am using capital letter. Okay. because here small letter I'm using as a carrier density. Okay. Sir, in the first chapter you have used a small letter n, here using capital letter N. Chapter to chapter it is varying. Okay. Don't worry. So here Ne divided by T. Use this. What is N? It is the number of particles, okay, carrier density, charge density, okay, number of particles per unit volume. So here number of particles, this can be written as volume into E divided by T. And volume can be written as, okay, area into length. Means if I consider length of a conductor, L, okay, length of the conductor as L, and area if I consider it as A. Now here what happens, this volume I can write it as A into L. So here further simplification divided by here volume it is rectified E and here T. Yes, okay. Now you see N, A and E and here L divided by T, okay, L divided by T. So this L divided by T, it is a drift velocity, okay, like a displacement per unit time. Displacement per unit time, it is nothing but drift velocity. Therefore, I is equal to N E V D A. Okay, N E D A. Okay, N E V D A. Right? Where N is the charge carrier density, that is the number of particles per unit volume. E is the charge on electron. V D is the drift velocity. Where A is the area of cross section of a conductor. Okay. Derive an expression to prove Ohm's law. Ohm's law. What is the Ohm's law? V is equal to I into R, right? V is equal to I into R. So by the definition of a current relation between drift velocity, that is NEVDA, right? Yes or no? Now I is equal to NE. What is the drift velocity? EE divided by M into tau into A. Further simplification, NE square, okay, and tau divided by M. E can be written as potential difference. This is the potential difference, okay, V divided by volt per potential difference per unit length and into E. So here V is a potential difference, okay, potential difference, and here V is a volume. Here volume, okay, here volume, here volume, okay, here volume. Got it? Okay. Now here potential difference. V means potential difference. Now V, take it out. Rearrange the equation. NE square tau A divided by ML into V. Just cross multiply it. V, that is equal to ML divided by NE square tau A into I. Okay. Now this entire term, okay, that is R is equal to ML NE square tau A. Okay. ML NE square tau A, it is the resistance. Okay. This is the resistance and potential difference. Potential difference it is given by, okay, potential difference, that V is equal to R into I. R into I. Same thing, right? Same thing. Ohm's law. That is V is equal to R into I. Where R is this one. Where R is this one. Got it? Okay. This is about, relation of Ohm's law. That is V is equal to R into I. And the next one, let's see. Next one. Derive the relation between current density and conductivity of a conductor. Or derive J is equal to sigma into E. We need to derive sigma, okay, J, current density, okay. That is capital letter J, that is equal to sigma into E, okay. Now, so original formula I is equal to NEVDA, right? So here what I will do is, I'll cross multiply that E, remaining NEVD. So I divided by A, by the definition of current density, what is that? I divided by A, that is the J, right? That is equal to NE. What about VD? EE divided by M into tau. So here what I will do is, I'll remove, means I'll shift this E outside the bracket. NE square tau divided by M. Okay, so this is This is E. This is the electric field. Now, the same formula I'll be writing here. It's a simple way I'm doing it, okay? No complication, nothing. N E square tau divided by M into E. So this only we are calling it as a, okay, we are calling it as a conductivity, that is E. So where sigma, that is a conductivity, Ne square tau divided by M. Conductivity, okay? So this is the required relation. Got it? Okay. Got it. Okay, let's move on to the next topic, resistance and resistivity. So differences, you please go through it, okay? If you do not get it anything, please ask me, okay? I'll be answering your questions, right? So just go through it. It is the theory part. Now, limitation of Ohm's law. What are the limitation of Ohm's law? It is applicable at very high and very low temperature. It is not applicable, okay? Here you need to point out that is not applicable. And it is not applicable to electron tubes and discharge tubes. And it is applicable for metallic conductor. Why? Here temperature is varying. Why this electron tubes, okay? This Ohm's law is not applicable for electron tubes because they are varying with a temperature. Yes? Sir, this part-wise complete marathon? Yes. Not part-wise. It is complete syllabus, okay? Part-wise means chapter-wise. Some part, and total syllabus, okay? Yes, applicable for constant temperature. Very good. Got into the track. Got into the track. Gogita. Okay? Now, very good. Now, next one. What are ohmic devices? The devices which follows or obeys Ohm's law is called ohmic devices. And graph you see, V versus I graph, the curves will be linear. Straight lines, okay? Example, voltmeter, ammeter as well as galvanometer. These are ohmic devices. Got it? Okay. Piyush Raj, what about for Hindi speaking? Piyush, I guess, Hindi channels are there, PW Hindi channels, so please visit them, okay? Got it? Okay. Next one. Non-ohmic devices. The meaning only is saying it is non-ohmic. It do not obey Ohm's law. And the curve of this VI graph, okay, it is not a linear, it is a non-linear, okay? It is not a linear, it is a non-linear. Like this, okay? Curved one. V versus I graph, okay? Electronic tubes, discharge tubes, semiconductors, transistor. Because all these are varying according to the temperature. Got it? Okay. Now, next one. By experiment, that is the temperature dependence of a resistivity. So, here before that, R is given by rho L divided by A. Depends on temperature, depends on nature, depends on length, depends on area. More the length, more the resistance, more the area, less is the resistance and nature of the material. What about temperature? We have not talked about a temperature of a conductor, right? Now you see. By experiments, okay, thermal expansion, linear expansion, cubical expansion, I hope you have learned in the first year, right? So in the same way, if I consider resistivity by experiment, okay, I have not given by experimental observation, what we got to know is change in resistance that is related to original resistivity, okay, not resistance, resistivity, and alpha change in temperature, okay. Alpha is the coefficient of a linear expansion, So here you can consider this change in resistivity can be written as rho minus rho naught. Rho naught means it is the initial resistivity. Rho naught alpha delta T. So here I need rho and I'll shift this negative rho naught to the right hand side. It becomes rho naught plus rho naught alpha delta T. Right? So rho naught plus alpha delta T. Right? So what I will do is For this equation, okay, for this equation, multiply and divide by L and A. Multiply L divided by A. So right hand side also same, L divided by A. Remaining, that is a 1 plus alpha delta T, right? So here resistance becomes R naught 1 plus alpha delta T. Graphically if you see, okay, graphically if you see, this one will be starting from here. What does it mean? This is the resistivity and this is a change in temperature, okay? So here, this part is rho naught. If you consider this is R naught, okay? Change in temperature as it is. Got it? This is the presentation. How the conductor, means resistance of a conductor depends on temperature, okay? I hope it is clear, right? Now, let's move on to the next topic, that is the graphical presentation of variation of resistivity and nichrome. Already I have shown this one, okay? Nichrome is a non-ohmic device, non-ohmic resistor. So that is the reason you got it as a curved line, okay? Not a linear line. Next one, define electrical energy. Electrical energy is the total amount of work done in maintaining electrical current in the electrical circuit. Simple definition, okay? You can go through it. Simple definition. Next, unit. SI unit, it is a joule, okay? SI unit is a joule, and a commercial unit, kilowatt hour. That is kWh. Got it? Okay. Now, electric power. Generally, how do you define? It is the rate of doing work. But here, what it is doing? It is the electrical energy consumed by the electrical appliance per unit time. That we call it as a electrical energy. Okay. Now, here work done. Okay. Electrical power is the rate at which electrical work is done by the source in maintaining electrical current. So here, expression if I speak, okay, that is P is equal to I into V. This one, okay, this one we can consider it as a original one, okay. Power that is given by work done divided by time. This also can be written as energy per unit time, okay. So here, after rearranging, okay, P is equal to I into V, okay. Unit, that is a watt. SI unit is a watt. And a commercial unit, kilowatt, okay. So this is about energy and power and Joule's law of heating. What is the cause of heating? Collision of electrons in a conductor after applying potential difference, or else the current is flowing through it. So that is the cause of, heating effect in a conductors. Collision, okay, due to the collision, the sum of the part of energy lost as a heat energy. So that law, it is given by Joule's law of heating, okay. Then what is the statement of this Joule's law? Statement, okay. All these electrons experience a collision and some part of energy is lost as a heat. And Joule's law of heat says that, okay, statement maybe for 2 marks they'll be asking, okay. Now, when a current I is made to flow through a ohmic conductor of a resistance R for the time t, heat is produced such that H is directly proportional to the I square and H is directly proportional to the R, H is directly proportional to the T, okay, directly proportional to the T. And finally, we can have this one as I square RT. Are you guys following? Okay, are you guys following? I'm not interacting much, okay, because time is moving, okay. Now, here SI unit, it is a joule, okay. SI unit, it is a joule and represented by capital letter J, and it should be small letter j, joule, okay. Practical unit, okay, energy, calorie. Heat energy, it is measured in calorie, okay. Now, let's move on to the heat energy and electrical energy. Heat energy, how do you consider heat energy? H is equal to I square RT, right? I square RT. And here you see, power, it is given by energy by time, right? This energy, can I write it as a power into time? And this energy, nothing but heat energy, can I write it as power into time, right? Power into time. Yes, power into time. Now you see, in place of H, it is H. In place of a T, it is a T. And what about this? Power. So what is the power? I square RT. Why in terms of I square RT? Because in a series combination, current will remain same, but the potential difference will vary. But a series parallel combination, potential difference remains same and the current will be varying. So that is the reason. Okay. Now, in terms of Ohm's law, if I use Ohm's law, V is equal to IR, right? So what I will do is, I'll replace this I. What I'll get? V square divided by R square into RT. So finally what I'll get? V square T divided by R. Okay, again this is a P. Now P is equal to V square divided by R. This is for parallel combination because V is a constant in parallel combination, right? Now last one, H is equal to IVT. And again it is a P. P is equal to I into V. Okay, if you follow what I'm saying, no need to learn. No need to go through the slides again. Okay, I am giving guarantee. Listen carefully. Okay, that's all. Now, next one. Okay, what are the characteristics of heating element? What should be the characteristics of heating element? They should have high resistivity because they should not melt. Okay, they should not melt. Next one, they should have high melting point. Okay, so on passing current for a long time, they should not melt. These are the properties the heating element should have. Okay, now electric bulb. If I consider electric bulb, okay, electric bulb. So here, electric bulb. So if I consider this power of a bulb, that is given by, okay, I into V. So here power rating, you can see power rating and voltage they will be giving, right? Power and P rated. If you buy one bulb, you see they have given, they'll be giving only P and V rated, right? Then how to calculate resistance? Okay. Resistance, it is related to power, okay? Power and voltage. That is V square divided by P. V square divided by V square, that is V rated square divided by P rated. This is how you can calculate resistance of the bulb, okay? Resistance of the bulb, you can calculate V rated square divided by P rated. Okay, V rated divided by P rated. Got it? Okay, now let's move on to the next concept. What are the characteristics of fuse? Fuse, it is made up of lead and tin, right? It should have a low melting point because if there is an excess of electric current flowing through it, that should break down, okay? So that it becomes an open circuit. So electrical appliance can be safeguarded by this fuse. Fuse is nothing but it is a safety device used in an electrical circuit. And the properties, if you see, it should have high resistivity and it should have low melting point. Okay, it should have high resistivity and it should have low melting point. Okay, now cell, a device which is used to, for example, every day we are using cells, maybe watch cells, remote cells, okay, battery cells, everything we are using, right? So here what happens? Cell means it is a chemical device which converts chemical energy to electrical energy. Already you know that, right? So how? Here we need to concentrate more on internal resistance, potential difference across a terminals, that is a terminal voltage, and drop in voltage. We have to concentrate on these three important parameters. Okay, now, so already we know that, right? So this is a symbol of, okay, the symbol of this cell is given by like this, okay? If both the lengths means height wise, that will be capacitor. One height is more and one height is less means we have to consider it as a cell. And battery, this is a cell, okay? This is cell. And the combination of cells, combination of a cells, okay? Combination of a cells, we call it as a battery. Got it? And this is high potential and this is low potential. This is high potential and this is a low potential. Got it? Okay. Now, EMF and resistance of a coil. So your simple and very important definitions are there. Please go through it. Terms related to cell. Okay. The first one, EMF of a cell. It is a total potential difference or else a total voltage of the cell when it is not connected to any external circuit. Means, for example, if you hold a everyday cell, the value which is written on that particular cell, we call it as a EMF of that particular cell. And if that battery or a cell, okay, everyday cell, it is used in the circuit, then we cannot call it as a EMF of a cell. Instead of that, here we have a two. One, it is a terminal voltage, another one is drop-in voltage. Okay, let's see. It is the maximum potential difference between two terminals of the circuit when it is open. Means it is not connected to any external source. Internal resistance, like resistance. Resistance means it is the obstruction. It is the property of a material or conductor which opposes a flow of current. Here internal resistance means it is also obstruction offered by the elements of a cell. Means inside chemicals will be there. No? By them, it is opposed by, opposed electricity or current electricity by these elements. We are calling it as a internal resistance. Internal resistance is simple word, that is obstruction offered by the elements of the cell inside battery. It takes place inside the battery. Okay. For example, EMF of battery, they have mentioned, for example, okay, 5 volt. Okay. When the cell is used in the circuit, when you calculate, means using the voltmeter and apply at the terminals, you'll be having, or else that reading will be 4.8. Where is that? 0.2 volt? It is a drop in voltage. Why it is a drop? Because of internal resistance of the cell. Got it? Okay. Now, next one. EMF, internal resistance and terminal voltage. Okay. So please wait for 2 minutes. Okay. I'll be back. 2 minutes. Okay. Nothing, not more than 2 minutes also. 2 minutes I'll be coming. Okay. I'll drink water and come back. 2 minutes. Hello students, let's get started. I hope it is clear. Okay, now it's time to know EMF, internal resistance and terminal voltage relation. Okay, so here you see, when you consider general definition, okay, Ohm's law, by Ohm's law, okay, by Ohm's law, by Ohm's law, what does it says? So if you want to calculate current, it will be V divided by R, right? So total potential difference across resistor, right? So here how many resistors are there? Two. One, it is the internal resistor, another one is load resistor. I'll consider it as a R, external resistor. Okay. So now what I have to do is I, that is equal to V divided by, in place of V, put total potential difference, that is EMF of the cell. In some books, they have used this epsilon as a E also. Here they have used epsilon, right? Now, next one, resistor. How much? Total resistor. Total potential difference and total resistor. This can be written as R. Rearrange this equation. Epsilon, that is equal to I into R plus R. So this is load resistor, that is external resistor, and this is small resistor, that is the internal resistor. Okay. Now, next one, epsilon, open that bracket, IR plus I small letter r. And this one, okay, so capital letter IR indicates terminal voltage, okay, IR, VT, terminal voltage, and VD, okay, no, I'll use capital letter D, drop in voltage drop, okay, or else you can use voltage drop due to internal resistor, okay. Now, here epsilon, that is equal to V plus V, that is terminal voltage plus drop in voltage. So, total potential, it is given by terminal voltage as well as drop in voltage. Terminal voltage, that is due to external resistor, and a small letter r, that is the internal resistor. Due to that, there will be a drop in voltage. Got it? And majorly, you need to remember this one. This formula is very important. Okay, now let's move on to the next concept. Derive an expression for equivalent EMF and equivalent internal resistance when they are connected in series. This is internal resistor. Let's consider this is the internal resistor. Means how many cells are there? How many cells are there? Here, 2. Okay, 2 cells are there. Therefore, I can use, okay, instead of epsilon, I'll be using EV. This is E2 and this is R2. And this is E1, this is R1. So, 3 terminals I'll be considering. A, this is B, and this is C. Okay, A, B, and C. Now, so if I want the total potential difference across AC, okay, total potential difference, total voltage, or else total voltage, that is voltage across AC, that will be VAB plus VBC, right? VAB and VBC. By previous case, okay, by previous case, that is epsilon, that is equal to, okay, you can use this relation also, okay, no problem. So by that you can consider, okay, by that you can consider I is equal to, okay, I is equal to, okay, that is E is equal to I into, or else V also you can consider V plus I into R, right? So this is a potential drop and this is internal resistance. Got it? Now, so use this same relation, okay? So here I need V. Therefore, E minus IR, V minus IR, apply here. VB across VAC, sorry, V across VB, that will be E1 minus IR1, right? Across VAB, what is the EMF? E1, resistance R1, therefore current IR1, okay? Now across BC, that is E2 minus IR2. Got it? Now simplification. Now VAC, okay, VAC, that is equal to E1 minus IR1 plus E2 minus IR2. Okay. Now rearranging E1 plus E2 minus I. If I take a common, that will be, okay, R1 plus R2. So comparing, okay, VAC, that is equal to E1 plus E2 minus I R1 plus R2. Okay, with respect to this one, okay, with respect to this one. So here you can consider V, that is equals to AC E equivalent minus IR equivalent, right? E equivalent minus R equivalent. So finally you will be having E equivalent, that is equal to E1 plus E2, E1 plus E2, and R equivalent R1 plus R2. Got it? So these are the relation you need to practice. This is for series combination. Got it? And please let me know, this is, you consider it as a homework, okay? Consider it as a homework. Consider it as a homework. Same relation you have to use. What is that relation? What is that relation? So I is equal to epsilon divided by R plus R, right? So one more, V, that is equal to E epsilon E minus IR. So here I is equal to, okay, I is equal to, what you can write this one as E minus V divided by R. So in this parallel combination, what happens is potential difference, voltage will remain same, but current will vary. So that is the reason in terms of I1 and I2 you calculate, okay? In terms of I1 and in terms of I2. You calculate and substitute, compare this, okay? You'll be getting your answer. Got it? Okay, now let's move on to the next concept. Kirchhoff laws, okay? First law or a junction law or a Kirchhoff law. What does it indicate? KVL, KCL, okay? First law, current law, okay? Now, you see, the net current at any junction is 0. Value of incoming current at a junction is equal to value of outgoing current. What does it mean? The current, okay, this is I1 and this is I2. At this junction, okay, at this junction, and this is I3. So here, what is the current left in this particular junction? It is a 0, I is 0. So that means the summation of a current at the junction is 0. This is the statement. It is based on conservation of a charge, because how much ever current is reached this junction, okay, how much ever current is reached at this junction and the current leaved from this junction. Got it? Okay. Now, second one, sign conventions are very important. Incoming current, if I consider negative, outgoing current should be positive. Now, here you see incoming current, it is a negative, outgoing current, it is a positive. So finally, you can write this one as, okay, summation means all the current minus I1 minus I2 plus I3, that is equal to 0. Meaning of that statement, okay, meaning of that statement. And the conservation, it is based on conservation of a charge. Got it? Now, let's move on to the next concept. Second law or loop law or Kirchhoff's voltage law. Okay, Kirchhoff's voltage law. Now, what do we have to do? Second law or loop law or Kirchhoff law. So what does it indicate? Total potential, okay, across, or else you can say total potential drop across all the components is 0. Okay, all the components will be 0. Okay, got it? Okay, now sign convention, if I consider, okay, if I consider this is battery and this is battery, okay. Now, if I consider this is a plus, okay, if I consider path in this way, okay, so this is moving from high potential to low potential. That means V will be negative. If I consider path in this particular direction and it is reaching from low potential to high potential, therefore V is a positive. Got it? V is a positive. Understood? Okay. Are you getting my point? Okay. Now, It is not tomorrow. I think it is 22, no? Shinchan? I think it is 22, not tomorrow. Right? You have 24 hours, right? So the benefit of attending this live session is, what will happen is, you'll be having 2 weeks for the preparation. So once you see this video, entire video, you'll be getting to know what are the concept and what depth of the concept you have to learn, okay? Right? Okay. Now, KVL is based on conservation of energy, right? These 2 points are very important. KVL, conservation of energy. KVL, conservation of energy, and KCL, conservation of a charge. Okay. Now, let's move on to the next concept. That is a Wheatstone bridge. So here you can see Wheatstone bridge, right? Wheatstone bridge. This is a P, resistance P, and this is resistance Q, okay? Resistance Q. And this is resistance R, and this is resistance S, okay? Now, this Wheatstone bridge is an electrical circuit in which unknown electrical resistance can be measured. Means, for example, any one of these, okay, any one of these, if we don't know the values, we can still calculate what is the resistance of that particular resistance. How? Here we have a, condition for balancing condition, okay? For balancing condition, I'm not deriving relations, okay? Because based on this, they can ask you a numerical part, okay? For balancing condition, okay? For balancing condition, that is a P divided by Q, that is equal to R divided by S. The ratio of a PQ and RS will be equal. Okay, ratio of PQ is equal to RS will be equal. That means the current will not flow through galvanometer. I is equal to 0. Okay, I is equal to 0. So this becomes a series and this is also becomes series, and the total resistance, it is the parallel combination, and finally you can calculate effective resistance. Okay. Yes, go get yes, P divided by Q is equal to R divided by S. Karan Pandey, very good. Gogita, very good. Okay. Shweta Mishra, conservation of energy, very good. Kanishka, very good. Summation B is equal to 0. Very good. I think, is there any lag? Is there any lag? No, right? Okay. No. Let's see. What is the next concept? Yes. So here, numerical part. A current of 5 ampere passes through a copper conductor, resistivity 1.7 into 10 power minus 7 ohm meter, of radius of cross section 5 millimeter. Find the mobility of a charge if their drift velocity is 1.1 into 10 power 3 meter per second. Can you calculate and tell me what is the value? Drift velocity they are asking, that is drift velocity with respect to mobility. Find the mobility. Mobility they are asking. Electric field. Okay. Is there any electric field? Electric field. A current of 5 ampere passes through the copper conductor, and a cross section area they have given. Find the mobility of a charge if their drift velocity is 1.1 into 10 power 3 meter per second. Okay. So what is the value? So drift velocity they have given. Drift velocity. This one is a drift velocity, and this one area of cross section, and this is a resistivity rho. Okay. So use this relation. Okay. ml divided by ne square tau a. Use this relation, and j, okay, j sigma e. Okay. So use this relation, you'll be getting the answer. Okay. Right. Use this relation, find the answer. Next one. So all these, yeah. Can you calculate this one? In Wheatstone network, P is equal to 20 ohm, Q is equal to 25 ohm, S is equal to 30 ohm, and R is equal to 15 ohm are connected in cyclic order. That means PQ, okay, that means PQ, that is equal to RS. We have to check it, okay. P value, that is the 20, Q value, it is the 25, R value, it is the 30, and it is the 15. So here you can see 4 by 5, and here 6 by 3. It is not matching, okay. This is not matching, this is a 2. So they are not matching. not balanced. Not balanced. That's all. Nothing else. Not balanced. Ratio, not balanced. Got it? Okay. Can we watch it for Gauss? See, I'm telling you, if the, please check the content, okay? Please check the content. So I think all the state board content will be same, okay? All the boards content will be same. You please watch this, okay? There will be some benefit. Not balanced. Very good. Kanishka and Jainav, not balanced. CBS board priority. Yes. Okay. Particular session, I'm giving priority to CBSE board students. Okay. Yes, Gokul, I'll be sharing a notes through the link. Okay. After the session, if you'll be finding a link below the video. So if you want a note, so please click on that and download the notes. Got it? Okay. Now, let's move on to the next question. In the following circuit, see, I'll be giving the clues. Okay. This is E1 and this is R1 and this is E2 and this is R2 and this is capital letter R here. You need to find out I. So I, that is equal to E divided by R plus R, right? So but here, what is the value of R? Here it is a parallel combination, right? Parallel combination. E value parallel combination you find out, okay? Parallel combination. Okay, parallel combination means E divided by R equivalent, okay? E equivalent divided by R equivalent, that is equal to E1 divided by R1 plus E2 divided by R2. Use this relation, okay? Use this relation. You'll be getting, okay? And R equivalent, you know that, what is the relation? R1 into R2 divided by R1 plus R2, okay? So, you substitute the relation here, you'll be getting E equivalent. You substitute E equivalent to here, R equivalent to here, okay? After finding this, you'll be getting the answer. Got it? Now, moving charges and magnetism. Okay. Now tell me, shall we continue or you want some break? Yes? Yes? Do you want some break? Okay, you want explanation, okay. See, here they have given combination of cells, okay? Combination of cells. And they're asking to find out what is the current, right? Current formula, that is a total EMF. That is nothing but E equivalent. Okay, because here we have one cell, here one cell, and clubbing it, we can find out equivalent EMF, right? And R is a external resistor, that is a 7 ohm, and R equivalent, that will be this value, okay? R equivalent value, use this one. E equivalent value, you can use this one. For this, you can find from here, okay? Yes, break. break. Okay. So you tell me how much time you need, okay? How much time you need? Tea break, okay. Sprinkle on fire, okay. Yes, tell me how much time you need? 10 minutes. Kanishka, 10 minutes. Jai now 20 minutes. And yes. 10 minutes, 20 minutes, 10 minutes, 20 minutes, 10 minutes, 20 minutes. Shinchan, 15 minutes. Okay. Next. Vinith, we should not reveal, okay? Okay, 100 minutes. What you'll do? Henil? Jainav, sir, average 15 minutes. Okay, 10, 20, 10, 20, 10, 20. Average 15 minutes, okay? Let's move on to the 15 minutes, okay? 15 minutes. So fourth chapter and the last biggest chapter. Okay, the last biggest chapter, that is the moving charges and magnetism. Am I audible? Yes, please confirm. Okay. Jainau, Shinchan. Yes. Is it useful? Is the session is useful for you? Amit Yadav, hi. Hi, hi, hi. Hello. Thank you, thank you. Your theater, thank you so much. Okay, Jainau, very useful. Yes, yes. Kanishka Sharma, yes, sir. Okay. Vinay the base, sir, I have a zero knowledge in wave optics. If I watch this lecture, can I understand this? Definitely. Okay, please wait and watch. Okay. Yes, sir, very useful. Tulsidas, thank you so much. Very good. Ajay Krishna, very good. Amish, Amish Sharma, hello, good evening. Good evening, good evening. We started from in the morning, right? We started with hi everyone, very good morning. And after that, good afternoon. Now, good evening. Okay. Trust me, after this fourth chapter, okay, every chapter maximum, max to max 40 minutes, okay, 30 to 40 minutes. And in that, electromagnetic waves, sorry, not electromagnetic waves, electromagnetic waves, okay, EMW, and I thought electromagnetic induction, okay. So electromagnetic waves, so magnetism and matter, and the next one, atoms, nuclei. So all these four chapters can be covered in a 1 hour, okay. So 4 chapter, 1 hour, okay. When will this session end? So till I think still 5 more hours, okay. Fine, derivation. Yes, yes, derivations we can do it, okay. So how many more hours approximate? So still we have 10 chapters, okay, 10 chapters. That means 4 chapters in one stretch. That is 1 hour, okay. So after this, we have one more chapter, that is ray optics, okay. Ray optics, it is 2 big chapters. If you want me to skip a few of the derivation, I'll skip and make it, less time. It is up to you, okay. You tell me how to manage. Yes, which chapter started, sir? Moving charges and magnetism. I hope the screen is visible for you, okay? Okay, fine. Let's get started. So now, the fourth chapter, it is the moving charges and magnetism. And let's see the first content of this chapter, that is sources of a magnetic field. So generally, what is the source of a magnetic field means? By bar magnet, we can produce or we can see the effects of a magnetic field, right? Other than that, what are the sources of a magnetic field? Moving charges, okay, moving charges also produces a magnetic field around it. Current carrying conductor also produces a magnetic field around it, right? So here, first if you see source of a magnetic field, okay, so first charges are at rest, okay, if we consider charges are rest, that means V is equal to 0 at rest. So magnetic field is 0, electric field, only electric field will be there, okay, only electric field. And a charge moving a constant velocity. Here electric field plus magnetic field, okay, magnetic field. Here V is a constant, okay, V is a constant. And here not a constant, it is not actually a constant, drift velocity will be there. And here accelerated charge, okay, accelerated charge, already have written. So in this particular case, here you can see electromagnetic radiation, electromagnetic radiation. So this one we are learning in atoms and nucleus, as well as electromagnetic waves. Got it? Okay. Now, next one. Next one. The magnetic field. What do you mean by magnetic field? It is the space around the moving charges. Okay, try to understand this concept. Okay, the space. Okay, the charges, the space around moving charges are current carrying conductor where the magnetic effects can be observed. That field or that reason we call it as a magnetic field. Okay, Atish Sharma, good afternoon. Welcome to the session. Okay, Uzma Parvez. Okay, I'm really sorry. I was busy with the content. Okay, good evening. Good evening. Welcome to the session. Okay, now here unit of this magnetic field, that is a Tesla, right? And it is represented by T. Next one, how is the magnetic field is produced? Already we have explained moving charges, current carrying conductors, okay, and bar magnet we can produce a magnetic field. Okay. Gogita, what happened? Why sad? Okay. Now here first one, that is a magnet can produce a magnetic field. And the next one, if you see, that is a current carrying conductor or wire can produce a magnetic field, and a moving charge can produce a magnetic field, and varying or by changing electric field can produce a magnetic field. Okay. So this concept you will be seeing in electromagnetic waves. Got it? Simple definition. Okay. Simple definition. Thak gaya. It should be, active, right? Ujjwal Singh. No, it is a physics class, okay? Uzma Parvez, hi, hello. Abid Sharma, good afternoon. Okay, Shinchan. Okay, now let's move on to the next concept, that is by experimental result, okay? By experimental result. This is a magnetic field, okay? This is a magnetic field and this is a motion of a charged particle with a velocity v. And both are moving with, okay, with respect to magnetic field, the charge is moving with a angle theta. These are experimental result, okay? These are experimental result. So by experimental result, we got to know force is directly proportional to the magnitude of charge. This is a magnetic force, okay? And force is directly proportional to the velocity of a charged particle. And force is directly proportional to the magnitude of a magnetic field. And force is directly proportional to the sine theta, okay, by the experiment observation. And by combining all these three, we got it as a QVB sine theta, okay, QVB sine theta. This is a force experienced by a charged particle in a magnetic field, okay, motion of a charged particle in a magnetic field. So here we need to understand what is the path or a trajectory of a charged particle when it is traveling or moving or projected into a magnetic field, okay? The first case, if we see the first one, factors, okay, before that, okay, what is that? Trajectory. Before that, we have some dependent factors, okay? Factors the force experienced by a charged particle moving in a magnetic field depends. C, Q, magnitude of a charge, V, velocity of the charge, B, that is the strength of the magnetic field, sine theta, okay? So this one, it is in a scalar form, okay? If you want to write in vector form, you can write a Q, okay? V into V vector into B vector. V vector into B vector. Got it? So this is a vector form. See, first one, magnitude of a charge, that is a Q. And next one, velocity, that is a V. And next one, strength of the magnetic field, that is a B. And angle between velocity and magnetic field, that is a theta. Right? So these are the dependent factors. So this question may arise for 3 marks. Okay? Now, Tulsidas, please don't... no, I have not skipped any derivation. Only one, right? That is a parallel combination. Okay? Right. Next one. Yes, motion of a charged particle in a magnetic field. So when a charged particle moving in a magnetic field, what will happen to the path of a charged particle? Okay, the first one we'll check out. Projected parallel to the field. Projected parallel to the field means velocity is parallel to the magnetic field. That means theta is equal to 0. Okay, theta is equal to 0 degree. And let's consider this is a magnetic field and this is the velocity. Okay, theta, angle between this velocity as well as the magnetic field, it is a 0. Hence, okay, hence, what is the magnitude of a force? It is given by QVB sine theta, right? When theta is equal to 0, what happens to the force? Force becomes a 0, right? force becomes a 0. Hence, the charged particle move in a straight path, okay? If there is no force acting on it, and the charge is moving in a parallel to the magnetic field, it will move in a same direction that do not change the direction of a charged particle, okay? There is no force acting on that charged particle due to magnetic field because of angle, okay? Now, path, if you see, the charged particle move in a straight path, okay? Straight path, straight line motion. We can consider it as a straight path or straight line motion. Got it? Now, projected anti-parallel means this is the magnetic field and this is a motion of a charged particle. So, opposite in direction. The charged particle is moving opposite to the direction of a magnetic field. In that situation, what will happen? So, that means magnetic field and velocity, motion of a charged particle, anti-parallel. Anti-parallel means what is the angle between them? Yes, what is the angle between them? Theta is equal to 180 degree, right? Theta is equal to 180 degree. Right? Now, next one. So again by the formula, F is equal to QVB sine theta. Now theta is equal to 180 degree. Again, F is equal to 0. Sine 0, 0. Sine 90, 1. Sine 180, again 0. Sine 360, it is the 1 again. Okay? Now, so again here, straight path. Okay? Again, the charged particle move in a straight path. No force acting on it. So the question may arise like this. When the force on a charged particle moving in a magnetic field will be 0. There are 3 cases. One, charge is at rest. Velocity is 0. Second one, the magnetic field as well as a motion of a charged particle parallel to each other. And the third one, the motion of a charged particle and magnetic field anti-parallel. So in all these 3 cases, the force on a charged particle is 0. Okay? Yes? Now, next one. Projection of a charged particle into magnetic field perpendicularly. Perpendicular means here, let's consider inward magnetic field, okay? I hope you know that as symbols, okay? This cross indicates inward magnetic field, okay? Inward means into the plane. Inward magnetic field. Inward magnetic field, and dot indicates outward magnetic field. Outward magnetic field. Got it? Okay. Now here we have an inward magnetic field, and here a charged particle is thrown, okay? Charged particle is thrown. The force acting on this, okay? Charged particle, the force acting on this particle, it is a downward in direction. Downward in direction means perpendicular to each other, right? So, when the charge, propagated in a magnetic field, what happens when it is a perpendicular to magnetic field? The path will be circular path, okay? Circular path. So, path will be circular path, okay? And this is also a V, okay? And this is also V. This is also V. This is also V. And this is also V. And magnetic field is inward, okay? The force acting on a charged particle, we can find out using our right hand palm rule, okay? Right hand palm rule, Fleming's left hand rule, okay? We can use it, right? Ankit Thakur, good afternoon. Any questions? Okay, now, so this session will be CBSE. Main motto it is for CBSE students, okay? And it is also helpful for other board or other state students also, other state board students also, okay? Circular path, okay? Circular path. And if it is moving in a circular path, then what is the radius of a path? What is the radius of a path? What is the radius of a path? See, this force, okay, this force, centripetal force is equal to magnetic force, right? Centripetal force, it is given by mv square divided by r. That is equal to qvb sine theta. And you can see the angle between velocity as well as the magnetic field. Velocity, for example, at this particular point you see, velocity along x-axis, magnetic field into the plane. See, into the plane, it is a magnetic field, and along x-axis, it is a magnetic field inward, and velocity, it is along x-axis. What is the angle between them? It is a 90 degree, right? So sine 90 becomes, so here theta is equal to 90 degree. Sine 90 becomes, okay, sine 90 becomes mv square divided by r, okay, qvb. Sine theta becomes 1 now. So here you can observe v and 1v get cancelled. So remaining mv divided by r, that is equal to qb. And here we need a radius of a circular path, right? Radius of a circular path. Therefore, what is the value then? mv divided by qb. mv divided by qb. mv divided by qb. Now, next one. Angular velocity. Angular velocity, we know that linear velocity is related to angular velocity, that is a r omega, right? R omega. Now we have v, r we have, that is mv divided by qb, right? mv divided by qb. So substitute here mv divided by qb and omega. So here we can observe again v get cancelled. Omega, that is equal to qb divided by m. So here you need to know what is omega, that is angular velocity. And here time period, before, time period is given by, okay, omega, that is equal to 2 pi divided by t. But here they are asking time period. So 2 pi divided by omega, right? So 2 pi as it is. What is the value of omega? That is qb into m. So here you can find out, okay, here you can find out, I'll write here, time period, that is a 2 pi m divided by qb. Got it? So derivation, I'm doing it, okay? Derivation, I'm doing it. Every derivation, I'm doing it, okay? Momentum. So in terms of a momentum, if we consider P is equal to mv, okay? P is equal to mv, momentum, right? Momentum, it is the property of a particle, moving particle, okay? Yes. So I'm getting answers, Jaino, okay, Jaino and Gogita, and next one, okay, right. So here you can substitute a v value, right? V value you can substitute. So using this relation, you can rearrange the equation, okay? Rearrange the equation. I hope you can do it, okay? And momentum and energy relation, P is equal to under square root 2 km, okay? 2 mk, okay? 2 mk, kinetic energy, okay? In terms of a kinetic energy also, you can express it. But mainly, you please concentrate on radius as well as this time period, angular velocity. Got it? Okay, fine. Now, next one, vertical motion. See, projected, when a charged particle projected at an angle, parallel it is done, anti-parallel it is done, perpendicular also it is done. What if it is not parallel, if it is not anti-parallel, if it is not a perpendicular, there is only one way, at an angle, right? At an angle, we don't know. It can be greater than 0, less than 90 degree. So that particular angle, what will be the, okay, what will be the radius of circular path? So what happens to the path of this charged particle? Here you can see, when a charged particle thrown, okay, at a acute angle, okay, that is a certain angle theta, that is a certain angle theta. So here you can see theta, that is equal to, okay, and here it is a velocity. Fine. So when a charged particle thrown into a magnetic field, it behaves like a, as if it is moving a helical path. Helical path means if it is moving around, okay, we call it as a circular path, right? Circular path. If it is moving, straight line path. Helical path means it is a mix of a linear as well as a circular path. For example, it is moving like this, okay? It is moving like this. So if it is moving straight means straight line path. If it is making a circle means circular path. What it is doing means it is a mix of both linear as well as circular motion. It is moving like this. A spring, okay, as if it is the spring. Getting my point? Right? So that means here we have to find out both linear velocity as well as, circular, with respect to circular path as well as the linear path. Okay. Now, first of all, Radius of helical path. What is the formula? That is mv divided by qb, right? mv divided by qb, original formula. Now here, resolve this velocity, okay? Resolve this velocity. How to resolve this velocity? Along x-axis and along y-axis, okay? So this one I'll call it as a v perpendicular, and this one I'll call it as a v parallel, okay? So v perpendicular means, what happens to the value here? V perpendicular. So resolving, what you'll get, this one you get v cos theta, and this one v sin theta, right? V sin theta. Now substitute here, mv sin theta divided by qb. That's all, okay? And next one, horizontal motion. This is for circular motion. It is done, okay? Vertical motion. Vertical motion means it is moving like this, okay? Vertical motion, moving like this. Vertical motion. Next one, the path. First of all, what is the path of this one? Helical, okay? Helical. When projected at an angle theta, okay, path will be helical. Helical, okay? Now, next one you see, horizontal motion. Horizontal motion. It is not a straight line, right? It is covering some circle also. Therefore, here what you have to do, it makes one complete circle, right? Complete circle means, can I consider it as a one oscillation? If I consider one oscillation, Deepalijin, am I late, sir? No. Okay? No. Fine. So here, let's consider horizontal motion if we consider, okay? Here you have to find out a pitch, okay? Pitch. Horizontal motion, it is done. Okay? What is the radius of this horizontal motion? That is done. mv sin theta divided by qb. And what about horizontal motion? Vertical motion, it is done. What about horizontal motion? Here you need to find out. So horizontal motion of this helical path, we call it as a pitch. Okay? So here, pitch is nothing but a linear distance traveled by the charged particle in a revolution, means one circle in a one time period along external magnetic field. External magnetic field direction. In the same direction of magnetic field, it is moving, right? Because it is a charged particle. If it is a negative charged particle, opposite direction, right? So pitch, that is given by v parallel into time period, right? What are v parallel? That is a v cos theta time period. How much it is? 2 pi m divided by qb. This is the relation between a pitch, radius of a circle, okay? Now let's move on to the next concept. Important rules, okay? Right hand clasp rule or else right hand thumb rule. Just remember right hand thumb rule. That is the Maxwell's right hand thumb rule. What does it give? If I consider this is a current carrying wire, okay? Let's assume that it is a current carrying conductor. If I hold this current carrying conductor in my hand, okay? Now, this thumb indicates the direction of a current, okay? This thumb indicates the direction of current, and encircled fingers indicates the direction of a magnetic field, okay? Direction of a magnetic field. For example, if my curls, okay, curled fingers, if it is going inward, okay, inward, the magnetic field indicates inward in direction. If direction of a magnetic field, that is a encircled finger, if it is a directing upward, means it is outgoing a magnetic field. Got it? Okay. Atish Sharma, sir, I'm in 9th, but I enjoy. Okay, from you. Thank you, studying, enjoying from you. Yeah, welcome. Okay, now, getting my point? Is it clear? So this is a Maxwell's right hand thumb rule. This is Maxwell's right hand thumb rule. Maxwell's right hand thumb rule. And here Maxwell's right-handed cork screw rule. Okay, it is a screw rule. What do we have to do it? See, just when we have a vector quantities, like we had a force, right? So force is given by Q, V vector cross B vector. So in that particular situation, what you have to do is, this is the direction of a magnetic field and this one indicates the direction of velocity, or else vice versa you can consider, okay? That is the screw rule. What does it say? It says that if right-handed cork screw is rotated such that, okay, rotates the tip, advance the direction of electric current, and the direction in which head of the screw is rotated gives the direction of a magnetic field. So in both the cases, we are finding direction of magnetic field only. Right hand thumb rule, another one is screw rule. Got it? Okay. Now let's move on to the next one. Before that, just mark this one, Maxwell's right hand thumb rule, and it is a clasp rule. And this is cork screw rule, and the first one, right hand thumb rule. Fleming's left hand rule. What is the use of this? This indicates, okay, this indicates Fleming's left hand rule. Okay, what you have to do is open all the fingers, okay, and close these two, okay, last two fingers, and open like this. Each finger should be perpendicular to each other. Okay, yes, yes. Father, mother, child. Very good. Father, mother, child. Or else FBI. Okay, force, magnetic field, and current also. This gives the relation between force, magnetic field, and current. Means when a current carrying conductor placed in a magnetic field, it experiences a force, right? And what is the direction of force? Which can be detected by, or else which can be given by Fleming's left hand rule. So in this case, thumb indicates a force, M indicates a magnetic field, and I indicates current. Okay, getting my point? Yes, done. So this is the Fleming's left hand rule. So this gives you force, okay, direction of force. This law or rule gives you direction of force on a conductor, acting on a conductor. If the first three fingers of the left hand are stretched in three mutual perpendicular directions such that the fourth finger, okay, forefinger is along the direction of a magnetic field, middle finger is along the direction of a velocity of the particle, then thumb gives you direction of magnetic force. Okay, done. Next, represent the direction of a magnetic field into the plane of the paper, emerging out of the plane of the paper for an observer face in the plane of a paper. See, just see inward. For example, this is the paper, okay? I am the observer. If the magnetic field going inward into the plane, cross, okay, this will be the cross. This will be the cross, okay? If magnetic field lines coming out, emerging for observer, okay, I am the observer. If the magnetic field coming out of the plane, we can say that it is a dot. Dot indicates emerging out of the plane. Got it? Okay. Now, so this is the easiest way to remember. Okay. Now, let's move on to the next question. Find the magnitude of a force experienced by, try to do it, okay? Try to do it. Experienced by an electron moving with a velocity 0.5 into 10 power 7 meter per second in a magnetic field of a strength 0.5 10 power minus 2 Tesla, making an angle 30 degree with the magnetic field. What is the force it is given by? Force it is given by QVB sine theta. Okay. Then what is the force they are asking, right? And what they are asking, find the magnitude of the force experienced. Magnitude we need to find out. Okay. Now, what is the Q value? Q. The magnitude of electron. Okay, electron they have given. Therefore, 1.6 into 10 power minus 19 into velocity, that is 0.5 into 10 power 7 into B, magnetic field, that is 0.5 into 10 power minus 2 into angle sine 30. Okay, angle sine 30. So force that is equal to, okay, group all the values. Okay, so here 1.6, this is 0.5, I can write as 1 by 2, this is also 1 by 2, and sine 30, that is also 1 by 2. And here you can see 10 power minus 19 and 10 power plus 7 minus 2. How much it is? Minus 12 and 14. So into 10 power minus 14. Okay. So simplify and get the answer. Okay. Simplify and get the answer. It is up to you, and comment your answer. Okay. Now let's move on to the next question. Okay. 12.5K. I don't know what you guys are talking. Okay. Now, Lorentz force. Lorentz force means when an electric charge, okay, it is projected into both electric field and magnetic field, then what is the force experienced by it? Okay, that force, that net force, we are calling it as a Lorentz force. Okay, yes, 0.2 into 10 power minus 14. Zai now, very good, ma. force experienced by a moving charged particle in a region containing both electric and magnetic field is called Lorentz force. And you remember force exerted by electric field, okay? That is a Q into E, right? And magnetic field, okay? Magnetic field, it is given by Q into, okay, V into B. And net force, okay, net force that is equal to force due to electric field and force due to magnetic field, okay? Now, here you can write Q into E plus Q into V vector into B vector, or finally you can express this net magnetic force, okay, net magnetic force, not a net magnetic, it is a net force due to magnetic as well as electric field, okay? Now, I'm taking Q outside, okay, E vector plus V vector into B vector. Getting a point? Okay. Are you getting my point? Is that clear? Okay. So this is the values. Okay. Fine. I hope it is clear. Now, Lorentz force depends on. Look at the values. Okay. Look at the values you'll be getting to know. Okay. First one, magnet of a charge, velocity, magnetic field, and electric field. All this parameter depends on a Lorentz force. Okay. Means the force experienced by a charge. Okay. Now, so first one you can see strength of electric field, that is a E vector, and all these are vector quantities, right? Okay. Now this is also vector quantity. Now second one, magnet of a charge, that is a Q, and component of velocity perpendicular to the magnetic field. Okay, that is nothing but a cross. Okay, V cross B. This is a V cross B. This is a V cross B. Got it? Okay, easy. No worries, easy. The fourth one, a magnet of the magnetic field. Magnet of the magnetic field means that is a B. Okay, simple. Dependent factors. Now, so somebody is crying. I'll check out. Help sir, कल physics exam है, कुछ पढ़ाई नहीं, बहुत रोया हूँ. Don't cry, okay? Learn. Okay, still you have a time, okay? At least you prepare for at least 4 chapters. 4 chapters. Okay, definitely you'll clear your exam. Don't worry, don't cry, okay? Be happy. Okay. Sir, what is the magnetic and magnetic field? Magnet, it is an object. Magnetic field, it is a region, okay? Vedant Singh, I think it is clear for you, okay? Okay. Fine. I may not, respond continuously. Don't mind, okay? Now, let's move on to the Biot-Savart's law. Biot-Savart's law statement, okay? What does it says, okay? Statement, everybody knows that, okay? So magnetic field dB is directly proportional to I, directly proportional to elemental current, okay, dl, and inversely proportional to r square, and directly proportional to the sine theta, right? So all these are statement of Biot-Savart's law, and here you can note down directly proportional to the strength of the current I, and directly proportional to the length of current element, and the third one directly proportional to the sine theta, and directly proportional to the where you need to find out a magnetic field, okay, right? This is a magnetic field, it is given by dB, small dB, okay? Now, it is given by the first one directly proportional. After eliminating this proportional, we have this mu naught divided by 4 pi into ideal sine theta divided by r square. And when will be, it is a maximum, okay? When this dB will be maximum, okay? When this dB will be maximum, theta is equal to 90 degree, okay? Theta is equal to 90 degree. That is a maximum condition, okay? Maximum condition. If a theta is equal to 0, then it is a minimum, okay? Got it? And this is where we are finding a magnet. At this point, using right hand thumb rule, okay, this is a current carrying element. Here I am considering element and the current carrying, and that particular point, how my fingers are acting into the plane, means a cross. And if I want to calculate a magnetic field at this point, what happens? It is out of the plane. So here a dot. Getting your point? Here this side is the dot and this side is a cross. Got it? Okay, this is a magnetic field. Fine. Now, let's move on to the next slide. Vector form. You go through it. It is a very easy one. Just to go through it. Already we have learned, because this electric charges and fields and magnetism similar, almost similar. Where we are talking about electric field, but here we are talking about only magnetic field. Okay. Yes. Fine. Now let's move on to the when is the magnetic field at a point due to current element. Maximum and minimum. Maximum and minimum. So maximum and minimum. Maximum it is for theta is equal to 90 degree and minimum for theta is equal to 0 degree. Already I have discussed in that. Okay. Fine. Now. So let's move on to the next concept. What is the current element? So current element nothing but a small part of, no, if I consider this is a particular length, okay, length L, total length L. If I want to calculate a magnetic field due to only small part of this length, okay, small part of this length carrying current. So that part we are calling it as a elemental current. Got it? Okay. Yes, Tulsidas. Okay. See, general formula this much, right? This much. General formula this much. So when you are expressing in a vector form, no, just add this r vector. I mean r cap, unit vector, okay? R cap means unit vector. Got it? So what you have to do, just you add r cap, that is a unit vector. So that's all. Okay, only this much. Just adding r cap gives the direction of a magnetic field. Nothing else. Got it? Okay, now. So here they have given the magnetic field, okay, direction of the direction of magnetic field perpendicular to the plane containing elemental current element and that point. Now, what is current element? Already just now I have explained. And here ampere current unit is ampere meter, because along with the length we are considering. Okay. Yes. Any doubt? Do you have any doubt till now? Yes. Yes. Do you have any questions? If you have any questions, you can ask me. Okay. Okay. Don't worry about waves, okay? Who is, I want to say one statement, okay? That is a very, mind booster. Everybody will start early, but only if we can last till end, right? So if you are preparing for a board exam, let's do it. Let's do it. Let's do it and make it happen. And later on, you should not cry. Like, I have not did that, have not done that, okay? You should not have all these regrets. So this is the right time to study and explore your life, professional careers, okay? Got it? So everybody will start early, but nobody will last for till end. Okay, not forever, till end. At least we started in the morning, that is 11. Can't you stay till 8 or 9? Throughout the year, you have learned, okay, I know. Throughout the year, you have learned so many things. Okay, not only physics, so many things you have learned. Spend this particular time, only one day, and you know where you are standing in your preparation. Okay? Right? Yes. Shinchan, thank you so much. Shakib, I don't know if I am pronouncing your name correctly. If I pronounce it wrong, okay, don't mind it, okay? Okay. So there is no CGS unit of a current, okay, Ankit? Right now, I have not come across that is CGS unit of current, okay? I have learned that, ampere only. Okay, fine. Thank you so much. Okay, fine. Please take my name. Already have done that, okay? Yes, sir, we can. I am there, okay? Do it, guys, do it. Don't lose hope, okay? Don't lose confidence. Bear with me. After this, you'll be enjoying. After this, chapter, next chapter you see how nice it will be. This is also very good. I'm not saying it is, not that much important. It is very important. So that is the reason I'm, teaching very slowly, make you understand. I can just, read and I can change the slides, right? I'm not doing that because you need to understand the concepts. That is my motto. Okay. Yes, SKY creations. Yes. Okay, sir, where to use SI units? Wherever it is asked, then you have to use the SI units. Okay. Fine, fine. Let's get into the topic. And what is the direction of the magnetic field due to current element? See, perpendicular to the plane containing the point and the current element means this part. Alright. This part. Okay. This part. Or else this part. Got it? Now. Yes. Magnetic field on the axis of a circular current carrying loop. Okay. Current carrying loop. Okay. So generally, by Biot-Savart's law, what is the magnetic field? That is a dB, that is equal to mu naught divided by 4 pi, right? IDL divided by R square sine theta. This is the original formula. Am I right? So this derivation is very important. Okay. Archana, my name is Ashok. Okay. Ashok SK. Now. So current carrying loop. So direction of current carrying loop this way, okay? So it is moving, okay? So what is the direction? Use this right hand thumb rule, okay? Use this right hand thumb rule, okay? Use this right hand thumb rule. At this point, I want to calculate a magnetic field, okay? What is the magnetic field at this point? Okay, what is the magnetic field? Not a dB, that is a B. What is the magnetic field at this point P? Now, at this point P, let's mark our reference points, okay? Reference points. Okay. So due to this small elemental current, okay, due to this small elemental current, so direction of a current in this way and direction of elemental length in this way. You see, it is a downward, right? It is downward. And at this particular point, okay, this is the direction of elemental current and the current will be in this direction. You see here also 90 degree. So angle it is clear, okay? Angle it is clear, okay? Now, so at this point, again, distance from here to here, I have a marked, okay? Now, this is the radius of a loop and this is X and this is R, okay? So due to this elemental current, okay, due to this elemental current, okay, due to this elemental current, so at this point, okay, at this point, what is the direction of a magnetic field? What is the direction? Upward, okay? No, it is downward. So this is downward and this is ulta, this direction, right? Due to this direction, okay? Is it clear? Using which one? And this one. Okay. I hope it is clear for you how to find the direction of a magnetic field. Use right hand rule, okay? Mr. Sarthak, okay. Ram, okay, fine. Now, you see, this is angle, okay? This is the angle. This is the angle. This is also angle. So this is the components. Let's resolve this components, okay? Let's resolve this components. One it is along y-axis, another one it is along y-axis. And here, due to upper elemental current and lower elemental current, okay? So here if you consider this is a theta means this side, okay, this side and this side. Here you see this side will be theta and here cos. This side is a cos and this side cos theta and this side cos theta and this side sin theta, right? Sin theta. Fine. dB sin theta because elemental current, right? dB. Now here you can see this side and this side get cancelled, right? Got it? Okay. Now, after this, okay. Now, after this, magnetic field, sin theta you have, right? Sin theta. Then what about the sin theta? Sin theta is nothing but perpendicular divided by hypotenuse. What is perpendicular? R. And hypotenuse, small letter r, right? Sin theta value, we got it. Okay. Now, here you see both the side, okay? both the side we have a dB, 2 elemental current. Therefore, net magnetic moment, okay, net magnetic field at this point P, okay, net magnetic field at this point P, that is mu naught divided by 4 pi IDL divided by R square. And initially it has become 0, okay, means sine 90 becomes 1, okay. Now, here what you have to do is ideal, after this ideal, add sine theta, okay, add sine theta. dB, that is dB already it is done, sine theta, okay, sine theta, right? What about the sine theta here? If you want to remove B, means a dB, what you have to do? dB, right? Use the same. dB means already you have used it, right? dB, already you have used it. So this theta initially 90 degree, it is eliminated, ignore it, okay? Now net magnetic field, that is, okay, this is a 2, this is a 2 dB. Substitute the values. 2 dB, 2, what are the values? 2 mu naught divided by 4 pi IDL R square into sine theta, right? And B is equal to 2 is common, mu naught common, 4 pi is common, I divided by R square and sine theta. Sine theta is also common, right? Constant, and only variable quantity, that is a DL. Sine theta also we know that, right? That is a 2 mu naught I divided by 4 pi R square. Sine theta is given by R divided by R, right? R divided by R. So now, so sine theta it is done. And what about this total length of the circular loop? That is a 2 pi R, right? 2 pi R, that is a capital letter R. Capital letter R, okay? Now, you see, here 2 pi, here 2 pi, gone, okay? So next one, simplification. Now here you can use B is equal to mu naught I R square divided by 2 pi is there? No. 2, what is the value of R? Here R, can I write it as a R square plus X square? 1 by 2, okay? R cube it is there, R cube. That means R square plus X square power 3 by 2, okay? So this is about, 2 pi it should be there, right? 2 pi R, right? Okay, now here 2 pi get cancelled. So finally, for n turns, okay, mu naught Ni R square divided by 2R, okay, 2R square plus X square 3 by 2. This is the derivation, okay? I hope it is clear. Got it? Got it? Okay, now let's move on to the next topic. Ampere Circuit Law. So statement, explain the Ampere Circuit Law, okay? Yes. Okay. They also clear? 2 also get cancelled. Now, state and explain Ampere Circuit Law. Statement, the integral value of the magnetic field over a closed loop, okay, closed path around the conductor is equal to mu naught times the net current in the conductor. What does it mean? So B dl mu naught I, okay? So here we have a with respect to current, okay? We have a with respect to current, B dl is equal to mu naught I. Got it? Jainav got it? Tulsidas, okay. I guess I have cancelled it, okay? I've cancelled it. Okay, fine. Now, let's move on to the next question, that is the derived expression of a magnetic, expression for a magnitude of a magnetic field at a point around the straight conductor. So, by Ampere Circuit Law, that is a BDL, okay, mu naught I. This is the current carrying conductor, okay? This is the current carrying conductor and this is the loop. And here we need to find out what is the expression of a magnetic field? That means B value we need to calculate. Okay. Now, here you can see BDL can be written as BDL cos theta mu naught I, right? That is current carrying. This cos theta, that is a 90 degree, 0 degree. Why? Say length current as well as, okay, this length current as well as a magnetic field. Magnetic field inward, length direct. So it is a 90 degree. It is a 0 degree. Along the same line, right? Length as well as, for example, if I consider this is the length and this is also magnetic field direction. So what is the angle? That is the 0, cos 0, right? Cos 0, it is a 1. So remaining part, that is a BDL, that is equal to mu naught I. So here B, I'll take it outside, okay? And DL, that is equal to mu naught I. And B is equal to, what is the area? It looks like a loop, nothing but a circle. So total length, that is a 2 pi r, that is equal to mu naught I. So finally, you will be having a magnetic field mu naught I divided by 2 pi r. This is the relation. Mu naught I divided by 2 pi r, or else multiply and divide by 2. 2 mu naught I divided by 4 pi r. Okay, 4 pi r. So this one, to make it as a mu naught divided by 4 pi r. Both are correct, okay? Come on, guys. So what is going on in the comment section? Yes? Please concentrate. Don't disturb. I mean, it is a kind request. Don't disturb others, okay? Fine. Now, let's move on to the next question. What is solenoid? So solenoid is an insulated copper wire. This is also we have learned in our foundation level. Here what? Yes, a DL, total length, no? Total length. This a DL. See, this a DL means total length. Total length. What is the total length? What is the total length? It is a circle, right? It is the circumference of a circular path. I think you can consider it as a circumference of a circle. What is the answer? That is the 2 pi r, right? Circumference 2 pi r. Area pi r square. Got it? Okay. Now, next one. So here you need to remember field. That is a mu naught Ni. No derivation for this solenoid. Okay, no derivation for the solenoid. Just you need to go through a value of this, okay? And where N is number of turns per unit length. Number of turns per unit length. Got it? Okay. Yes. Okay. Now let's move on to the next concept. That is the factors on which the magnetic field at a point inside the solenoid depends. So you see, first, if you remember the formula, that is a B mu naught Ni, and this also can be written as mu naught N divided by L into I, means number of turns per unit length, okay, into I. So first one, number of turns, that is the capital letter N, strength of the current, that is the I, and the permeability of a medium inside the solenoid, that is this parameter, mu naught. Okay, got it? Okay, now let's move on to the next question. Next question, a rate of, force on a current carrying conductor. It is very, very important. Parallel. See, 5 marks in your hand. Got it? Okay, 5 marks in your hand. How? For example, electrons, if I consider, okay, if I consider electrons, moving downward, motion, okay, motion downward, motion of electron downward. And what is the direction of a current? Direction of a current will be opposite, right? Opposite of the flow of electron. That we know, basic of physics law, right? So now current is upward and a magnetic field inward in direction, that is into the plane. Now what you have to do? Use the right hand palm rule, okay? Use the right hand palm rule. So here, this finger indicates the direction of a current and this fingers indicates direction of a magnetic field, and this palm indicates a force acting on a current carrying conductor in a magnetic field. One more time, this thumb indicates a current, direction of current, and this fingers indicates the direction of a magnetic field, and this palm indicates the direction of force acting on it. Now, direction of a current, thumb, direction of magnetic field, fingers, and this one indicates direction of a force. That means direction of a force towards the left hand side. Got it? What if I consider current downward in direction? Current is downward in direction, and magnetic field still it is inward in direction, into the plane. This is the direction of a current. So magnetic field direction and current direction, and this is the direction of a force, and this is the direction of force, that is F. Okay, this is a force, that is also force acting on a current carrying conductor. Or else you can use a Fleming's left hand rule. You will be facing difficulty while holding like this. Okay, so use this right hand palm rule only. Got it? Okay. Now next one, force on a current carrying conductor. So already we know that a force on a current carrying conductor. Okay. So electrons, for example, force on one electron. Force on one electron. Force on one electron, that is given by QVB sine theta, right? QVB sine theta. Force on all electrons, okay? The formula will become QVB sine theta into N, okay? Number of electrons, okay? Now, charge density, number of particles per unit volume, and N is nothing but N into V. That is a volume, okay? That is a volume. N can be written as, okay, N can be written as N into A into length of the conductor. So here if I consider, okay, here if I consider, this is the length of the conductor, okay? This is the length of the conductor, and this is the area of a cross section, and this is the area of a cross section. Okay, this is the length. This is the length, and the volume of this conductor will be A into L, right? In the same way, here I am doing it. So force on all the conductor, electrons in a conductor. So what is the value of N? That is N into A into L QVB sine theta. Okay, QVB sine theta. And what I am doing is just rearranging the equation. What I am doing, so in place of N as it is N, in place of Q as it is Q, in place of V, that is the velocity, okay, here V means the velocity, and in place of A as it is A, okay, done, and remaining B sine theta, okay. Now, do you remember drift current, drift velocity, that is NEVDA. This is the same form, right? N as it is, in place of an electron, here a charge Q, in place of drift velocity V, in place of area as it is area. Therefore, I can replace this IB. And one more thing, where is that L? L, I forgot it, okay? Here L. I'll take it out, okay? IBL sine theta. So, here simplification, Bill sine theta, okay? Make it Bill sine theta. Bill sine theta. So, in vector form, we can consider it as a I, L into B. L into B. So maximum and minimum, if you want to calculate maximum and minimum, so what should be the theta value? Theta value should be 90 degree. Means the direction of length. For example, this is the length means, okay, current carrying conductor along the length. So length of the wire, how do you consider? Direction of a flow of current, okay. For example, length is moving, means current flowing upward. That is the direction of a length, okay. And that inward in direction, that is a magnetic field inward, okay, magnetic field inward, and the current is moving upward. Current is moving upward. So this is a current, okay, this is the current. So what is the direction of a force? This force will be this one, okay, this force will be this one. Got it? Okay, this is the force. I hope it is clear, okay. And maximum force, okay, this is the minimum force, okay, this is for minimum force. Theta should be 0. Theta should be 0. What does it mean? Along the, okay, along length of the conductor is along a magnetic field. there is no force acting on it. Okay, and for maximum force, okay, for maximum force, theta should be 90 degree. Theta should be 90 degree. Got it? Okay. So here force will be 0. Here force will be maximum. Got it? Now, next one. Force between two current carrying conductor, parallel conductor. Okay, current carrying parallel conductor. So first I'll consider one wire. Okay. So current carrying in this way. Okay, current is carrying in this particular direction. Current carrying in this particular direction, I1. Okay, current carrying in a conductor 1, that is a I1. So due to this, magnetic field will be produced, right? Current carrying conductor produces a magnetic field around it. So what is the direction of a magnetic field around it? Here, this side it will be inward in direction, right? Inward in direction. What about this side? Outward in direction. Use this right hand curl rule, okay? Right hand curl rule. So this side it is a dot, okay? So now, what is the magnetic field at this point? It is a, all right, 2 mu naught I divided by 4 pi r. You'll be asking, sir, where did we get that value? Current carrying conductor, okay? I'll show you. Yes. 2 mu naught I divided by 4 pi r. 2 mu naught I divided by 4 pi r, okay? Mu naught divided by 4 pi r. Okay, now, here magnetic field is produced, okay? Now, what I will do is, I'll consider same conductor, I'll place in this particular place, okay? I'll write this one aside, okay? So magnetic field, that is a B 2 mu naught I divided by, this is I1, right? Due to magnetic field due to current 1, 4 pi r. And the separation between, okay, separation between parallel conductor, that is a r. Got it? Okay. Now, second case. Now I have replaced another conductor at this magnetic field. This is also carrying a current in the same direction, that is I2. That is I2. So first force on this conductor 2. Okay, force on this conductor 2. Force on 2 due to 1. Bill sin theta. Okay, Bill sin theta. That is the magnetic field due to 1. Current carrying 1. Bill I1. Okay, this is current carrying conductor 2. Bill sin theta. Length is same, therefore I am writing as it is. Sin theta. Okay, this is 1. So here I'll be writing F21. F21, that is given by B1 I2 L sin theta, right? What is B1 value? F21 B1, that is a 2 mu naught I1, right? I1 divided by 4 pi r into I2 L sin theta. Okay, now further simplification, F21, here L per unit length I'll be considering, because it is the infinite straight wire, right? I'll be considering for a finite length, okay? Finite length if I consider, that is a 2 mu naught I1 I2 divided by 4 pi r. And what about theta? Theta is angle between length and magnetic field, okay? If you see, theta is 90 degree, right? 90 degree. So this entire term becomes 1, okay? Now first case it is done. Now just imagine it is not there, okay? This wire, it is not there. And it is a current carrying conductor, okay? At this point, okay, what is the direction? At this point, okay, it is the outward in direction, right? Outward in direction, right? Here a magnetic field is there, that is due to 2, that is a mu naught, all right? 2 mu naught I2 divided by 4 pi r, okay? Now, so now I'm placing this, particular conductor in this particular magnetic field, okay? It experiences a force. That means a force on 2 due to conductor 2. So that is given by Bill 2, that is a magnetic field 2, I2, that is I1, right? Current carrying I1, and the length Sin theta already it is a theta is 90 degree, right? Theta is 90 degree. Now, so just to replace, okay, just to replace the values, F12, okay, F12, that is equal to B2 value, that is a 2 mu naught I2 divided by 4 pi r and I1 into L. So rearrange that equation, F12 2 mu naught I1 I2 divided by 4 pi r per unit length. Compare equation 1 and 2. Compare equation 1 and 2. Okay, both are same, means both are equal. The magnetic field as well as the force both are equal in magnitude. Okay, see, force per unit length, 2 mu naught I1 I2 divided by 4 pi r, 2 mu naught I1 I2 divided by 4 pi r. Okay, so this is what, magnetic force acting between two parallel conductor carrying a current. Got it? Okay, now let's move on to the next one. Force between a two conductor carrying parallel conductors. See, in this particular section, that is the concept, here we have two questions. Okay, what is the nature of a force? What is the nature of a force between these two parallel conductor carrying a current? Okay, if a current is in the same direction, I1 and I2, if both are in the same direction, then there will be force of attraction. You see, if the current in the wires are in the same direction, then wires attract each other, right? What if one conductor carrying current upward in direction, another conductor carrying current downward in direction, opposite in direction? Now, the wires repel each other. This is the nature of the force acting between two parallel conductor carrying a current. Got it? Okay. Now, let's move on to the next one. Definition, you go through it. Okay. This definition is very important. Next. Magnetic moment. The magnetic moment of a current loop, okay, is a vector whose magnitude is equal to, I as well as area, means the magnitude of a current and area of a loop. Okay, that is the magnetic moment. Got it? Definition wise, how do you represent this one? The magnetic moment of a current loop is a vector whose magnitude is equal to product of area of the loop times. Means, what does it mean? So this is area, okay? This is the area. Okay, fine. This is the area. This is the area. And current carrying, okay? Current is carrying. Okay, this is the current carrying loop. And this is the magnetic moment. So this magnetic moment can be represented by capital letter or small letter, okay? Small letter or capital letter. Now, see, this is a magnetic moment, and this magnetic moment, it is given by I into A. For one loop. For n loop, nothing but for a coil, it will be Ni into A. Ni into A. Got it? Okay. Are you guys understanding? Yes, Manu, he is answering. Okay. Okay. Very good. Go Geeta, what happened? Done. Okay. Fine. Okay. Now, here you can write, this is for N, I, A, and this is for one loop. One loop, that is I into A. And what is the unit? What is the unit of a current? Ampere. What is the unit of a area? Meter square. That is ampere meter square. Okay. N is the number of turns. Quantity. It is a vector quantity. Okay. It has a direction as well as a magnitude. It is a vector quantity. Okay. Got it? Okay. Now, let's move on to the next concept. That is the torque on a current carrying coil. Okay. So, I hope this torque, already we have done this. Okay. So, I'll be leaving it to you. So, where torque in a electric field, what we have learned? PE sine theta, right? PE sine theta. Here what we need to do is replace P with a magnetic moment, that is the M, electric field with a B, and sine theta. Same procedure you follow. Same procedure. And vector method, okay, vector, in terms of a vector, that is a m cross b, m cross b, okay, m cross b. Got it? Okay. Yes. Yes, guys. Is it clear? Same procedure. See here also, in place of electric field, here we have a magnetic field. See, just look at here. In place of electric field, here magnetic field. In place of a dipole, here we have a magnetic moment. Where electric dipole moment, here a magnetic dipole moment. That's all, okay? Yes, Atesh Sharma, Dinesh Tanwar, and Jainav. Yes, sir. Yes, yes, boys, come on, come on. Okay, now let's move on to the next concept, that is, when is the torque on a current loop in magnetic field? Maxima and minimum. See, first formula, just remember the formula. So torque, it is given by mb sine theta. So completely, this m as well as b, it is a constant. So that means it is depends on only theta, right? It depends on only theta. So if theta is equal to 0, okay, if theta is equal to 0, torque will be 0, right? Torque will be 0. If theta is equal to 90 degree, torque will be mb. That is a maximum, right? So this is minimum and this is the maximum. Got it? Okay, got it. Now, let's move on to the next concept. What is a moving coil galvanometer? Mention a principle behind it. So, it is an instrument used to measure low electric currents. It works on the principle that current carrying coil placed in the magnetic field, okay, experience a torque. Like last topic, that is the torque. The based on torque only it will work out, okay. Now here you can see the lines, okay. All these lines we call it as a radial magnetic field lines, okay, radial magnetic field lines. Due to that sine theta component there, no, that becomes a 1. Theta value becomes a 90 degree because the magnetic moment as well as a magnetic field becomes a 90 degree, okay. Current carrying loop, okay, current carrying loop, if I consider, the sine theta value becomes a 1. Getting your point? That is the importance of a radial magnetic field lines. Here, this side, you can see radial magnetic field lines. Okay, and here also radial magnetic field lines. Got it? South and north pole, and magnetic field lines starts from south and move towards the north. Okay. Now, here there is a pointer. Are you able to see this? Here a pointer, okay? Pointer. It is a pointer. So we are going to talk about this pointer itself. Okay? Pointer itself. Okay? Yes. Very good, very good, very good. Okay? Now, so generally this torque, it is given by mb sine theta. Right? mb sine theta. And this mb, okay, this mb, we can write it as a nia b sine theta. Now here you can see this loop as well as a magnetic field lines. What is the theta value? 90 degree. So therefore, torque acting on that coil, okay, this is the coil, okay, torque acting on the coil, okay, torque acting on the coil, that is NIAB. Okay. Now, after rotating this coil, what will happen? There is a, where is that? One second, pointer, it is there. One second. Yes, phosphorus bronze. Phosphorus bronze strip will be there. What will happen? It will be rotating, right? For example, spring. Okay, when you tight it, what will happen if you leave it? It will re-rotate. Means counter torque will be produced. In the same way, phosphorus bronze, recounter, or else what do you call it as? Opposite way, it will produce a torque on this coil. Okay, so that you can see through this. Okay, so sine theta, already I have written this one. Okay, mb sine theta, and the torque in the coil, that will be given by nb. Okay, NBIA. Got it? And next one, a coil rotates. It opposes a phosphorus bronze. Okay, phosphorus bronze. Now, at equilibrium, okay, at equilibrium, torque at equilibrium, torque produced in the coil, that will be equal to counter torque by the phosphorus branch. Counter torque by the phosphorus branch. So we know that this coil, okay, due to coil, we know that torque is NBIA. And here, this is due to C phi, where is C is the torsional constant, okay, where this phi is the angle of rotation by the pointer, okay. Now, so we are using the same phenomena in this particular case. You can see NBI is equal to C phi, torsional constant, angle rotated by the pointer. Now, see, first one, here you need I. What you'll do? C phi divided by NBA. Okay. Now, what I will do, just rearrange it again. I divided by phi, that is equal to C divided by NBA. C divided by NBA. Got it? C divided by NBA. Okay. Now, this one we call it as a current sensitivity of a galvanometer. Current sensitivity of a galvanometer. Now, in the same way, we have a current sensitivity, definition wise, angle rotated by a pointer per unit a current in a galvanometer. Okay. So that will be given by, okay, this is a phi, right? Definition wise, the angle rotated by a pointer per unit current. Per unit current means a reciprocal we have to consider. Reciprocal. So reciprocal means that is pointer angle rotated by current, that is equal to, okay, that is equal to NBA divided by C. NBA divided by C. Okay. This is the current sensitivity of a galvanometer. Unit will be, okay, ampere per radian. Ampere per radian. Ampere per radian. Okay. Now, current sensitivity of a moving coil galvanometer depends on, see a formula, that is N is number of turns, A means area, and B is the magnetic field, and C is torsional constant of the spring. Simple. Okay. Next one. Conversion of galvanometer to ammeter. So, directly we cannot use galvanometer in a circuit. Reason, this galvanometer has, actually, galvanometer should measure current, right? Should measure current. What happens is, when you connect this galvanometer in the circuit, what happens? It has a resistance. It has a resistance. So when the circuit has a resistance, the proper current cannot be measured. So that is the reason this galvanometer converted to ammeter. So ammeter has a very low resistance, hence it can measure a current through it properly. Got it? Okay. Now, so this resistor connected parallel to the galvanometer. Okay, this is the galvanometer, and resistance of a galvanometer, it is given by Rg. Okay, so the current is moved, and here current is I, and this side Ig is moved, and remaining current, that is I minus Ig. Okay, so total current, it is from the source, current flowing through this entire circuit. So this one we are calling it as a galvanometer, and this one, it is a external resistor, we call it as a shunt resistor. Okay, small resistance we are connecting it, so that what happens, the minimum current will be flowing through the ammeter. Getting your point? Okay. Now, here you see this RS, okay, this RS shunt resistor. Now, voltage is same across the terminal. Why it is same across the terminal? For example, if I consider this is A and this is B, okay, why it should have a same potential across the terminals? What is the reason behind it? Yes, what is the reason behind it? So here, because this resistor, see, resistance of a galvanometer and external resistor, that is a small resistor, shunt resistor, both are connected parallelly. Therefore, here you can consider parallel means the same voltage. Therefore, voltage external resistor, okay, that is a galvanometer resistor. So voltage same means galvanometer resistor. So here VI, that means IR total current, VG, that is IG total current. So IG and RG, that is equal to, and I minus IG into RS. Okay. So if you want shunt resistor, so you can do it IGRG. Okay. IGRG divided by I minus IG. Okay. So here VA, that is equal to VB. Okay. Same potential difference. Hence we can use this. So I'm writing one more time. Okay. I'm writing one more time. Please go through that. Shunt resistor. Okay, that is a small resistor connected across galvanometer, that is IG RG divided by I minus IG. Got it? Okay. This is the resistance we have to connect in a galvanometer with a parallel. Got it? So in a board examination, you'll be having a questions. How do you convert moving coil galvanometer make it a ammeter? So we have to convert that into ammeter. You have to connect a small resistance, that is a shunt resistance, parallelly. Got it? Okay. Now, in the same way, why is ammeter is always connected in a series with a circuit? Ammeter is always connected in a series because it has a low resistance. The introduction of an ammeter in the circuit will not appreciably alter the resistance, and hence the current in the circuit. Means proper readings can be taken. So next one, this galvanometer converted to voltmeter. How? Previously, we have converted to ammeter by changing, by connecting resistance parallelly. What if the resistor connected a series? What happens? The current, maximum current can flow through it, right? So here current will be same, but what happens to the potential difference? Potential difference keep on varying, right? So therefore, here you can consider current is same, means whatever current is flowing through this will be, so IG, okay? So here potential difference VG, and this is VR, external. So potential difference, okay, V, that is equal to I into R plus G, okay? R plus G, okay? Now this is about simple one. So consider all these as homework, that is, okay, not mark, this is homework, okay? Okay, so let's do it as a homework. Yes, we are in our 5th chapter. From this chapter, we are going to be, very fast. So difficult topics, everything, okay, not all, everything is completed. Now everything is very easy, okay? So let's take a small break. 20 minutes I'll be giving a break. So after that, we can start our session. Got it? Okay. So small break. For 20 minutes. Hello, hello. Good afternoon, good evening. Am I audible? Welcome back. So now, am I audible? Please confirm. Yes, yes. Janav, good evening. Good evening, good evening. Okay, thank you, thank you. So let's get started with a new chapter, that is the magnetism and matter. So from now onwards, the chapter will be moving faster and faster. Okay, so faster and faster. So let's move on to the first topic of this particular chapter. Here you can see. So magnetism and matter. Okay, so the reduction in syllabus, everything you can go through after the session. So first one, bar magnet. Bar magnet means it is an object which attracts a magnetic material. Am I right? Yes. Am I right? Thank you, Manu. Thank you so much. Thank you. Thank you. Yes. You guys are doing something and all. Okay. It's a learning platform. Try to understand. Okay. Now, so it is an object which attracts a small piece of iron and nickel. We call it as a magnet, right? Okay. So what is the property of a magnet? So when you see properties of a magnet, so first one, it attracts a magnetic substance like iron, cobalt and nickel. Okay. And like poles repel, unlike pole attract. These are the basic properties, you can go through it. Okay. And the next one, isolated poles do not exist. Okay. So Gauss law of magnetism, it proves that the monopole do not exist. Okay, so magnetic dipole always exists, but monopole do not exist. So this is concluded by Gauss's magnetic law. Okay, magnetism, Gauss law of magnetism. Got it? Okay, now, sir, Biot law in which chapter? That is the moving charges and magnetism. Okay, Kiran Singh, hi. Okay, now, so these are the properties of a bar magnet. Next one, you see magnetic field lines. Okay, so like electric field only, these magnetic field lines also imaginary lines around the bar magnet, which represents the presence of a magnetic field around it. Okay, so it is also having some important properties of a magnetic field lines. Okay, let's see what are those properties. The first one, you can see magnetic field lines are represents of a magnetic field. The second one, magnetic field lines forms a closed loop, because when you see a magnet, okay, so outside a magnet, the magnetic field lines always start or originates from north and move towards the south. And inside a magnet, if you see, the magnetic field lines move from south pole to north pole. So hence, these magnetic field lines forms a closed loop. And these magnetic field lines do not intersect. If so, that particular point, it shows a two direction, it is impossible. Okay, at a particular point, the magnetic field do not show a two direction. Got it? Okay. Hi Kiran Singh. Hello. Okay. Now, next one, magnetic field lines do not intersect. It is also done. More the number of field lines, so more strong the magnetic fields. See, number of field lines indicates more the number of fields, means the strength of a magnetic field. Okay. So for example, if you see magnet, near the poles, the magnetic field lines will be denser. What does it indicate? The strength of a pole is more compared to the other parts of a bar magnet, right? So here you can see here the strength of a magnetic here at the poles. Okay, it is a different one. Okay, leave it. So when you see a magnet at the poles, the magnetic field strength is more by saying the density of a field lines. Got it? Okay. Sir, I know you will provide the PDF, but please do it without fail. It will be very useful for us. Thank you very much. Definitely, Tulsidas, definitely I'll be doing it immediately after the end of the session. Within 5 or 10 minutes, I'll be uploading it, okay? Maybe it will take, uploading in the internet, okay? Getting my point? Okay, now. Okay, now. So next one, the direction of the magnetic field line, magnetic field line at any point represents the drawing the tangent at point. For example, if I draw one point over here, okay? If I draw one tangent, what does it indicate? That point indicates, that tangent indicates the direction of a magnetic field. Okay, direction of a magnetic field. Got it? Okay, now let's move on to the next concept. That is, first one, magnetic field pattern, okay? Magnetic field pattern of a bar magnet currently carrying finite solenoid and electric dipole. Here one of the important, comparison between bar magnet and solenoid, currently carrying solenoid. You know why? The magnetic field lines of a bar magnet as well as the solenoid are similar. Okay, what is the difference from this topic is the strength pole. Okay, strength of the pole or pole strength can be, or else you can say strength of a magnetic field can be varied in case of a solenoid because it is a current carrying conductor. It can be controlled, where bar magnet we cannot control it. It is a fixed amount. And in a solenoid, you can change the polarity south to north, north to south. But in a bar magnet, you cannot change it. It is a fixed. Okay, got it? So here you can see this is a bar magnet and this is a solenoid. What is the difference? You see, same magnetic fields are same, magnetic field lines, pattern, everything is same. What does it indicates? This solenoid, currently carrying solenoid, acts as a bar magnet. Simple. Okay, significance of this is a currently carrying solenoid behaves like a bar magnet. Got it? Okay. And the next one, it is for the electric dipole. Electric dipole, it is nothing but equal and opposite poles separated by a small distance. And you can see, okay. So it is a bar magnet, right? This is the first one, bar magnet, electric dipole. So here electric field, but here bar magnetic. Okay. This is bar magnet and this is a solenoid and this is a electric field of a electric charges. And don't get confused. Okay, the last one indicates electric field. The first two indicates a magnetic field. Okay, getting a point? But the similarities are they are showing. Okay, similarities between bar magnet, current carrying solenoid. The last one, that is a dipole. Got it? Okay. Now let's move on to the next topic. That is a magnetic dipole moment of a bar magnet. See, already we have learned about a dipole moment, right? That is with respect to a loop, right? So here if I consider this is a north pole and this is the south pole, okay? And a current carrying loop acts as a, okay, current carrying loop, if I consider the dipole moment will be, okay, dipole moment will be given by I into A. For coil, N into I into A, right? So in the same way, with respect to bar magnet, the magnetic moment of a bar magnet, okay, dipole moment of a bar magnet, it is also same. Okay, Everlasting Gospel Ministries, sir, tell about the dipole. So there means they are comparing the field lines, electric field as well as a magnetic field. So with respect to dipole, it is a electric field, not a magnetic field. That's what I said. Okay, got it? Okay, now, so a bar magnet, okay, if I consider bar magnet, it is also acts as a, dipole moment, but how? See, the magnetic dipole moment of a bar magnet is the product of pole strength and separation between the poles. What is the pole strength? For example, the pole strength of a north pole, if I consider plus M, and pole strength of a south pole, if I consider negative M, and you'll be having questions, sir, why it is a positive and why it is a negative? Okay, while studying a properties, it is indicated. Okay, and dipole moment of a bar magnet, it is from south to north. Okay, dipole moment of a bar magnet, it is a south to north. Got it? Here I am representing it as a capital letter M. Okay, so this is due to bar magnet. So your expression, you see, that is equal to, okay, strength of the pole into separation. Separation, if I consider this as a 2D, okay, 2D, here also you can consider 2D, okay, 2D, length between two poles. Got it? Here quantity, it is also vector quantity, and the direction, what is the direction? South to north. South to north. Unit is same, that is ampere meter square. Okay. And pole strength is directly proportional to, okay, small letter m. Capital letter M, it indicates a magnetic dipole moment, where small letter m indicates a pole strength. Okay. Pole strength is directly proportional to the area. If area reduces by 2 times means, okay, for example, area is reduced by 2 times means, what happens to the pole strength? It is also reduced by 2 times. If the area increases by 2 times, strength of the pole is also increases by 2 times. Okay, so directly proportional. Got it? Next one. So electrostatics analog means a comparison. Electrostatic analog comparison. What are the comparison? First, if you see electrostatic proportionality constant, what is the proportionality constant we have considered? K is equal to 1 divided by 4 pi epsilon naught, right? 4 pi epsilon naught. And in magnetism, mu naught divided by 4 pi. Correct? Next, dipole moment. Dipole moment, it is a P that is equal to either charge into separation between them, that is a 2D. Right? In a magnetism is also M that is equal to, in place of a Q, okay, first I'll write, okay, first in electrostatic that is due to a charge, but in a magnetism that is due to a pole strength, okay, that is due to pole strength. Okay, next one that is the electric field in electrostatic, magnetic field in magnetostatic, and dipole moment in electrostatics, and magnetic moment in a magnetism. Okay, so this is the important conversion. Now here M into 2D, pole strength into separation between the poles. Got it? Now next one, equatorial field, electric field. Okay, magnitude I'm writing, okay, magnitude. So equatorial, if you want me to write, that is a minus Kp divided by R cube, right? But what about here? Magnetic field. In place of electric field, it is a magnetic field. No derivation is required. K in place of a P, that is a M, capital letter M. Okay? No. It is a dipole moment, right? So dipole moment here, yes. K M divided by R square. Okay? Now, R cube, not R square. This is R cube. Okay? Yes. Sir, yeah, this is the first introduction part, okay? It is the introduction part. Till electromagnetic waves, it is a electromagnetism only, okay? Till electromagnetic waves, it is a magnetism only. Got it? Okay? Now, next one, axial. Axial line, that can be written as 2 kp divided by r cube. What about here? Magnetic field. That is k m divided by r cube. Okay, now in this case, external field, torque it is given by Pe sin theta. In a magnetic field, torque that is given by Mb sin theta. Okay, next one, energy, potential energy. Let's consider potential energy only. Okay, that is given by Pe cos theta. Pe cos theta, that is with a negative sign. Here, minus Mb cos theta. Minus Mb cos theta. This is the electrostatic analog to magnetism. Okay, now next one. Yeah, this one, see, derive expression for potential energy for a bar magnet when placed in a external magnetic field. See, I have a given clue, okay? I have a given clue. Please go through it. Same as moving charges and magnetism, replace dipole with a magnet. Where we have used a dipole, but here we are using just a magnet. Okay? Yes? So tell the differences between electrostatic and magnetism. everlasting gospel ministers, you have a time, okay? This is a live marathon, and here time is very important for us, okay? Don't mind, okay? So in regular classes, I'll be explaining, but it is a marathon. Please give us some time. Got it? From the basic, you need to understand, okay? Now, so do it as a homework. Next one, Gauss law and magnetism. So what does it says? Okay, so here magnetic field, okay, magnetic field in a closed surface. Okay, magnetic field in a closed surface, that is integration, that is equal to 0. What does it indicates? The magnetic flux through any closed surface is 0. What does it mean? The magnetic field lines or magnetic flux entering and magnetic flux leaving the surface, it is equal. So that is the reason total magnetic flux will be 0. In other word, okay, in other word, if I consider any surface, okay, let's consider this is any surface, okay, any closed surface, and here I'll be keeping one bar magnet, okay, one bar magnet, and in that, if I want to see, this is a north pole, so say it is a plus m, and it is a south pole, say it is a minus m. What is the net moment? I mean strength pole, that is the 0. So magnetic flux, see, electric flux, that is due to charge. Here magnetic flux, that is due to a strength of the pole. If the strength of the pole it is 0, what happens to the flux? Flux will be 0, right? Flux will be 0 if m is 0. Got it? Electrostatic, it is due to charges. Magnetism, it is due to strength pole. Okay, now next one. So this is the statement of Gauss law of magnetism, and the statement is very important, okay? Statement, the net magnetic flux through any closed surface, it is always 0. That is summation, okay? Summation or a sigma B dot ds is equal to 0. Means the sum of all the magnetic flux through surface, it is a 0, okay? Now, here explanation they have given, go through it, okay? Now, next one. What are the consequences of a Gauss law in a magnetism? What does it indicate? So first one, an isolated magnetic pole do not exist. Yes, magnet always exists. Dipole, okay? Up to what time will the session will be going on? Till I think 4 hours, okay? 4 to 5 hours. Now, always magnetic dipole exists, not a monopole. The last one, numbers of magnetic field lines entering a surface is equal to the number of a field leaving the closed surface. Okay, flux, they are talking about a flux. Inward flux, that is equal to outward flux. Therefore, what is the flux inside? That is the 0. That is the consequence of a magnetism. That is a Gauss law in a magnetism. Okay, now next one. Yes, magnetization and magnetic intensity. So first of all, what is the magnetization? Making magnetic material, making a magnet from magnetic material. Simple. Okay, magnetization is nothing but making a magnet from magnetic material. What is that process? We call it as a magnetization. Okay, now how to make a material into magnet? So here we have a procedure. By a solenoid we can magnetize the material. How? Here you can see solenoid, right? Solenoid, okay, and this one, okay, this one connected to external source, say battery. So what I will do is, I'll consider one material, okay, magnetic material. So I want to make this material as a magnet. Okay, I want to make this material as a magnet. What I will do is, so we know that inside this solenoid, the magnetic field will be mu naught Ni, right? Mu naught Ni. So I'll keep this magnetic material inside. So what will happen? After some time, due to magnetic field inside the solenoid, this magnetic material become a magnet. Means it acquires magnetic properties. Get your point? Okay. Now, so this is how you can magnetize a material. Got it? Okay. Now, here we have some important terms with respect to this magnetizing a material. Okay. First one, magnetizing field. Magnetizing field, nothing but external source. External source means the field in which material is placing to magnetize. Okay. Nothing but a magnetic field of a solenoid. That magnetizing field is also called magnetic intensity. Okay. Magnetic intensity. Right. And intensity of a magnetization. Intensity of a magnetization means this material acquires some magnetic properties, right? That property we are calling it as a intensity of a magnetization. Getting your point? Okay. So let's see the definitions. Magnetization, magnetic intensity, magnetizing field. All these terms are same. Okay. First one, it is defined as the net magnetic moment. Okay. First once again. Okay. The first word only, that is a magnetic intensity, magnetizing field, magnetization. Okay. The first one defined as magnetic moment developed per unit volume. Okay. Developed per unit volume. Magnetization, this is given by, okay. So magnetization, magnetic moment per unit volume. Okay. And this one can be written as, so here you can consider small m. Okay. Here they have used a capital letter M. Here you need to use small letter m. Got it? Where V is the volume, right? SI unit if you see, okay, SI unit if you see, that is ampere per meter. Ampere per meter. Next one. Intensity of a magnetization. It is defined as pole strength per unit area of a cross section of the material. Okay. So here you can write this one as, okay, H, that is equal to B divided by mu. Okay. Mu naught. Actually it is a mu naught, where H is N into I. So here you'll be having confusion. Sir, how do we get these values? Remember, magnetic field due to solenoid. Okay. So now here what I am doing is mu naught, this group, okay, Ni, I'm making it as a group. Okay. Now mu naught, that is equal to H. Now H is equal to B divided by mu naught. Okay. Mu divided by mu naught. Got it? Now next one. Magnetic susceptibility of a magnetic material means ease of magnetization. Ease of magnetization means how easily we can make a material as a magnet. Okay, that is we call it as a susceptibility. Okay, now how to define this one? See, the ratio of a magnetization developed in the material to the applied magnetic intensity. Okay, applied magnetic intensity, that is given by chi is equal to m divided by h. M means magnetic moment, okay, magnetic moment or magnetic intensity, divided by h. Okay, h means that is a magnetizing field. Okay, got it? Now, next one. Mention the significance of a magnetic permeability. Okay, permeability. So here it is the ability of a material to permit a magnetic field lines through the material also. Okay, so here ability, permeability, magnetic permeability, mu r. Okay, it can be defined as mu m divided by mu naught, and this is also can be written as B m divided by BO. Got it? This is with respect to magnetic field and this is with respect to permeability. Okay, these two formulas are highly important. Okay, now next one. Define magnetic permeability. Magnetic permeability of a substance is defined as ratio of a magnetic induction to the magnetic induction. Permeability. See the last one. So that mu r is nothing but B divided by H, magnetic induction. Okay, B divided by H also you can write. Okay, the same formula. Okay, this one I am writing. Okay, Bm divided by B naught. Instead of a Bm and B naught, I am writing this one as a B divided by H. Got it? Okay. Yes. Fine. Okay. Now let's move on to the next concept. Derive the relation between relative permeability and magnetic susceptibility. So your relative permeability, it is easy one. Mu r, that is equal to 1 plus chi. Mention. Okay, just mention. So not required a derivation, just mention it. Okay, where mu r is a relative permeability, where chi is the magnetic susceptibility. Got it? Okay, now let's move on to the next topic. susceptibility of a ferromagnetic substance is 3000. What is the relative permeability? Okay. So just now we have a derived, right? Relation, that is 1 plus chi, and here chi value they have given, that is the susceptibility. So mu r, that is equal to, and 1 plus 3000, and this one becomes 3001. 3001. Okay. Now, get your point? Okay. Yes. Ajay Krishna. Okay, you have already learned. Okay, no problem. Okay, no problem. Aram se, aram se. Okay. Yes, any doubts? Any doubts? Do you have any doubts? Okay. Okay, Manu. Yes, I'll do it. Dia, para, as well as a ferromagnet. Okay, it is interesting one. Okay. Blessy, hello, good afternoon, good evening, good evening. Euphoria, paramagnet, diamagnetic ferro. Okay. Jainau, no sir. Okay. Okay. So any questions? Any questions based on this? If not, I'll continue the session. Got it? Okay. Okay. Let's move on to the next topic. Based on a magnetic property, material. There are three types of material. Okay. There are three types of a material. The first one, diamagnetic. Second one, paramagnetic. And third one, ferromagnetic. Okay, ferromagnetic. Okay, so let's start with the diamagnetic. So what is diamagnetic substance? Give an example. Okay, what is diamagnetic? And give an example. See, first definition, I'll try to explain the theory. Okay, the substance which are weakly magnetized in a direction opposite to that applied external field, okay, magnetic field, are called a diamagnetic substance, or a diamagnetic substance are the ones which resultant magnetic moment in an atom is zero. Example, gold, diamond, copper, silver, lead, mercury, and bismuth. So what does it mean? See, each atom, if I consider, okay, if I consider each atom, see each atom. So these arrow marks indicates electrons, okay, electrons. Electrons are anti-parallel to each other. Therefore, net magnetic moment, okay, net magnetic moment and magnetic field will be zero. Because zero, the reason, okay, electrons of atom aligned anti-parallel, okay, anti-parallel to each other. And this is how the magnetic field lines looks like. Here you can see the magnetic field lines moving away from this material. The material is a diamagnet and it is independent of a temperature, okay. The magnetization of this material, actually we cannot magnetize this diamagnetic material, okay. So magnetic field lines are weakly repelled by a magnetic field, okay. So this diamagnetic material, the magnetic field weakly repelled by diamagnetic material. Got it? Okay. Now, so this is about a diamagnetic material. Now, next one. What is paramagnetic substance? Give one example. The substance which are weakly magnetized in the direction of magnetic field are called paramagnetic substance. Here you can see when the material placed in an external magnetic field, so some of the magnetic field, passing through this magnetic material, means this paramagnetic material weakly attracted by this external magnetic field. Okay, this material, what is that material? Paramagnetic material weakly attracts magnetic field lines, means it allows a magnetic field lines to pass through them. but it is a weakly, not strongly, right? So that is, about a paramagnetic material, about paramagnetic material. Example, you see aluminum, sodium, and platinum. And the last one, that is a ferromagnetism. It is a better version of a paramagnet. Okay, better version of a paramagnet. See, better version of a paramagnet. Why? Because they have a domains. They have a domains. Okay, they have a domains. Due to alignment of these domains, okay, so these are called domains. Okay, these are called domains, and in each domains, if you see the magnetic dipole moment, they are aligned. Okay, they are aligned in a particular direction. They are aligned in a particular direction. Okay, and this one, see, each domain, okay, separately, each domain have, these are called domains. Okay, these are called domains. These are called domains. Each domain has magnetic moment as well as a dipole moment. Magnetic moment as well as a magnetic field. Okay, so this one we call it as a better version of a paramagnet because the magnetic field lines, okay, magnetic field lines looks like this. Okay, so these ferromagnetic material, okay, strongly attracted magnetic field. Magnetic field lines. Okay, magnetic field lines. Magnetic field lines. Got it? Okay, fine. Now, let's try to understand the definition. Already I have explained theory part. Now, substances which are strongly magnetized in the direction of applied external magnetic field are called ferromagnetic material. The example, iron, nickel, cobalt are the ferromagnetic material. And soft iron, it is a ferromagnetic material. Where do you use? That is in the core of a transformer. Core of the transformer. Got it? Okay, now. So this is all about, ferromagnetic material. Ferromagnetic material. Now let's move on to the next concept. Write the differences between diamagnetic and paramagnetic material. Please go through it, okay? So this is the theory part, okay? I have explained in the, atomic model. Please go through this, okay? Will you go through this? Theory part, this is also distinguished between diamagnet as well as ferromagnetic material. Theory part, what I have explained is the same thing. See, they are freely repelled by the magnets, diamagnet. They are strongly attracted by the magnets, right? Second one, magnetic susceptibility is low and negative. Magnetic susceptibility high and positive. All these I have explained previously. Okay, now, next one. Solenoid has a core of a material with a, okay, this is the numerical part. Okay, I'm leaving it to you. Next one, numerical part, I'm leaving it to you. And the next one, electromagnetic induction. Next one, electromagnetic induction. EMI, electromagnetic induction. Got it? Yes? Guys, if you have any questions, you can ask me. Okay? If you have any questions, you can ask me. Yes? Yes, yes. We can solve. We can solve the numericals. Okay? Tulsidas, we can solve. Yes? Jaino, no questions, sir. Please continue. Okay, fine. 1 second. I'll come back. Yes? Any questions? Yes? Any questions? Yes, yes. Both the parts. Art with Praveen. Yes, both the parts I'll be taking up. Okay. Tulsidas. Guys, shut up and study. Let them enjoy. Okay. They have a freedom. Fine. Okay. Let's start. So electromagnetic induction, the first one. So here the data you can see are deleted portion as well as Marx distribution. Okay. Now magnetic flux, like electric flux only. So number of where in electric charges and fields we have learned about electric field, right? Here with respect to magnetic field, that's all. So in case of electric field, what we have learned, flux is equal to EA cos theta. Here BA cos theta, that's all, nothing else. Same explanation. See, the number of magnetic field lines passing perpendicular to an area is called magnetic flux. Expression, if you see magnetic flux, okay, expression if you see magnetic flux, that is given by BA cos theta. And here this is a B and this is area vector, and this is B, magnetic field. And angle between them is a theta. Got it? Okay. So can you tell me what is the unit and quantity? Magnetic flux. Okay, when it will be minimum and when it will be maximum. So unit, can you tell me what is the unit? Yes. What is the unit? Tulsidas. Yes. And Jainav. Yes, Jainav. Minimum when theta is 90 degree. Yes, perpendicular to area. Right. So here unit of a magnetic flux, that is a, what is the unit? Tesla and meter square. Tesla meter square. Flux. Okay. Unit is Tesla meter square. You know why? What is the unit of a magnetic field? That is Tesla. Area, that is a meter square. Theta do not have a unit. Quantity, it is a scalar quantity, like electric flux only. Scalar quantity. Magnetic flux minimum, when it will be minimum, theta is equal to 90 degree. Okay, theta is equal to 90 degree. Then magnetic flux will be 0. Okay, and the maximum when theta is equal to 0 degree or 180 degree. So flux will be, magnetic flux will be plus or minus BA. Why? Cos 0 is 1, cos 180, that is minus 1. Okay. Gogita, TM square, very good. Okay. And Tulsidas, Euphoria, yes, correct. Very good, my dear students. Okay, so let's move on to the next concept. So here we have electromagnetic induction. What is this electromagnetic induction? It is the phenomena in which, okay, inducing electromotive force, EMF, in the coil due to change in a magnetic flux linked with the coil. Simple. Here nothing but we are producing electricity by magnetism. Simple. Okay. So here you can see the phenomena in which EMF and hence current in the induced in a circuit by varying a magnetic field is called electromagnetic induction. Simply, why? How do you vary magnetic field? How do you vary magnetic field? By changing a magnetic flux. Means a flux, magnetic field lines linked with the coil so that we can change the magnetic flux, rate of change of a magnetic flux. Okay? Yes? Okay. Now let's note down the definition. After this, we have one more topic, that is observations. Okay? What are the observations? Yes. So the experiment of a Faraday and Henry. What is the first point? Experiment arrangement consists of a coil. Here you can see coil. Okay. And here galvanometer and here a bar magnet. Simple. Okay. Insulated copper wire and connected to a sensitive galvanometer. Galvanometer G. A bar magnet is moved towards to and fro as shown in the figure. See, as the magnet is moving towards the coil and away from the coil, this galvanometer shows the deflection in it. Okay, shows the deflection in it. So when the bar magnet is at rest, means there is no velocity. when velocity is, it is 0, okay, when velocity it is equal to 0, when it is rest, there is no change in magnetic flux. When magnet is at rest, there is no change in magnetic flux, okay. So here, there is no change in magnetic flux means there is no deflection in the galvanometer. And one more observation, if the magnet is moved faster towards the coil, the more the deflection and faster the deflection is observed. And Tulsidas sir, when it is sine theta 90, it is a maximum, and angle it is minimum. And when it is cos, yes, that's what? Dot product and cross product of a vectors, okay? Dot products and cross product of a vectors, okay? Please concentrate on that. Fine, okay. Now, when this bar magnet is moved slowly, what happened? Slow deflection happens and slow magnetic rate of change of magnetic flux happen, okay? Now, these are the observation made by the Faraday and Henry. Here you can see, go through that. When the magnet is moved towards the coil, a momentary deflection is produced in the galvanometer. When it is moved away, deflection is produced, but in the opposite direction. Second point you see. Second point. When the magnet is moved faster, more deflection is produced and faster the movement of a galvanometer needle. Okay, next one. When both the coil and magnet are stationary, means stationary. Okay, both are stationary, are moving in the same direction. Moving in the same direction, same speed. There is no relative motion, right? If the magnet is moving, as well as coil is also moving, therefore, what is the relative velocity between them? It is a 0. So hence, okay, hence, here there is no deflection in a galvanometer. Okay. Okay, now, the last one, the amount of deflection increases if the number of turns in the coil increases. Means, here number of coils are there, no? If you increase the number of turns, then the magnetic flux linked with the coil is also increases. Okay, that is the fourth important point. Okay, these results shows that there will be a EMF, hence current is induced in the coil due to relative motion between the magnet and the coil. Okay, magnet and the coil. Got it? This is the experimental observation. Next one. Faraday laws. First law. The magnet of induced EMF. We know that whenever there is a change in magnetic flux, there is a induced EMF. But magnitude-wise, how much induced EMF will be produced? How to know it? So for that, okay, Faraday gave a law. First law states that the magnitude of induced EMF in a circuit is equal to the rate of a change of a magnetic flux linked with the circuit. Okay, so this is epsilon. Okay, epsilon d phi divided by dt. So negative sign indicates it is opposing nature. Okay, opposing nature means there is a magnetic change in magnetic flux. Okay, the coil do not want to change the magnetic flux. So here negative sign indicates it is the opposite nature. Negative sign indicates the direction induced EMF. Okay, direction of induced EMF. Okay, the direction of induced current in a closed loop opposite to the change in the magnetic flux. Opposing. Okay, for a coil. Okay, for a coil, if I write epsilon, this is for a loop. Okay, this is for a loop. This is for a loop, and this is for a coil. So this one can be written as N d phi divided by dt. Got it? With a negative sign. Next one. Induced electric field. Its field lines are concentrated circular closed surface. Okay, like electric field. Here also induced electric field. Okay, induced electric field. So what are the characteristics? Here you can see its field lines are concentric circular closed curves. A time varying magnetic field, okay, dp divided by dt always produces induced EMF, that is electric field, in all spaces surrounding it. And this last one, it is very important one. Okay, that is epsilon, that is equal to integral of E induced, electric field induced dl is equal to minus d phi b divided by dt. That is a magnetic flux. Okay, magnetic flux. Got it? Okay, now let's move on to the next concept, that is Lenz's law. Lenz's law, it is nothing but opposes a change in a magnetic flux. Lenz's law, it's nothing but it gives the polarity. If there is increase in the magnetic flux, okay, change in magnetic flux, this coil develop opposite nature in the coil itself. Okay, so now here you can say that Lenz's law states that the polarity of induced EMF is such that it tends to produce a current which opposes the change in a magnetic flux. Okay, what is that? Opposes magnetic flux, produced it, or else you can say that this is the easiest way to say. Okay, the induced current in the coil flows always in such direction as to oppose the cause which produces it. Okay, simple polarity. Just remember it is a polarity. Got it? Okay. Now let's move on to the next one. Motional electromotive force. Motional electromotive force. What does it mean? The EMF induced across the ends of a conductor due to which motion in a uniform magnetic field is called motional EMF. Okay. So for example, here I have considered a magnetic field, inward magnetic field. Okay. Inward magnetic field. And this is inward magnetic field. And this is a length of a conductor. Okay. Length of the conductor moving. Okay. Moving with a velocity. Moving with a velocity v of a length L, and this is the x. So this one will be moving forward as well as forward and backward, motional EMF. By moving, okay, by moving this rod across the frame in a magnetic field, it produces, okay, it produces induced EMF across the ends. Ends means for this. Okay, now here you can use, okay, the magnetic, this one rod moving in a magnetic field. Okay, now what you have to do is, so if it is a moving, okay, magnetic field direction, and this thumb indicates a motion of a conductor. Okay, motion of a conductor. Use the same right hand palm rule to find out direction of a EMF. Okay, which one is high potential and which one is low potential, because by this, okay, by the statement we know that induced EMF, okay, EMF induced. So which side is a positive and which side is a negative? To know that, use right hand palm rule. Okay, now here you see direction of a magnetic field. Use this fingers. Okay, direction of a magnetic field, and this is the direction of a motion, and above this, okay, this palm indicates high potential. That means it becomes a positive potential, and this one negative potential. Okay, so this one give you, okay, so here what is the value of a phi? Okay, phi it is given by BA cos theta. So here theta is again 0 degree. Why? Because magnetic field and area vector both are in the same direction, inward in direction only. Okay, inward in direction. Therefore, I'll be left with a BA. So here I can substitute the d divided by dt and BA. Got it? BA. And here you can see B, E, that is equal to, and here you can see this a BA, area. What is that area? Here you can see that B is a constant, B divided by T, and area can be written as, okay, here area can be written as this one. Okay, area can be written as, we are not able to consider this one because it is an open one. Okay, it is not a closed loop, this is an open loop. Here we cannot consider it. Area, it is given by x into L, x into L. So here what I'll do, in place of A, I'll be replacing L, x into L. So here L is also constant because length of this rod cannot be changed. Take it outside. So BL remaining dx divided by dt. Okay, so dx divided by dt, what does it mean? It is a velocity. Okay, BLV. Okay, velocity. BLV, velocity, right? Okay, velocity. Got it? Fine. Now, so this is about motional EMF. Now let's move on to the next topic, that is self-inductance. Self-inductance. What is the meaning of a self-inductance? What is the meaning of a self-inductance? Okay, what is the meaning of a self-inductance? You see, so it is connected to a battery. Okay, it is connected to a battery, and the current starts flowing, okay, in this direction. The current flows in this particular direction, and it will be moving along the wire, and the wire in form of a loop, So due to this loop, there will be a magnetic flux. Due to the loop, there will be a magnetic flux. So what is the magnetic flux? Here phi, magnetic flux. So this magnetic flux, okay, the magnetic flux is directly proportional to the current in the coil, okay. Flux in the coil is directly proportional to the coil, current in the coil. Means if I increase the current, okay, if I increase the current, magnetic flux is also increases. Magnetic flux also increases. If I decrease the current, the magnetic flux also decreases. Okay. So I want to eliminate this proportional. Therefore, I can consider L into I. So this L only self-inductance. Okay. Self-inductance. 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 And in terms of self-inductance, I can write this one as L is equal to phi divided by I. L is equal to phi divided by I. Got it? Okay. Now, next one, self-inductance of a solenoid. Self-inductance of a solenoid. How to do this? Self-inductance of a solenoid. Okay. No, it is going out of, okay, out of the range. Okay. So please concentrate on studies. Okay. Now, so magnetic current, okay, derive an expression for a self-inductance, okay. So here, when a current passes through the solenoid, the magnetic field, okay. So magnetic field, it is given by, okay. Magnetic field, it is given by mu naught Ni, right? Mu naught Ni. Mu naught can be written as N divided by L into I, okay. Now, flux through the coil. Flux is given by one coil, okay. Flux through one coil. So here, if I consider flux through one coil, two coil, three coil, four coil, five coil, six coil, and so on. So let me consider for first one. So BA, okay, BA. And here, B, what is the value? That is mu naught Ni divided by L. What about the area? Area pi r square, right? Pi r square. Flux through all the coils, okay? Flux through all the coils. That will be N mu naught, okay, Ni pi r square divided by L. So here what I will do is, I'll take out this I outside. So here N square, okay, N square mu naught, okay, N square mu naught and pi r square divided by L into I, okay. So now this value only, we are calling it as a L. So where L is N square omega naught, okay, mu naught pi r square divided by L, okay. So this one reduced to this form, that is a phi that is equal to L into I, where L is this one, self-inductance. What they are asking? Self-inductance only. That is the value. And if you want to further simplify that, you can still do it. Multiply and divide by L. Multiply and divide by L. What is the values then? L is equal to N square mu naught pi r square L divided by L square. So here mu naught N square divided by L square, okay, and pi r square, it is a A, right? Pi r square, it is a A into L. So further simplify, flying, okay, further simplifying. So L is equal to mu naught, what is the value? This one, okay, it is a N square and A into L, area into length, that is the volume, okay. So this is correct, this is also correct, okay, both are correct only. Got it? Okay, fine. Let's move on to the next concept. So that is magnetic energy. So magnetic energy, nothing but when a solenoid or inductor is connected to a battery, and energy is stored in an inductor in the form of a magnetic field. The work done to make a current flow in the inductor is store energy in the form of a magnetic field. So generally power, it is given by W divided by dt, and this P, nothing but a power. So I want to work done, therefore I am writing it as a dW into P into dt, okay. dW, that is equal to P, that is equal to I into V dt, and V is a EMF. Therefore I can write from the EMF, induced EMF, I into, okay, L into di divided by dt into dt, right? So here di get cancelled, dw that is equal to li di. Okay, now I want total work done, therefore I can do it as a dw. Okay, dw. So here work done that is equal to integration dw value, that is L I into di. Okay, now w is equal to L, it is a constant, I'm taking outside, and what is the integration of I? That is I square by 2 into di. Okay, and finally you have, that is Li divided by 2. This is the work done. Okay, so that is in terms of L as well as I square. Yes, Manu, I'll be covering all the chapters, okay? Don't worry, I'll be covering all the chapters. Within 10 or 10:30, I'll be completing all the chapters. Got it? Okay. Now still we have a 2.5 hour more. Okay. Now, let's move on to the next topic. So, magnetic energy coil. So, just to go through it, okay? Just to go through it. And it is not so important. So, important one, we'll do it, okay? Why self-inductance is also called inertia of electricity? Because it opposes the current developed itself, okay? So, when a current flowing through the circuit, means a coil, it develops a magnetic flux to oppose it. That is the reason we call it as a self-inductance is a inertia in a circuit, okay? So, that is the reason, okay? Self-inductance shows down, okay, slows down or oppose any change of a current through it. That's why it is called as inertia of electricity, okay? What are the factors on which self-inductance coil depends? So, to know that, you remember this formula, okay? Okay, I'll write here only. Self-inductance, okay, what is the self-inductance? That L is equal to, okay, mu naught N square V. So, this can be written as mu naught N square divided by L square into A into L, okay? We can use this one. Area, that is, further we can simplify it, not required. See, it's a length, fine. Number of turns. Area of a cross section. Permeability of a material. Got it? If you know the formula, aramse you can write it. Okay? Fine? Yes? Kriti from Rajasthan. Okay. Yes. Okay. Now, let's move on to the next slide. So, here calculate induced EMF in the coil. Okay? Magnetic flux linked with the coil changes from, okay, 12 into 10 power minus 3 to 6 into 10 power minus 3 in 0.2 second. 0.01 second, calculate induced EMF. Induced EMF, it is given by, try to calculate this one, d phi divided by dt. They have given a change in magnetic flux from, okay, from 12 into 10 power minus 3 minus 6 into 10 power minus 3 time, it is 0.01. Okay, simplify this. Yes, any answer? What is the final answer for this? Yes, what is the final answer for this? Yes, fast. What is the final answer for this? Okay, please try to answer this question. Simplify this. Okay, next one. What is the mutual inductance? The phenomena of inducing of EMF in one coil due to the change of a current in the neighboring coil is called induced EMF or mutual induction. Okay, what does it mean? For example, this is the coil and this coil is connected to cell or battery. Okay, cell or battery, and when the current flows through this, okay, when current flows through this, and there will be a magnetic field emerging from it, right? And the neighboring circuit, okay, and it is not connected to anything, okay, If these magnetic flux, okay, linked with this coil, what will happen? There will be a mutual induction. Get your point? There will be a mutual induction. So, neighboring coil is called mutual induction. So, it is just a phenomenon of inducing EMF in one coil. okay, inducing EMF in one coil due to the change in the current, in this coil, okay, neighboring coil is called mutual inductance. Got it? Okay. Now here two derivations are there. Try to do it, okay? Try to do it. Coaxial as well as a mutual inductance. What is an AC generator? What is the principle behind it? So your AC generator is nothing but a device, okay? It is a device which generates a mechanical energy into electrical energy, okay? I am tech editor. It will be awesome. You'll be enjoying, okay? I am tech editor. You have a lot of, bright future because still you are in 11th and watching 12th standard videos, okay? Good. Curiosity. Aru Sharma. Good evening. Yes, the principle of a mutual induction. Principle A is a mutual induction, yes. So you are answering this one, okay. A device, it is a converting mechanical energy to electrical energy, okay. Why not DC generator? DC generator produces a very less amount of current, right? So DC generator, like, small toy car, it cannot run, okay. It is very, magnitude wise, if you consider a magnitude wise, it is a very small, okay. AC current, it will be more. Frequency of a 50 hertz, okay. Got it? Okay. Euphoria, 50 hertz, correct. AC frequency, it is a 50 hertz in India. So in different countries, they have a different frequency, okay. Now, so first of all, definition, AC generator. It is a device which converts a mechanical energy to electrical energy, first one. Next one, a principle. What is the principle behind it? It is a EMI, that is the electromagnetic induction. Precisely, it is a mutual induction, okay, precisely. It is a induction only, that is the electromagnetic induction only. Got it? Mutual induction, that is based on transformer, AC, okay, that is alternating current. We'll see that, okay. Now, next one. So principle, it is done, okay. So it is simple, just a principle and a naming, you should know. And output of this, okay, output of this, E is equal to d phi, okay, dt, and phi it is given by BA, right, BA. So BA, and here flux it is given by d phi divided by, okay, so magnetic flux, and here the coil is rotating, okay. Okay, so this is for one coil, you have a BA. For n coil, that is a n loop, okay. For this one, it is for a loop. This is for loop. And d divided by dt, that is equal to NBA cos theta, right? NBA cos theta. NBA cos theta. NBA cos theta. And here, NBA cos theta. And differentiation, NBA, it is a constant, take it outside. Differentiation of a cos theta, it is a sin theta, right? Differentiation of a cos theta, that is a sin theta, okay, sin theta. And here you can see, here theta, okay. So first of all, here we need to change. Theta is nothing but omega t, okay, angular velocity. So here you can say d divided by dt, NBA cos omega t. This is angular displacement, okay. Theta is angular displacement. Now here we can consider E is equal to differentiation NBA sin theta. In place of sin theta, it is a omega t, but it is just not just a t, it is a omega. So here you can consider it as a NBA. Magnitude I am considering. You'll be knowing, sir, cos theta differentiation, it is a negative, right? Right? But here I am considering just a magnitude. NBA omega sin omega t. Okay, sin omega t. And here you can see NBA omega. This one I am writing it as a sin omega t. So E naught, this one we call it as a peak value. This one we call it as a peak value. This is the EMF. So this one we can write it as a V is equal to V naught sin omega t. Sin omega t. Got it? Sin omega t. Okay? Okay. Fine. Welcome. Gamers fun for. Okay, that's fine. Nice. How much? Okay. You guys are discussing the answers. Okay, good. Manu, yes, sir. Okay, fine. Next one. So this final, see, this V is equal to V naught sine omega t. We are going to use in AC. Okay, we are going to use in AC. Fine. Now let's move on to the next concept, that is alternating current. So alternating current, already you have seen the chapter name, that is alternating current. Okay, alternating current. So here you can see the deleted topics also. The first topic, that is what is an alternating current, DC as well as AC. Okay. Tulsi Das, sir, how do you remember all these derivations? It is the practice. Okay, if I leave for at least 1 or 2 months, gone. Okay, if I leave teaching for at least 1 or 2 months, it is gone. Okay, nothing will be there in my mind. I have to recover again, recall it again by sit and study. Simple, sit and study. Now, okay, so let's start with a new chapter, that is alternating current. And before starting alternating current, just to remember, okay, what is the difference between AC and DC? Okay, so AC, it is a alternating current, DC, direct current. The word only indicating. DC, where the magnitude as well as the direction remains the same. But alternating current, the direction as well as the magnitude keep on vary periodically. Got it? Okay, so this is the smallest difference between AC and DC. And here we use AC power. Okay, AC power. What is the reason? Because we can reduce the loss of energy. Getting your point? Okay. Now, the current which varies periodically with respect to time, reversing the direction. See, first it is started from 0. Okay, started from 0, moving, increasing. This part we are calling it as a peak values. Okay, peak values. Okay, peak values. If I use current, I will be using I naught. If I am using voltage, I'll be using V naught. Okay, peak values. And again, as the time is increasing, again it comes to the 0 and moving downward. That is a negative and positive, and 0, positive, negative, 0, like this. Okay, and here we are going to use this part. Okay, this part, this is also can be used, but for our syllabus, the first one it is there. Okay, now next one. Write any two advantages of AC. Why do we use AC current? Someone asked, right? Someone asked, sir, why don't we use the DC? Why only AC? Because the loss of power is less in AC. Okay, the first one you can see, electrical energy can be transmitted easily to long distances. Okay, economically, without loss of energy. Okay, AC can be stepped up or stepped down easily and effectively, but DC it cannot. Okay, it is a magnitude as well as direction, it is a constant. We cannot do that. Okay, now, so this is the two advantage over DC. Okay, advantages over DC. Now next one you see, define time period. So time period means, okay, it is the time taken. For example, waves, already in the first year we may remember these definitions. Okay, time period, frequency, waveform, amplitude, everything. Okay, yes. Okay, define time period. It is the time taken by AC to complete one cycle of a variation. Means if I consider this is y-axis and this is x-axis, and from here to here, okay, from here to here, okay, from here to here, okay, this we call it as a time period. Okay, to complete one wave, means one crest and one trough. Okay, one crest and one trough. So this time taken by the waves to complete it's a one cycle, we call it as a time period. And amplitude, the maximum displacement of the wave, we call it as a amplitude. Okay, frequency means number of vibrations or number of cycle completed in one time period, or per second, we call it as a frequency of a wave. Okay, now next one, frequency of wave. Already I have explained. Okay, that is number of times AC quantity changes its direction in the circuit per second. Means positive axis, negative axis, positive axis, negative axis, positive axis, negative axis. So how many times it changes per unit time? Means per second. That one we call it as a frequency of AC. Got it? Okay. Now, so next one. Define instantaneous value of AC. Instantaneous, immediately, at a particular time, okay, at a particular time. Now we can see the value of alternating current or voltage at any instant of a time, T, is called instantaneous value, okay, instantaneous value, okay. Now, let's move on to the next one. Define mean value of a voltage or current. Mean value. Here, mean value, what does it mean? Mean value. Instantaneous value, we know that. What about a mean value? See, mean value is nothing but it is defined that steady current which is transports same amount of a charge in a given circuit in the same time as the alternating current does in the same circuit in a time equal to the half of its time period. So that means steady current means a DC current, okay? Q AC, okay? So for example, if I consider a circuit, okay? If I consider a circuit and this is a current, that is a DC current, and this is a resistor, and time T1 to T2, okay? And a DC current if I consider, okay, AC current if I consider, okay? AC current if I consider, this is IAC and this is also resistor, R1, T1 to T2, time is also same. If I want to calculate total charges, okay, total charges, it will be I into, okay, IDC, that is equal to Q total IDC bracket of a T1, T2 minus a T1. And here in this particular case, you can calculate this total charge, okay, total charge as integration IDT, okay, that is T1 to T2. So here by substituting the values, okay, by substituting the values, here you will be getting IDC T2 minus T1, that is equal to integration T1 to T2 IDT, okay. So further simplification, okay, I'll be using here only. Further simplification, IDC that is equal to integration of a T1 to T2 IDT divided by T2 minus T1, okay. So after derivation, you'll be getting this IDC only, I mean that is equal to T1 to T2 IDT divided by, okay, I divided by T2 minus T1. This is the relations. This is the relation, okay. Now let's move on to the next question. Define the RMS or effective value, IRMS, and of a current and voltage. It is same. It is defined as the square root of mean of the square of instantaneous value of voltage as well as current, okay, taken over the complete cycle. You need to remember VRMS and IRMS, okay, IRMS formulas, okay. Now let's move on to the next question. If the peak value of a current is 1.41 ampere, then what is the value of a root mean square of current, okay. So IRMS, previous slide you can see, okay, I naught divided by root 2, and the peak value they have given. How much it is? 1.41, okay. Then what is the value of a root mean square? So just substitute the values. IRMS 1.41 divided by root 2, okay. Solve it. Next one. Next one. If the voltage of AC supply is 300, what is the RMS value? So V naught, okay, V naught peak value they have given 300, okay, 300 voltage, and VRMS we need to find out, okay, and VRMS that is given by V naught divided by root 2. So substitute the values and get the answer, okay. Numerical part, I think it is very easy, okay. Already I am writing formulas and giving it to solve, okay, simple, okay. Now fine. What is a phasor? Phasor, it is nothing but a rotating vector to represent EMF, nothing but a voltage as well as a current, okay. Voltage as well as a current. Very good, Manu. Very good answer, okay. And this phasor will be used in a representation of EMF as well as a current because they are changing with the angle, means a phase difference. Get your point? Phase difference. Got it? Okay, so that is the reason this phasor is very important. Okay, phasor is very important. Now, next one. AC voltage applied to a resistor. AC voltage is applied to a resistor. See, AC voltage applied to a resistor by Ohm's law, okay? Ohm's law. V is equal to IR. What is the input voltage? That is V naught sine omega t into is equal to IR. Here I want instantaneous current, so that I can write V naught divided by R sine omega t, right? So this one I can write it as a I naught, okay, sine omega t, okay, sine omega t. I hope leading as well as a lagging, I hope you remember all these topics, okay? Here we have a lesser time. I cannot revise all those things, okay? Leading and lagging, okay? Yes. Okay, Akash Padak, okay sir, fine. Okay. I got answer from only Manu, okay? Gogita, okay. Try to answer, okay? Don't involve in such things, okay? Please concentrate. It is very important time for you, okay? Now, see, observe these functions, okay? Current as well as voltage. Current as well as voltage, okay? One second. Voltage, here I'll write, okay? So, voltage, V is equal to V naught sine omega t. Sir, where do we get this equation? Previously, from AC generator, okay? Now, compare these two, okay? In place of I, it is a V. In place of I naught, it is a V naught sine omega t, sine omega t. So, is there any phase difference? No phase difference. So, hence, this is, there is no phase difference with respect to resistor. Hence, no lagging as well as leading, okay? No lagging and no leading in case of this AC circuit containing resistor. Now, AC voltage applied to a resistor. Already I have derived it, okay? Already I have derived it. Next one. Did an expression for the instantaneous current in case of AC applied to pure inductor. Draw the phasor diagram represents the relation between current as well as voltage. So, voltage is given by, okay? Voltage is given by, okay? Voltage is given by V naught, right? So, here, see, inductor, generally, so here inductor. So, already we have learned about, coil, magnetic flux, EMF, everything we have learned in an EMI, right? So, same concept used there, okay? By applying Kirchhoff laws, okay? So, this one, I can write it as a minus voltage across inductor, that is equal to 0. Voltage by the source, VL across inductor. Why it is a negative? Because it is opposing nature. It acts as a coil, opposing nature, okay? That is a VL. So, V naught sine omega t minus, what about VL? That is L di divided by dt, that is equal to 0. Rearrange this equation. After rearranging, okay, L di divided by dt, that is equal to V naught sine omega t, okay, sine omega t. And here I'll be writing, so L, okay, cross multiply this one, di divided by dt, okay, V naught divided by L sine omega t, sine omega t. Now I need a di, therefore V naught L sine omega t into dt, okay. So on integration, okay, on integration, I'll move on to the next slide. On integration, what do we have? Di is equal to V naught L divided by sine omega t into dt. On integration, okay, on integration. So this one becomes, okay, on integration di, V naught and L both are constant. I'll take it outside, and the integration of a sine omega t into dt. And after writing this one, okay, inductor, so total current I and V naught L and sine omega t, that will be minus cos omega t divided by omega, integration, okay. There is no definite integral, okay, no definite integral, mu naught divided by omega L, okay, and remaining cos omega t, okay. This one by definite integral, indefinite integral, here we do not have any definite integral, means limits we do not have. By doing that, okay, easy way, if you get a minus cos omega t, So phase difference will be, okay, V naught divided by omega L into, okay, in terms of a sine, I'm converting it. This cos omega t in terms of a sine, I'm converting. That is a mu t minus phi. That is nothing but pi by 2, okay, pi by 2, pi by 2. So now this one I'll reduce to further that I is equal to V naught. This one omega L, I can write it as a, okay, omega L, I can write it as a XL sine omega t minus pi by 2, okay, minus pi by 2. Now, this again reduced to I is equal to I naught sine omega t minus pi by 2, okay, and V, compare the V naught sine omega t, that's all right, with respect to EMF, that is a sine omega t. Got it? So this one, this is I with respect to, and this one is with respect to V. Okay, getting my point? English examination 100 out of 100. Very good, congratulations. Very good, Akash Padak. Very good. Abibi V logs. Here this chapter is AC, okay, alternating current, okay, and we are almost half finished. Fine. V sine omega t. Now, you see, here a negative sign is there, right? Negative sign. Compare this negative sign. Negative indicates lagging or leading, right? Lagging or leading. Current as well as V. Current as well as voltage. So, negative sign indicates a lagging. Therefore, I is a lagging V. Means V is a leading a current by pi by 2. Can I say that? Okay. This V is leading, okay, current by pi by 2. Why? What is the reason? Here we have a phi phase difference. How much it is? Pi by 2. But a positive or negative? Negative. Negative means lagging. Positive means, okay, positive means a leading. But here current, with respect to current, what is the a phase difference? That is pi by 2 with a negative. That means I is a lagging. Very good, Manu. Okay, very good. Okay. So now, here you see, this V is a leading and a current lagging. Here you can see. This is a V and this is I. So, V is leading, I is lagging. Got it? And waveform, phasor diagram, we can write this, you can write this, we can write this. Anyone, okay? Got it? Sham Chaudhary, okay. Got it, okay, fine. Fine? Okay. Next one. AC voltage applied to a capacitor. Same procedure you have to do it, okay? So by the definition, okay, by the definition, C is equal to Q by V, right? I need Q, therefore CV I can write, and Q, that is equal to C. What is V value? V naught sine omega t, right? So Q, what is the definition of a current? That is a rate of a change of charges, okay, rate of flow of charges. So if I differentiate with respect to time, dq divided by dt, CV naught, okay, cos omega t into omega, right? Cos omega t into omega. So further simplification, you can see this dq divided by dt, can I write it as a I? Yes, by the definition of a current. Next, V naught C omega cos omega t. Okay, now I is equal to V naught. This can be written as, okay, this can be written as 1 divided by C omega. Can I write? If I take to the numerator, still you are getting a same value, cos omega t, right? So this cos omega t, in terms of a sine, if I write, okay, V naught, this entire term, I can write it as a xc, okay, xc, sine omega t plus pi by 2. Why it is pi by 2? Because this is just a cos, not a negative cos omega t, okay? Yes? Okay? Now, so further simplification, I is equal to, this is I naught sine omega t plus pi by 2. Okay? Now, with respect to V, V naught sine omega t, compare the both things, okay? So this is a pi, phase difference, it is a pi. Phase difference, it is a pi. But sine you see, okay? Pi. it is a positive. Pi by 2, it is a positive. Means leading. Current is leading voltage in case of a capacitor. In case of a resistor, no lagging, no leading. Next one, in case of inductor, there is a lagging. But which one is lagging? Current is lagging. But in case of a capacitor, V is lagging, but current is leading. Getting my point? Pi by 2. Angle by a pi by 2. Okay. Now, next one, voltage. So here you can see this is a waveform and this is a phasor diagram. Okay. Now, so these are the definition of capacitive reactance as well as capacitive inductance. Okay. Got it? Okay. So you please go through it like resistors only. Resistors only. Now, inductive reactance and capacitive reactance. So difference. Okay. So here inductive reactance that is given by omega L. Capacitive reactance that is given by XC. Okay. That is 1 divided by omega C. And here you can see it's the opposition offered by the inductor to the flow of alternating current. It is the opposition offered by the capacitor to the flow of current. Both XC, XL acts as a resistors itself. Okay, but they are not resistors. Okay. Now, inductive reactance increases with increase in frequency. Capacitive reactance decreases with increase in frequency. Because here you can see inversely proportional. So that means if a frequency increases, what happens to the XC? Decreases, and vice versa. But here XL and omega both are directly related, but here inversely related. That XC is inversely related to omega. So that is the reason if a capacitive reactance decreases, increases with the frequency. Omega is a frequency. Got it? Okay. Now, next one. Did an expression for impedance in a series LCR circuit using phasor diagram. So here I'll be writing directly. Okay. So net voltage. Okay. Please go through this once. Okay. That is R square. Okay. VR square. Resistor plus XL. Okay. So VL minus VC whole square. That is in terms of voltage. In terms of resistance, okay, in terms of resistance, okay, Z, that is the impedance, okay, that is impedance. Here you can write V, that is equal to IR, okay, by Ohm's law. So V net, I can write I into Z in series, okay, so in series means I will be constant. Therefore, I square R square, okay, and this one, IXL minus IXC whole square. Take out this I outside the square root. So I under square root R square plus XL minus XC whole square. Now here you can see this I get cancelled. Remaining impedance. Impedance means a total effective, okay, total or effective resistance of the circuit. Okay. Got it? So here you can see this is R square plus XL minus XC whole square. Okay. Got it? Fine. Now, next one. Mention the factors on which impedance does depends. So, impedance you see, okay, that is R square plus XL minus XC. XL minus XC whole square. Okay. So, this is the impedance. So, depends on resistor, capacitance and inductance. Okay. So, next one depends on the frequency of AC. So, here impedance does depends on. Okay. XL means XL we can write it as a omega L XC 1 divided by omega C. Right. Omega C. Yes. Fine. Next one. Electrical resonance. Electrical resonance means when XL that is equal to XC. Okay. So external frequency is matching with a frequency of a circuit, then we can say it as a resonance. Okay. What are the conditions? For XL that is a omega L that is equal to 1 divided by omega C. So omega square, okay, rearranging the equation LC, and you need omega that will be under square root 1 by LC. This is the resonance condition. When an alternating voltage of a particular frequency is applied to a series LCR circuit, the current in the circuit becomes a maximum. Okay, and phenomena in which is called electrical resonance. Already we have written. This is the condition. Okay, to be resonance. AC circuit said to be resonant when the natural frequency of a circuit is equal to the frequency of applied voltage. For resonance, both L and C must be present. Yes, L and C both are there. Okay, so again here, so with respect to omega, that is 1 divided by under square root LC, and here conditions are there. To be resonant, first XL is equal to XC. Next one, impedance R, impedance minimum, that is Z minimum is equal to R. Circuit behaves as a resistive circuit. Next one, the phase difference between V as well as I is 0. Okay, V as well as I is 0. Angular frequency, that is given by 1 divided by under square LC, and this one frequency, okay, frequency FR. And next one, see, go through the formula once, okay. Average power consumed, PAB, average power consumed becomes a maximum, current becomes a maximum, that I max is equal to V RMS divided by R. Okay, got it? Okay. Okay, now let's move on to the next slide. Derive expression for a resonant. Already we have derived it. Okay, already derived it. What is the resonance condition? Resonance condition, that resonance condition, omega, that is equal to 1 by root LC, where L is a inductor, C is the capacitor. Got it? Z should be minimum. Z should be minimum. Z should be minimum means, what is the formula for that? Z is equal to under square root R square plus XL minus XC whole square. When XL is equal to XC, what happens? This entire term becomes 0. Therefore, Z is equal to R. Okay, Z is equal to R. Z become minimum. Okay, now. So power is nothing but it is the product of V as well as I. Okay, product of V and I, right? So here you can consider PV, P is equal to VRMS, IRMS cos phi, where cos phi is a power factor, where cos phi is a power factor. Power factor. Okay, power factor. Got it? So just you go through this definition. Next one, define power factor. It is the power factor cos phi, that is equal to R divided by Z. It is the ratio of resistance and impedance. Impedance already we know that. Transformer. Transformer means to increase, okay, to increase or decrease, to increase or decrease the voltage. Okay, increase or decrease the voltage is called, okay, transformer. We use transformer. Okay, we use transformer. And here, what is the condition? It is based on electromagnetic induction. Okay, electromagnetic induction, that is a mutual induction. Particularly mutual induction. Okay, principle. Mutual induction. Okay. And here we have a coil, that is the primary coil, and this is the secondary coil. So here primary coil and secondary coil. So what will happen? So your EMF with respect to this primary coil, it is given by, okay, E primary, that is the d phi divided by dt, and with respect to number of turns in a primary coil. And EMF with respect to secondary coil, that is ns d phi divided by dt. So when both are equal, that means if I take a ratio of this EP as well as ES, okay, so what will be having? NP divided by NS, okay. So this is the condition. So this we call it as a turns ratio, okay, turns ratio. Got it? Now, so the same thing, power, if I consider power input, that is equal to power out for ideal case, So here I can write I into ES, okay, I is equal to, okay, primary coil, IP VP, that is equal to IS and VS. And after taking the ratios, IP divided by IS, that is equal to VS divided by VP, and NS divided by Np, okay? Ns divided by Np. This is for ideal transformer, okay? These formulas are very important. Next one. Some energy losses are there. You please go through that, okay? Easy one. Next one. Questions, step up and step down transformer, okay? Step up and step down transformer. So difference, see, output voltage, it is a greater than input voltage. Step up, output voltage is greater than input voltage. Then we can call it as a step up. And step down, output voltage is less than input voltage. That means it is a step down transformer. First point, it is clear. Output current is less than the input current. Okay, output current is less than input current. Okay, but here opposite. Output current is greater than input current. Okay, now the turns ratio, if it is greater than 1, so turns ratio means number of turns in a primary coil, number of turns in a secondary coil. If we take the ratio, it should be greater than 1. Then it indicates a step up transformer. Got it? Okay. Now, in the same way for this. So symbol you can see, step up transformer means number of turns in a primary coil is less than number of turns in a secondary coil. But in case of secondary coil, that is a step down transformer. Here number of a primary coil is greater than number of a secondary coil. Okay, this is the difference between step up as well as step down transformer. Okay, and here you can see the light bulb is rated 100 watt for a 220 volt supply. Find the resistance. So resistance, we know that resistance of the bulb, that is given by V rated square, right? V rated square divided by power rated, okay, P rated. And what is the value of a P? V, that is a 220 into 220 divided by P rated, that is 100. 101010. Get cancel. So 2020 is how much it is? 2020. So 2 to the 4, 2 to the 4 plus 2 to the 4 and 2 to the 4, 4, 8 and 4. Okay. So that is a 484 ohms. So this is the resistance of the bulb. Okay. The second one, you calculate the peak voltage as well as RMS current. Got it? Okay. Yes. Yes, 484. Very good. Very good, Manu. Dinesh, Tanwar, what is the answer? Gogita, what is our answer? And Euphoria, what is the answer for this question? Can you please answer this question? Yes. Okay. Unnati Gupta. Okay. Fine. You'll do it, right? Okay. Now let's move on to the next concept. So sinusoidal voltage of a peak values 283 and frequency 50 Hertz is applied to a series LCR in which R, L, C. Okay. Find impedance. Impedance means that is equal to under square root R square plus XL minus XC whole square, right? So R, we know that. What about L? What about XL? XL is equal to, so omega L, right? What is omega? Omega 50 Hertz, right? 50 Hertz they have given frequency. Okay. So that is given by, okay. So this is a frequency and omega it is given by, okay, 2 pi divided by T, that can be written as a 2 pi F, okay, 2 pi F. Omega that is equal to 2 pi into 50, that is 100 pi, okay. What you have to do is, so omega value, it is 100 pi, okay, and L value, that is 25.48 millihenry, and the capacitor 796 microhenry, okay. So here what you need to do, first to find out XL and then XC, that is 1 divided by omega C. Omega, here you have C, here you have for XL, L you have C, omega here. Okay, after finding this value, substitute in this above equation, you'll be getting the answer. Okay, got it? Okay, now let's move on to the next question. A charged 30 microfarad capacitor is connected to 27 millihenry capacitor. What is the angular frequency of oscillator? Angular frequency, that is omega, that is equal to 1 divided by root LC. Okay. So here 1 divided by charged capacitor they have given. How much it is? 30. 30 microfarad, 10 power minus 6 into L, that is the inductor, 27 into 10 power minus 3. Okay. So after multiplying, okay, after multiplying, how much we get? 27 into 3. So here we are getting 27. Okay. So 27, if we take out, no, it is not possible. That is 87. No, it is not 87. Something missing. 81. Okay. So that means this is 1 divided by 81 into 10 power minus 9. Okay. 81 into 10 power minus 9. So here 30. 30 means 1 0. Right. So here 81 I'll take it out. 81 if I take it out, it will be 9 under square root. It is a 10 power minus 8. If I take it out, 9 into 10 power minus 4. And further simplification, I left with you. Okay, that is a 10 power minus 4. So that is 1 by 9 into 10 power, okay, 10 power plus 4, okay, radians. This is the answer. This is the answer. Got it? Okay, now let's move on to the next question. Electromagnetic waves. Okay, electromagnetic waves. It is a very small chapter. We can complete it in half an hour. Okay, maximum half an hour. After this, we will have a small break. After that, we can continue with the ray optics and wave optics, then dual nature of radiation, and the last 5 chapters within 2 hours. Okay, last 5 chapters within 2 hours. Next, trend analysis, you can go through it. Okay, and deleted topics, you can go through it. First one, displacement current. What is this, a displacement current? See when two capacitor connected, okay, connected to a battery, So this one connect to a battery. When switch is closed, okay, when switch is closed, the current start flowing, okay. So here Maxwell's observed that the current flowing through a wire, we call it as a conduction current, that is IC. This one can be noticed by using, okay, by using a magnetic needle. Why? Current carrying conductor produces a magnetic field around it, so it will deflect. So he concluded that this is a conduction current. The current flowing through a conductor, that is called conduction current. And what he has done is, he took that magnetic needle and placed, okay, in between a parallel plate capacitors. In that time, what happened? It is deflected. You got to know that there is something, okay, there is something. Due to that, that magnetic needle is deflecting, right? Magnetic needle is deflecting. And that is only due to a current, okay, change in electric flux. Change in electric flux, due to that there is a current, okay, there is a current, and that current is called okay, displacement current, ID. So if you define, okay, displacement current, how do you define? The current between two parallel plate capacitors developed due to change in electric flux. That current we call it as a displacement current. Got it? Okay. Now, so this, what is the main cause of displacement current? The time varying electric field. Okay, here time varying electric field. So Maxwell, okay, modified Ampere Circuit Law. So originally PdL, that is equal to mu naught. Okay, this is mu naught I. This is the original one. He modified this equation. You know why? DL, total current. Okay, total current, that is current due to conduction, current due to displacement current. This displacement current, that is due to, you know, change in flux. That is the d phi divided by dt. So again, it is reduced. Okay, this Maxwell's Ampere Circuit Law, it is modified again. BDL, okay, BDL mu naught conduction current plus epsilon naught d phi divided by dt. Okay, next. What is the displacement current? The current which appears in the region in which the electric field is changing with the time is called displacement current, or else you can define the current between two parallel plate capacitor is called a displacement current. And here, what is the need of displacement current? Maxwell's introduced the concept of displacement current to remove the inconsistency in an Ampere Circuit Law. Before, I showed equation that is a BDL that is equal to mu naught I. It is rectified. Okay. Now, next one, what is the conduction current? The current carried in the conductors due to flow of charges is called conduction current. Okay. Important definitions. Distinguish between conduction current as well as displacement current. Conduction current follows Ohm's law. Okay, conduction current follows Ohm's law, where displacement current do not follow Ohm's law. That is the one difference, major difference. Current in the conductor due to flow of charges is called conduction current, and it obeys Ohm's law, where current due to time varying electric field is called displacement current and does not obey Ohm's law. Okay, now next one, Maxwell's equation. Okay, so first one, Gauss law of electrostatic, that is E dot ds is equal to Q divided by epsilon with respect to flux. Okay, next one, Gauss law in a magnetostatics. So that magnetic field due to a closed loop, it is a zero. That indicates the monopole do not exist. Okay, next one, Faraday's law of electromagnetic induction. So I showed induced electric field. Okay, induced electric field, that is with respect to Faraday's first law. Okay. Hello, Kittu, hello. Yes, hi, good evening. Next one, Ampere's Maxwell circuit law is modified, that is mu naught IC plus ID, that is due to conduction current as well as next one, a displacement current. Okay, IC is the conduction current and ID is the displacement current. Got it? Okay. Now next one, electromagnetic waves. Why these electromagnetic waves comes into the picture? That is due to accelerated charges. Okay, that is due to accelerated charges. Now here you can see electromagnetic waves. Waves are radiated by accelerated charges and consist of a time varying transverse. Transverse means oscillation of a waves is perpendicular to the propagation. If it is oscillating, okay, if it is oscillating like this, the motion will be along x-axis. Okay, oscillating along y-axis, motion will be along x-axis. So this nature we call it as a transverse nature. Got it? Okay. And electric and magnetic fields are called electromagnetic waves. Accelerated charges produces electromagnetic waves. Which one produces electromagnetic waves? Accelerated charges produces electromagnetic waves. Important characteristics of this electromagnetic waves. The first one, they are produced by accelerated electric charges or oscillating electric charges. That already we know that. Okay. Next one, they do not require any material medium for their propagation. Like a sound. Sound require Unnati Gupta, sir, drink H2O. Yes, my voice is gone. Okay, my voice is gone. That's fine. Okay, that's fine. No problem. We can continue. Okay. So within 10 or 15 minutes after completing this chapter, I'm taking little break, 10 minutes of a break. Okay. Next one. Electromagnetic waves are transverse in nature. As I told, oscillation of waves along y-axis and propagation of waves along x-axis. So they are perpendicular. So this kind of a nature we call it as a transverse in nature. Longitudinal direction and oscillation will be on the same direction. Okay. For example, sound wave. Oscillation of a particle as well as motion of a wave. It is the same direction. That nature we call it as a longitudinal nature. Next one, the oscillations of E and B are in the same phase. At the same time, they are reaching a maximum point, peak point, and at the same time, they are coming back. Okay. At the same time, they will be oscillating. Okay. I'll show you the diagram. This is how they'll be oscillating. See, for example, this is electric field. Okay. Electric field along x-axis, y-axis. Okay. And magnetic field along z-axis, outward. Okay. This is x-axis. Okay. This is y-axis and magnetic field along z-axis, and motion of propagation of a wave, it is along x-axis. Okay. So how they are moving? Like this. Okay. At the same time, they are becoming minimum and maximum, peak values, minimum values, peak values, minimum values, peak values, and they are moving like this. And this nature we are calling it as a transverse in nature. Got it? Okay. Now this is the diagram of a propagation of a wave. So transverse in nature, how do you represent? Electric field cross magnetic field. Okay. And this gives you a velocity or propagation of a wave. Okay. Now, next one. Transverse nature of electromagnetic waves. Electric field and magnetic field in electromagnetic waves are in same phase. Speed of electromagnetic wave is given by, okay, speed of electromagnetic wave, it is given by E naught divided by B naught, or else E naught that is equal to B naught C, okay, where you can see this C, it is also given by, okay, this C is also given by, okay, mu naught and epsilon naught. Still you will be getting that value is 3 into 10 power 8 meter per second. Getting your point? Okay. So all these are very important, and here they have given meaning of the symbols. That's just to go through it. Okay. Now next one. There are some important characteristics of electromagnetic waves. Important characteristics. The first one, energy in electromagnetic waves is divided on average equally between electric and magnetic field. Yes, energy associated with the electromagnetic waves, this is with respect to electric field and this is with respect to magnetic field. Okay, with respect to magnetic field. So it is a magnetic field. Okay, this is a magnetic field. This is with respect to magnetic field, and this one, it is respected to electric field. Okay, that is of epsilon naught E square, and with respect to magnetic field, that is 1 divided by 2 mu naught B square. Okay, now next one. Electromagnetic waves also carry momentum and energy. Linear momentum delivered to the surface by the electromagnetic wave is P is equal to U by C. What is that U? It is the energy, and C is the speed of light. Okay. Now, where U is the total energy transmitted by the electromagnetic waves, and C is the speed of electromagnetic wave. Since it has a momentum on an electromagnetic wave, also exerts a pressure called radiation pressure. Got it? Okay. Now, next one. Last 2 points. That is, electromagnetic waves are not deflected by electric and magnetic field. Next one, electromagnetic waves obey the principle of superposition. They show the properties of reflection, refraction, and infraction, diffraction, and polarization. Okay, these are the important characteristics of AC. Not AC. It is the electromagnetic waves. Okay, now. So you can see the electromagnetic spectrum. I'll tell you a simple statement to remember the order of electromagnetic waves. Okay, simple statement. Okay, Raju's mother is visiting Uncle Xavier's garden. Okay, first letter of each word. Okay, first letter R, M, I, V, U, X, G. What does it mean? R means radio, M means micro, I means current, infrared, V means visible, U means ultraviolet, X means X-ray, G means a gamma ray. Okay, so these are degrees in wavelength, and opposite increase in frequency. Got it? In the same way. Okay, so these are increase in order. Now, so you have to go through all these. Okay, radio wave, microwave, infrared. This is in degrees in wavelength. Okay, degrees in wavelength. So same order. Raju's mother is visiting. Okay, visible. Okay, visible Uncle's Xavier's garden. Okay, this is the way you have to remember that is in a degrees in order. It is greater than 0.1 meter. Okay, it is 0.1 meter to 1 millimeter. See, degrees in order. So in examination, they'll be asked you to, Unnati Gupta sir, we have to learn the frequency and wavelength too. Please suggest. No. No need to learn the values. Okay, no need to learn that values. If they give you a frequency and ask you to find out a wavelength, which formula we need to use? This formula you have to use. Okay, C that is equal to F lambda. Okay, use this relation and C. I hope you know that what is the value of this. And c, that is the speed of electromagnetic waves, that is given by c is equal to 3 into 10 power 8 meter per second. I hope it is clear. I hope it is clear, right? Unnati Gupta? Okay. Okay. Yes, yes. Okay. Very good, very good. Okay. Fine. Now, let's move on to some important applications of these electromagnetic waves. First one, radio waves. Radio waves. You see, radio waves are electromagnetic waves produced by accelerated motion of a charges in a conducting wire. Uses, where do we use this? They are used in a radio and communication system. Okay. Next one, higher frequency up to 54 megahertz to, okay, for a shortwave bands. That is, this is the first one, and second one. Third one, cellular phones used radio waves. Okay, whatever we are using mobiles, right? Now you are watching our live marathon session. Okay, in a mobile. So what are the electromagnetic waves used in that particular mobile means? That is a radio waves for a communication purpose. Got it? Okay. Now, next one, that is the microwaves. Give any two uses of a microwaves. These are electromagnetic waves so produced by electrical oscillations in LC circuit. Okay, how does it produces and uses they have given. Microwaves are used in a radar system. Okay, radar system used aircraft navigation, because we use a term as a radar. Okay, radar. So here, radio detection and ranging. Okay, radio detection and ranging. Radio detection and ranging, like sonar. If you want to, enemy ships, okay, underwater, if you want to calculate, determine any object inside water, you can use a sonar. That is the sound navigation and ranging. But in the sky, how do you detect the enemy's flights or flying object? Using radar. Okay, got it? Okay, now microwaves are used in micro ovens. That this similarity already everybody knows. We are using at homes, bakeries, in restaurants, everywhere this micro ovens are used. Okay, now next one, infrared radiation. Infrared waves. Give any two uses of IR. Infrared rays are produced by hot bodies. Okay, so like if you see, our earth temperature keep on increasing, right? Keep on increasing. What is the reason behind it? Means the reason being that is infrared radiation. Whatever the radiation is reaching our earth, it should go back, reflect back. But these infrared radiation, it is not allowing, means not allowing that radiation to escape from earth's surface. That is the reason our earth is getting hotter day by day. Okay, Unnati Gupta, very good. Remote controls and to see through fog. That is one more applications. Okay, so in remotes, any kind of remotes. Okay, maybe AC remote, maybe TV remote, maybe any other electronic device remote. So in that remotes, infrared waves are used. Okay, because it can penetrate for a long distance. Okay, IR. So here applications you can see waves. Okay, infrared waves are from the sun, keep earth warm and hence helps sustain life on the earth. They are treated as thermal rays. Okay, as Unnati Gupta said, heat waves also we can see. Okay, heat waves. Very good, very good. Okay, next one. IR detectors are used in earth satellites both for military purpose and to observe the growth of crops. So in agriculture field also these IR waves are used. Okay. Next one, electronic devices also emit infrared radiation, are used in the remote switches of house, electronic systems such as TV sets and video recorders, etc. Okay. Now mention uses of UV, ultraviolet waves. The first one, it is used, okay, highly focused UV rays are used in eye surgery. Where do we use? Eye surgery. Next one, UV lamps are used in kill germs in a water purifier. Okay, so this one is very important. Okay, next one, I think this is the last one. Okay, yes, X-rays. X-rays are used as a diagnostic tool in a medicine and as treatment for a certain forms of cancer, and used in study of a structure of a crystals. X-ray is also used in, okay, to identify any fractures in the body, okay, bone fractures in the body. That is one more application, okay. Now, so let's move on to the I'll start from a nucleus, okay, from a nucleus, and I'll come back to the ray optics, okay. Let's finish it off small chapters. Yes, atoms. So atoms will finish off these two chapters. Okay, it is a very small chapters. After that, we can take the break. Okay, 8:30 we can take the break. Okay. After that, we can move on to the ray optics, wave optics, then dual nature of radiation and matter. Okay. Now let's start with this atoms. So here atoms. Alpha particle scattering experiment by Rutherford. Okay. It is a completely theory based. Just listen. What I read is just listen. Okay. Nothing else. Just listen. Okay. Unnati Gupta, correct answer. Okay. Very good. Now, experimental arrangement. A narrow beam of alpha particle from radioactive source, okay, bismuth 21483 was allowed to fall on a thin gold foil of a thickness 2.1 into 10 power minus 7 meter. The scattered alpha particles were observed through a rotatable detector, means microscope, okay, consisting of a zinc sulfide screen and a microscope. The alpha particles striking the screen produces a light flashes, which could be observed through the microscope as shown in the figure. Where is that figure? You can see here. Yes, this is the arrangement. Okay. And what are the observations from this particular experiment? The graph of a total number of alpha particles scattered and theta of the scattering angle theta as shown in the graph leads to the following observation. What are the observation? Most of the alpha particles pass straight through the foil without suffering any deviation. Means when alpha particle is shooted towards this thin gold foil, so almost every particle have moved in a straight path. Only 0.014%. Okay, very less number of particles it is a deviated. Okay, first observation. Next one. Only about 0.14% of alpha particles scattered at an angle more than 1 degree. Okay, 1 degree. About 1 in 8,000 deflected by more than 90 degree. Only one. Okay, out of 8,000, only one. Okay, only one particle is deflected by 90 degree. What about others? They moved in a straight path. Okay, now let's move on to the next observation. This is the graphical observation. Explanation of this experiment. Since most of the alpha particles emerges straight without any deviation, the atom is almost empty. What is the conclusions, okay, of this particular experiment? Okay, we got to know the atom is completely or almost empty. Second one, the large scattering is due to electrostatic force of repulsion between alpha particles and the entire positive charges of the atom concentrated in a small region called a nucleus. Okay, next one. Impact parameter. What is this impact parameter? When it is coming towards the nucleus, okay, alpha particle coming towards the nucleus, due to Coulomb force, what happens? It is slightly moving or away from this particular direction. Okay. Yes, atom is mostly hollow inside. There is a concentric of positive charges, 3 thin positive. This positive part of a nucleus, different foil have a different alpha deflections. Hence, we can say they have a different nucleus. Exactly. Very good. Okay. And impact parameter is the perpendicular distance between initial velocity vector of the alpha particle and center of the nucleus when the particle is finite distance. See, this is impact parameter, that is a B. Okay, impact parameter, and it is given by 1 divided by 4 pi Z E square, that is atomic number, E square divided by kinetic energy cot phi divided by 2. Okay. Here it is the angle. Okay. Here it is the angle. Here it is the angle. Okay. Now, next one. Distance of a closest approach. When an alpha particle approaches a nucleus of a charge, due to electrostatic repulsion, the kinetic energy decreases and the potential energy increases. At the particular distance called a distance of a closest approach, the entire kinetic energy is converted into potential energy. The relation here, you can go through this. Okay. Fine. Now, here R naught, that is the closest distance of approach. This is R naught, denominator. Okay. Now, next one, Rutherford atomic model. So, first one, it is a alpha scattering. Here, atomic model. Okay. Now, here you can see h divided by 2 pi. Okay. So, please concentrate. Okay, please concentrate. Rutherford's atomic model based on alpha scattering. Okay, this is alpha scattering experiment. Rutherford proposed a model for atom according to that. Okay, from alpha particle scattering. He has given atomic model theory. So in that, the first point, what he has concluded by that experiment, atom is a sphere of a size 10 power minus 10 meter. The entire positive charge and most of the mass is concentrated in a small region and its center is called a nucleus where proton and neutron is present. Okay, and the size of the nucleus is about a 10 power minus 15 meter to 10 power minus 14. It is about a 10 power 4 to 10 power 5 smaller than the size of the atom. Thus almost, okay, thus atom is almost empty. Okay, thus electrons revolve around the nucleus in a circular orbit just as a planets revolve around the sun. Okay, we say that electron revolves around a what is that, center of atom, that is called a nucleus, right, by this model only. Okay, now next one, Bohr's postulates of hydrogen atom. So first postulates, an electron in an atom revolve around the nucleus in a certain permitted orbits. Okay, so Rutherford say that electrons revolving around the nucleus, but he suggested that in a particular permitted orbit, okay, that orbits we call it as a stationary orbits. An electron in a stationary orbit does not radiate energy. Okay, so in that particular orbit does not radiate energy. First postulates. Second one, an electron can revolve around the nucleus only in those orbits for which angular momentum is integral multiple of, okay, integral multiple of, okay, h divided by 2 pi. Angular momentum, it is given by nh divided by 2 pi, and centripetal, this one is a angular momentum and nh divided by 2 pi. L or mvr is equal to nh divided by 2 pi. Any one of them you can write. Okay, L is nothing but mvr. Got it? Okay. Now, next one, where h is a Planck's constant. Next one, an atom can radiate energy only when the electron undergo transition from orbit of higher energy level, that is EI, to orbit of lower energy level, that is EF. Okay, EI minus EF. Here is some. Okay, now this h nu, that is equal to EI minus EF. Nu is equal to EI minus EH. These are the formulas. Okay, please remember. Okay, now next one, limitation of a Bohr's theory. Bohr's theory states that, okay, theory is applicable only for hydrogen and hydrogen-like atoms. Okay, it is only applicable for hydrogen and hydrogen-like atoms. Now, second one, these are the limitations. Okay, theory fails to explain fine structure of a spectral line. Okay, series. Okay, series are there, no? That one. Okay, next one, Bohr's theory fails to explain the relative intensity of a spectral line. Okay, next one, relativistic variation of a mass is not taken into account. These are the limitations. Now, radius and velocity and energy in an nth orbit. So, centripetal force, it is given by mv square divided by r, and Coulomb force that is given by, okay, that is given by K, okay, K Z E divided by R square, okay. So here I can write it as a K Z E square divided by R square. Got it? So in place of, in place of R get cancelled. So in place of R, okay, in place of R, I can write this one as K Z E square divided by, okay, divided by, cross multiply this mv square, okay. So or else you can replace this one, okay, you can replace this one. So mvr, okay, mvr, okay, nh divided by 2 pi, nh divided by 2 pi into mv, okay. So here you can replace with r, here r, okay, still you'll be getting a radius, okay. Got it? Radius also you'll be getting. Any doubt? Fine. Next one, energy of electrons in hydrogen atom, Z is equal to 1, energy. So here you can see this one first state, and this is a second state, and this is third state, and this is fourth state, and so on. This one continuum and continuous, infinity, up to infinity it will go, okay. Now here hydrogen emission spectrum consists of a 5 series. The first one Lyman series, next one Balmer series, next one bracket series, P-Fund and Ampere, okay. Reason, where do we find all these series? UV visible, except that everything is in IR only, okay. N1 and N2, okay. If I consider N1, what is the N1 value? It is a 1, and remaining N2, 2, 3, 4 and so on. And here N2, sorry, N1 only. So N1 is equal to 2, N1 is equal to 3, N1 is equal to 4, N1 is equal to 5, N1 is equal to 6 and so on, okay. N2 that is equal to 3, 4, 5 and so on, 4, 5, 6 so on, and 5, 6, 7 and so on, and this one 6, 7, 8 and so on. Here N3 only, N2, okay. Here N2 only, okay. This is N2 and this is also N2. That is 7, 8, 9 and so on. Got it? Okay. Fine. Now, so spectrum, emission of a spectrum corresponding to Lyman, Balmer and Paschen series, okay. Please go through that, okay. Please go through that. So like this, okay. So spectral lines. Next one, nuclei, okay. So I'll take a small break, okay. So I'll take a small break. Got it? 15 minutes, 15 minutes break I'll take, okay. So after 15 minutes, we can continue with our session. We can continue with our session. Welcome back to the session. So, yes, is my voice is audible? Is my voice is audible? Once again. Yes, dear students. Okay, 1 second. I'll be coming. So, file is still loading. Okay, okay. Yes. So, still file is loading. So, we have to wait for some time. Okay. So, we have almost 1 hour 30 minutes. Okay. So, 1 hour 30 minutes. So, I know a few of the topics I may not complete. So, I'll tell you what to learn. Okay. Because, you know, the physics syllabus is vast. Okay. Vast syllabus. It has a lot of content. Okay. Now, thank you. Christina, very thank you. Very thank you. Okay. Fine. Okay. So, a nuclei. So just I'll tell you the important points related to nuclei. Okay. So first on composition of a nucleus. Okay. Composition. So this nucleus is contains a number of protons and number of neutrons. Okay. So generally we call it as a nucleons. We call it as a nucleons. And presentation of any element, it is given by, okay, AZ number. Okay. This is a Z and A. This is atomic number, okay, atomic number, and this is a mass number, okay. This is a mass number. So this gives you number of protons, okay, number of protons, and this one gives you a difference of A minus Z, that is the neutrons. Got it? Okay. So this is the composition of this nucleus, okay, and electrons will be revolving around it, okay. Electrons will be revolving around it, and we are concentrating on this particular a reason, that is a nucleus. Okay, now let's get started. So first one, what is atomic number? What is mass number of element? So when we represent an element, that is given by A and Z. Okay, so this Z indicates a, this is a atomic number, A indicates a mass number. So this Z, it is a number of protons, where A is the mass number. Okay, it is the number of protons present in the nucleus of an atom, where this mass number of element, it is the total number of protons and neutrons. Okay, it is the total number of protons and neutrons, that is Z plus N. Okay, Z plus N, right? Neutrons present in the nucleus of an atom. Got it? Next one. So isotopes, isobars, and isotones. See here, iso means same, topes means number of protons, okay, number of protons. Isotope and isobars, same, bar means mass, okay. So isobars, same number of mass number, and here same number of atomic number. Isotones, neutrons. Isomers, it is not so important, please concentrate on first, second and third, okay. Nuclei with the same atomic number, for example, X1, okay, XA1, Z, and same number, right? Same number. Element is also same, right? Nuclei with the same atomic number but different mass number, okay, same atomic number but a different mass number is called isotopes. What does it mean? Different mass number, that is Z1, XA, Z2. See, A numbers are same, right? So this one we call it as a isotopes. Got it? Okay. Now, Unnati Gupta. Very good. Okay. Fine. Now, next one, nuclei with the same mass number but different atomic number. What does it mean? Different element also, okay. For example, this one, if I consider this is A1, okay, this is A1, this is Z, and Y, this is Z, and this is A2. Say different elements having same mass number but different atomic number. This one we call it as a isobars. Got it? Easier way. Okay. Now, third one, nuclei having same number of neutrons are called isotones. See, difference of this, okay, difference of A minus Z, okay, neutrons, okay, same number of neutrons you will be getting. So that one we call it as a isotones, okay, isotones. And isomers, what does mean it? Isotones, it is done. And isomers, nuclei having same atomic number and mass number, difference only in their energy states are isomers. Excited state, ground state, okay. Correct man, my name is Ashok, okay. We have started session in the morning, 11 o'clock, okay, in the morning, right? Now, next one. So, properties of a nucleus. What is the size? What is the volume? What is the density of a nucleus? Size, if you consider, size of a nucleus, it is given by, okay, it is given by R is equal to R naught, okay, this is the constant, R naught, A power 1 by 3. That means R is directly proportional to the atomic mass number, okay, mass number, not atomic, it is a mass number. R is proportionally constant. The value of R naught, that is 1.2 into 10 power minus 15 meter. And volume, if we talk about the volume of a nucleus, we consider as a sphere, okay. So what is the volume of a sphere? That is a 4 by 3 pi r cube, volume of the nucleus, okay. Density. So when you talk about density, nuclear density, okay, generally it is not just density, it is a nuclear density. If we consider a nucleus, okay, so if we consider a nucleus, here number of protons as well as number of neutrons will be presented, right? Number of protons as well as number of neutrons will be presented. And this A indicates, okay, atomic number, that is a number of, what is this M? That is the mass of a proton or a neutron. And here, this 4 by 3 pi r cube into A. Okay, so here you can see A and A get cancelled. Remaining, this 3 will go to the numerator. So here 3m divided by 4 pi r cube. And here you can observe one thing, that is, it is independent of A, that is atomic number. Got it? Okay. So next one, nuclear density, okay. Nuclear density, it is independent of A and Z. A or Z, okay. Now, next one, nuclear charge. So nuclear charge, the nucleus of an atom consists of a positively charged proton and electrically neutral neutrons, okay. In the nucleus, this proton as well as the neutrons are bounded into the nucleus, okay, bound, okay. Thus, the charge of the nucleus is only due to the presence of a proton, because neutron is a chargeless particle. If we say nucleus is a positively charged, that means it is due to a presence of a protons. Proton is a positively charged particle. Got it? And the charge on a protons, we can consider it is a 1.6 into 10 power minus 19 Coulomb. Got it? Okay. And the fourth point, it is done. And the fifth point, nuclear mass. Nuclear mass is the sum of masses of all the photons, okay, protons and neutrons present in the nucleus of an atom. If Z is the atomic number and A is the mass number of an atom, then nuclear mass it is given by, okay, nuclear mass is given by ZMP, means atomic number multiplied by mass of the proton plus the difference of A minus Z, okay, difference of A and Z into mass of the neutron, okay, where MP is the rest mass of the proton, where Mn is the rest mass of the neutron. These are the properties of a nucleus, okay. Now, Einstein mass energy relation, what does it mean? IE is equal to mc square. Okay, by this equation, we can conclude that mass can be converted into energy and vice versa. Okay, it is multiplied with the speed of light. Got it? Yes. Euphoria proton is a yes. H plus ion. Okay, good. Very good. Okay, now according to this Einstein mass energy relation, mass and energy are interconvertible, that is the mass can be converted into energy and energy can be converted into mass. Okay, so that is given by, okay, that is given by this equation, E is equal to mc square. This one we call it as a mass energy equation. Got it? Okay, example you can see nuclear fusion and nuclear fusion. Okay, now mass defect. Mass defect, what does it mean? The difference between the sum of the masses of a nucleons, that is the protons and the neutrons, forming a stable nucleus, and the rest mass of a nucleus is called mass of the defect. Okay, mass defect. Okay, so it is given by mass defect delta M. Okay, delta M, same nuclear mass minus this M. Okay, so done. Where Z is the atomic number, A is the mass number, MP is the mass of the proton, Mn is the mass of neutron, M is the rest mass of a nucleus. Okay, capital letter M is a mass of the nucleus, entire mass of the nucleus. Okay, got it? Okay, and next one, mass nuclear binding energy, means this neutron as well as the proton bonded, right? If you want to separate them, okay, if you want to separate them, and how much energy required to separate them? Okay, so binding energy, first of all, what is the binding energy? The energy, okay, is, okay, energy required to separate the nucleus, bonded nucleons. Nucleons means proton as well as neutron as well as proton, right? So if you want to separate, how much energy it is required? So that is a binding energy. Or else vice versa also we can say, what is that? Nuclear binding energy is the energy required to bind the nucleons, okay, required to bind the nucleons to form stable nucleus, okay, to form stable nucleus. It is also defined as energy required to break the nucleus into its constituents nucleons. Nucleons means proton as well as neutron, to separate them. And nuclear binding energy, it is given by delta M c square. And delta M is the mass defect and C is the speed of light. So small concepts are there in a nucleus, okay, nucleus. So you can go through it. Okay, now next one, binding energy per nucleons. So what is the energy required to bind one nucleus? Means nucleons. Nucleons means proton and neutron. So what is the specific binding energy? How much it is required to bind those nucleons? Okay, is called binding energy per nucleons. Okay, so here you can see the ratio of a binding energy of the nucleus to the number of nucleons, means for each nucleons how much energy it is required to bind. Simple. Okay, and it is given by, okay, it is given by binding energy, okay, binding energy per nucleon, EBN, binding energy per nucleon, is given by binding energy per A, means atomic number, okay, A is the mass, sorry, that is atomic mass, sorry, here A is the mass number, okay, A is the mass number. Got it? Now next one, nuclear forces. What are the nuclear forces? Mention the characteristics of the nuclear forces. The strong attractive force which binds the nucleons together is called nuclear force. Okay, and you will be having a question, sir, why nucleons bound together? Because of a nuclear forces. Okay, proton and neutron, why they are bounded? Okay, derivation is not required. Okay, derivation is not required. So why they are bounded? Because of a force, that is a nuclear force. Got it? Now next one, characteristic properties of a nuclear forces. Long range, short range. Okay, first one, it is a non-central. Next one, it is the strongest force in nature out of 4 fundamental forces. Next one, it is an extremely short range. It is not a long range. It is a very short range. Okay, of order of 1 Fermi meter. 2, that is a 10 power minus 15. Okay, now next one, it is a strong attractive force, but when the distance separation is about 0.8 Fermi, okay, the attractive force becomes suddenly repulsive. Okay, this is the nature, property of a nuclear force. Okay, and the next one, it is charge independent. Okay, charge independent forces. If a nuclear force between any two nucleons remains the same, okay, maybe between proton-proton, maybe between proton-neutron, maybe between neutron-neutron, represents nuclear force between two protons. Okay, two protons are proton-neutron and two neutrons. Okay, respectively. Then FPP means a force between proton-proton, force between proton-neutron, force between neutron-neutron, all are equal. Got it? Okay. Now, next one. Next important point. Nuclear force has a property of a saturation. And the next one, it is a spin-dependent force. Already you have learned it, right? Nuclear forces are exchange force. Okay. And the next one, semiconductor electronics. Okay. Semiconductor electronics. So, semiconductor electronics. So, first of all, the material based on, okay, conductivity, we have a 3 types, right? The first one, conductors. Second one, insulator. Third one, semiconductors. And what about semiconductor? Conductor means the material which conducts electricity, or else the material which, what do you say? The material allows electricity pass through them, right? Insulator, they do not allow electricity to pass through them. So simple. And what about this semiconductor? The semiconductors are material false or resistivity or conductivity between conductors as well as insulators. Okay, these are called semiconductors, and this is based on conductivity. This conductivity property used in semiconductors. Okay, conductivity property. So then, based on energy gap, okay, based on energy gap also, this conductor, semiconductor as well as insulator divided based on energy gap. Okay, conduction band and valency band. Okay, let's see. Okay, now next one. So here, semiconductor electronics. First one is the semiconductors. What are electronic devices? Okay, what are electronic devices? It is the device in which electrons' motion is controlled. Okay, electrons' motions are controlled. Is called electronic devices. Okay, like rectifier, off wave, full wave rectifier. Explain the origin of energy bands. Okay, so energy, okay, consider n atoms, okay, of an element is separated by large distance. Electrons present in one atom does not interact with the neighboring atom. But if the atoms are brought closer, electrons present in one atom interact with other atoms. Energy level of each electron splits into number of closely spaced energy levels. These are discrete energy levels of the electron is called as energy band. Okay, now here you define valence band as well as a conduction band and energy gap. Okay, so here it is based on energy gap. Okay, so here again we have 3 types of material. I'll show them. Valence band, energy bands which are completely filled at a 0 Kelvin. Okay, valence band, energy bands which are completely filled at a 0 Kelvin are called valence bands. Okay, conduction band, energy band above the valence band is called conduction band, and conduction band may be empty or partially filled. Energy gap, the energy gap between the top valence band and bottom conduction band is called energy gap. Okay, I'll explain it in detail. Okay, I'll explain in the next slide. Okay, what is conduction band, what is valence band, what is energy gap between, right? Classification of material. First one, conductors. Okay, first one, conductors. Next one, insulators. Insulators. Okay, insulators. And the third one, that is a semiconductors. Semiconductors. Right? So already we know that based on energy gap. Okay, energy band. So here I'll make a, this is conduction band. Okay, this is conduction band. This is conduction band CB, and this one, this is a valence band. Okay, so this is a valence band VB. Okay, now here what happens is this conduction band as well as valence band are are, here you can see, mixed up, okay? So this one we call it as a conductors, okay? Conductors, okay, closely packed. Now here, so let's consider this is conduction band, okay? This is conduction band, and this is a valence band, okay? Valence band. And here there is a gap, right? There is a gap. So this gap we call it as a energy gap or else a forbidden gap, okay? So here the Eg, okay, it is nothing, it is a 0. And here you can see, consider this is for conductor, and if we consider you know, in semiconductors, okay, semiconductors, if we consider semiconductors, here you can see, okay, here you can see this energy gap, okay, this energy gap will be energy gap less than 3 electron volt. So or else this energy gap is nearly equal to electron volt, nearly equal to 1 electron volt, okay. Nitin Sharma, okay, so it is you know, instruction is medium of instruction, it is English, okay, don't mind. Now, so last one, that is the insulators, okay, insulators, okay, insulators. So here this is conduction band, and this one valence band. This is conduction band and this is valence band. And here energy gap, okay, energy gap, it is greater than 3 electron volt. It is greater than 3 electron volt, greater than 3 electron volt. So this is a forbidden energy gap, okay, energy gap for conductors, insulators as well as semiconductors, right? Next one, let's move on to the concept. On the basis of energy band diagram, distinguish between conductors, insulators and semiconductors. The same thing I have explained in the previous slide, okay, you can go through it. Next one, so same that I have explained in the previous slide, that is semiconductors. Give an example. Semiconductor is a solid, okay, having conductivity between that of conductors and insulator, okay. The simple definition is enough, okay, simple definition is enough, conductor as well as insulator. And example, if you see, germanium as well as a silicon, germanium as well as a silicon, okay, germanium as well as silicon. Next, concept of holes. Concept of holes means, for example, if I consider a silicon, silicon is, okay, silicon is group 14 elements, right? Group 14 element, okay, group 14 element have 4 free electrons, 4 valence electrons or free electrons, okay, valence electrons, okay, valence electrons. So this can be represented by, okay, this can be represented by like this, okay, 4 valence electrons. And here just I'll show you example, okay, what is the concept of holes, what is the concept of holes, okay. Now here you see, for example, here electrons are there, okay, free electrons are there. Due to external energy, these electrons gain sufficient energy and come out, okay. So when electron comes out of this location, this empty location, we call it as a hole. It acts as a positive charge, okay, this acts as a positive charge. And seeing this empty space, this electron will jump and occupy this space, and this hole again created, this electron will come and occupy this space. This is what concept of holes, okay, acts as a positive, but it is not a positive charge, okay, it is acts as a positive. Got it? Now let's move to the next concept, that is types of a semiconductor. So semiconductor, there are two important semiconductor, that is intrinsic and extrinsic, okay, intrinsic as well as extrinsic. So this intrinsic semiconductor, it is a pure semiconductors, no doping, nothing. And this one, impure semiconductors, okay, extrinsic semiconductors are impure semiconductors. Why? Because of doping, okay, because of doping, we can change the a conductivity of semiconductors. Okay. Now, based on this doping, here we have two types of extrinsic semiconductor, that is the N type as well as a P type. Okay, P type and N type. Got it? And P type. So P type, when group 13 elements, okay, the doped this P type conductors with a group 13 elements. Here, what happens? Here, 3 free electrons will be presented. Okay, 3 free electrons. And this P type, okay, this N type doped with group 15 elements. Here, how many free electrons? 3. Here, 5. Okay, excess of electrons. Here, excess deficiency of electrons. So, these are type of material doping with a P type as well as N type. Got it? And here you can see the differences. Okay, differences we can see. Intrinsic as well as extrinsic semiconductor. It is a semiconductor in the pure form. Okay, and the second one, it is the pure semiconductor doped with a suitable impurity. Electrons and holes are equal. That is a pure semiconductor. Electrons and holes are equal. In this case, electrons and holes are unequal. And conductivity can be increased with the temperature. Conductivity can increase with the temperature and dopant. Okay, dopant. Right? Next. Which of the 3 different types of a compound semiconductors? So, organic, inorganic, organic polymers. Okay, just to go through it, it is not so important. Okay, extra. Next. What do you mean by doping? Adding impurities, we call it as a doping. Example, okay, example if I consider, okay, group 13 elements, boron, group 15 elements, that is a phosphorus, okay, example for doping, okay. Now, process of adding impurities to intrinsic semiconductor. Extrinsic should be right. 1 second, let me check. Extrinsic semiconductors. Okay, so it is a intrinsic semiconductor. Doping with a dopant means that becomes extrinsic semiconductor. Pure become impure. So it is an extrinsic semiconductor. Okay. Now, next one. P-type semiconductor, already I have discussed. Okay, let me, P-type as well as N-type semiconductor. It is formed doping germanium with a trivalent, okay, trivalent impurities. And here, pentavalent, okay, N-type semiconductors are doped with a pentavalent impurities. And major charge carriers are holes, because group 13 elements have a 3 free electrons, but silicon has a 4 electrons. So 1 electron is less, right? So hence holes are created. Therefore, majority holes will be there in P-type. In case of N-type, group 15 elements are doped with a N-type semiconductor. So 1 electron is more. Therefore, majority charge carriers are electrons. Next one, minority charge carriers. In this case, if holes are more, electrons will be less. And in this case, electrons more, holes will be less. Minority. Less number of quantities, we can call it as a minorities. Excess of numbers, we can call it as a, majorities. Okay. Now, last one, mobility of a majority charge carriers is less. Mobility of a majority charge carrier is high. Okay. Now, 3 points is enough. Okay. Acceptor impurities, here donor impurity. Okay. Acceptor, why? Because of holes. Donor, because 1 excess of electrons. Because of 1 excess of electron. Because it is a group 15 element. Okay, 5 valence, pentavalence electrons. Okay, pentavalent. Energy level of a trivalent impurity just above the valence band, and here energy of a pentavalent impurity just below the conduction band. Okay, so next one, P-type junction is made. Okay, P-type junction when it is made. Okay, so this is made up of a boron. Okay, boron along with a positive holes. Round means holes. Okay, boron. This is a P-type. Okay, all right. Okay, and here phosphorus, and here it is a positive. okay, phosphorus, so this is holes, and here electrons you can consider, okay. So this one you can consider it as a, okay, phosphorus, phosphorus, and phosphorus. So what will happen is, this is a p-type region, okay, this is a p-type, and this is n-type, okay, n-type. So what happens is, electrons start flow from or n-type to p-type. So this electron we call it as a diffusion current without any source, okay, without bias. Without any bias means unbiased condition, electrons are moving from n-type to p-type. That current we call it as a diffusion current, okay. So due to this diffusion current, so here what will happen? So negative to positive means here electric field will be developed. Due to this electric field, so these electrons will not move, okay. So that we call it as a potential barrier. It stops the flow of electrons, or else carriers, means charge carriers, okay, potential barrier. So this is how a potential barrier develops, and this one we call it as a depletion region, okay. This one we call it as a depletion region. Next, so when p-n junction is made, so this is how it looks like, okay. When it is a biased, this is the condition when it is a biased. What is diffusion current in a p-n junction diode? In an unbiased junction, current due to diffusion of a majority charge carriers. Majority charge carriers means electrons. Carriers across the junction is called diffusion current, okay. Diffusion current. Next one. What is drift current? See, when the motion of a charge carriers due to electric field, after electric field induced, the electrons means the charge carriers will flow from p type to n type. So that current we are calling it as a drift current, okay. They are not moving towards one region to another one. It will drift. They are trying to move, but due to electric field, they are coming back. So that electric current we call it as a drift current, okay. Now, what is barrier potential in a semiconductors? Potential developed across the junction due to diffusion of a charge carriers is called potential barrier, okay. Barrier potential also you can see. What is the depletion region in a semiconductor diode? The region containing dipoles and completely. Dipoles means two poles, okay. That is a negative as well as positive. That is a phosphorus as well as a boron, okay. Deplete of a mobile charge carriers is called depletion region, right? Next one. So 1 marks definitions, okay. 1 definition, I mean 1 mark definitions. To make a flow of a constant current by applying external battery to make a junction diode, okay. So here, this is a positive terminal, this is a negative terminal. If a positive terminal, okay, if a positive terminal connected to positive terminal of a battery, then it is called a forward bias. Positive terminal of the battery is connected to p-type region, okay, p-type region. This is a p-type region, okay. This is a p-type and this is n-type. If a positive terminal connected to this p-type region, then the diode is said to be forward biased, okay. Next one, negative. If terminal of a battery, negative terminal of a battery, if it is connected, okay, negative terminal, so it is a forward bias and it is a reverse bias. Simple, okay. And it is not not so important with respect to n region, okay. Now this is the same presentation, okay, or symbolically. Now, when p-n junction is said to be unbiased, what does it mean? A p-n junction is said to be unbiased when no external potential is applied across the junction, okay. So said to be unbiased. So when there is no battery, okay, when there is no battery connected to a diode, we can call it as a unbiased, okay. If the battery is connected to the diode, then it is a biased. Got it? Okay. Now, next one, when is a p-n junction said to be forward biased? Okay, when is a p-n junction said to be forward biased? Just now I said, if the positive terminal of a battery is connected to a p-type region or p-type end, we can call it as a forward biased, okay. p-n junction is said to be forward biased when p region is connected to positive terminal and region which is connected to negative, okay, and n region which is connected to negative terminal of a external battery. Now, next one, discuss the detailed forward biasing of a p-n junction. Just go through it, you will be getting the answer, okay. Now, so same what I have explained, the same thing, okay, in a wording format, okay. Now, so applications, that is half wave rectifier as well as a full wave rectifier is there, okay. Let's see that also. Half wave rectifier as well as full wave rectifier. Applications. What is a rectifier? The process of converting AC into DC is called, okay, rectifier. Here we have two types, half wave rectifier and full wave rectifier. So you see, the process of converting AC into DC is called rectifier. It is a process or a device which converting AC into DC. We call it as a rectifier. Okay. Now, next one, behavior of a diode. Behavior of a diodes in a circuit. Forward bias. Okay. If it is an ideal case, okay, it is an ideal case. Ideal diodes cannot exist. Okay, it is not exist. Okay. Now, next one, ideal case if we consider, if it is a forward bias, acts as a short circuit, means just a wire. And if it is a reverse bias, acts as an open circuit in both real case as well as ideal case. Okay, real case as well as ideal case. Next, real case, okay, real case diodes made of silicon and germanium. Okay, forward bias acts as a opposing battery and reverse bias acts as an open circuit. Still, it is a open circuit. Got it? Okay. Now, next one, half wave rectifier. What does it mean? So, if there is a wave, okay, if there is a wave, let me consider example. If it is a wave, okay, half wave means only for certain wave, half of the wave, it will be operating. When a current flows through the rectifier circuit only during one of input of AC, the rectifier is called half wave rectifier. See, half wave, from here to here it is operating, from here to here it is operating, this is not operating, okay, and here to here it is operating. Okay, this we call it as a half wave rectifier. Got it? Okay. Now, next one, with a neat circuit diagram, explain the working of half wave rectifier, indicate the waveforms, waveform of input and output voltage. See, this one is a coil, okay, this one is a coil. So this one acts as this part, okay, this part acts as a transformer, okay, this part acts as a transformer, right? Now, here you see input voltage. Input voltage can be, this side it is a positive and this side it is a negative, or else this side it can be negative and this side can be positive, okay, because the potential or else voltage keep on changes, okay, keep on changes. Now, try to understand. So let's consider positive only, positive half cycle. If I consider positive half cycle, what will happen? The current will flow through this transformer, okay, and it will reach point A. And what is the point A? It is a forward bias, because positive terminal is connected to P region of a diode. Then it acts as a forward bias. When it is acts as a forward bias, it acts as a just, when it is acts as a just, short circuit, okay, short circuit, because it is not mentioned whether it is made up of silicon or is germanium. You got it? Here we are not mentioning anything, whether it is made up of germanium or silicon. Therefore, it acts as a just a wire. So it becomes a wire, and whatever input you are giving, the same output will be reaching. Okay, this is for first positive half cycle. Now what will happen? Okay, now what will happen? And this one, okay, now this side it is a negative and this side it is a positive. Negative connected to a positive terminal of a diode. Now it is acts as a reverse bias. Initially it is a forward bias, now it is a reverse bias. So now it acts as an open circuit. There is no current flowing. So output will be zero. Output will be zero. The same repetition will happen. That is the reason for half a cycle, it won't be working. It won't be operating. Got it? Okay. So waveforms, how do you get it? Waveforms, here you see. First off, when it is a forward bias, okay, when it is a forward bias, when it is a reverse bias, okay, when it is a reverse bias, it is a forward bias, and it is also forward bias, and it is reverse bias, and it is a forward bias, and keep on repeats. Got it? And let's check out full wave rectifier. Full wave rectifier, it is given by, when a current flows through the rectifier circuit over the complete cycle input, okay, cycle of input AC, rectifier is called full wave rectifier. Means when a current flows through a rectifier circuit over the complete cycle of input AC, rectifier is called full wave. Not like half wave rectifier. Means for positive half cycle it is working, negative half cycle it is not working. Not like that. Even if it is a positive or a negative, okay, positive half cycle or negative half cycle, but there will be output. So that kind of rectifier we are calling it as a full wave rectifier. Got it? Okay. Now, so let's see how does it works. Okay, how does it works? I'll show you the diagrams. Okay, I'll show you the diagrams. Okay, see, this is the input. Let's consider this is a positive and this is negative. Okay, here you can see there are two diodes. Now it is a positive connected to a positive terminal of a diode. Now it becomes forward bias. Forward bias means just a wire. So current pass through it or voltage pass through it. Okay. Now the voltage can be measured across this one. Okay. Voltage across this output we can measure. And what about negative connected to this diode? This become reverse bias. Okay. This become reverse bias and a short circuit. Okay. Short circuit means not short circuit. It is open source. Means there is no current flow. There is no current flow. But due to this forward bias, there is a current through the D1. Okay, diode 1. There is no current through the D2. Got it? And next one, ulta I'll consider. Okay, ulta I'll consider. Now, here I'll consider it is a negative and this is a positive. Okay. This is the negative and this is a positive. Now, negative is connected to D1. That means this one becomes a reverse bias. And positive is connected to P type of region. This becomes a forward bias. Hence, there is no flow of current through D1 and there is a flow of current through D2. So, hence, here you can measure output. So, that is the reason if one diode acts as a reverse bias, another diode acts as a forward bias. Hence, there is a continuous flow of a current. So, therefore, you will be getting like this, okay? All these are for forward bias only, okay? All these are for forward bias, okay? Now, let's move on to the next concept. Next concept, okay? So, that is dual nature. Okay, after completing dual nature, we can have a session with respect to optics, okay, ray optics and wave optics. I think it is not possible to complete entire syllabus, okay, and still we can have, optics part, okay, only optics part I could not complete, okay, I may not be complete optics. So only 12 chapters I could complete. Got it? Okay. So last chapter we'll discuss and I'll be giving entire notes. Go through that. Okay. So it will be there. So entire chapters will be there. So optics part you please read. Okay. Now, so if possible, I'll be coming up with new session. Okay. Optics part. Now, dual nature of radiation and matter. So here you can see dual nature of radiation and matter. So here you need to concentrate more on, okay, you need to concentrate more on which one? Photoelectric effect. Okay, photoelectric effect. Okay, now let's see. Let's see the first content of this particular chapter, electron emission. First of all, emission. Emission means emit. But here electron emission means emit of electrons from metal surface. So generally we call it as a emission of electrons. So here emission of electrons from metal surface, we call it as a emission of electrons. Here three types of emissions are there. The first one, okay, the first one which is thermionic emission. Thermionic, due to heat, emission of electrons due to heat, we call it as a thermionic emission. Second one, field emission. That is due to electric field. Okay, that is due to electric emission of electrons due to electric field. And the last and very important third one, that is a photoelectric effect. That is the emission of electrons by light. Okay, that is a photo emission. Got it? Okay, photoelectric effect. Now we are studying about this photoelectric effect. Okay, now let's move on to the concept. What do you mean by, okay, only metals are preferred for electrons emission. Why? Because metals are having a more number of free electrons compared to all other, right? So metals have a number of free electrons more compared to any other material. That is the reason. Okay. Here you can see metals have a large number of free electrons. Therefore, they are preferred for electrons emission. Okay. Reason. Next one. Important terms related to photoelectric effect. Okay. This is a photoelectric effect. Electric effect. Photoelectric effect. Okay. The first one, threshold frequency. Threshold frequency or cutoff frequency. Below this frequency, there will be no photoelectric effect occurs. Above this frequency, above this cutoff frequency or threshold frequency, photoelectric effect occurs. Okay. I hope you know that. Okay. The next one, work function. Okay. So work function, the energy required by the electrons to emit, just emit from the metal surface. Okay. Metal surface. Work function is nothing but energy itself. Okay, work function is nothing but energy itself, and this energy required by the electrons. Why? To emit from the metal surfaces. That work function, it is given by phi. Okay, that is phi, and instead of energy, okay, in place of energy, we are writing h nu naught, where nu naught is a threshold frequency. Okay, threshold frequency. Now, stopping potential. Stopping potential means the negative potential applied at a collector. Okay, negative potential applied at a collector. So there are two terms. Okay, emitter as well as a collector. Okay, emitter means the electron emitting from the metal surface, that is the emitter, and a collector, those emitted electrons are collected by the one more end, right? Anode and cathode, and collector as well as emitter. So emitter, that is with respect to anode, collector with respect to cathode. So where electrons are emitted and these electrons are collected by some other part, that is opposite part or opposite end, that part we are calling it as a collector. Okay, these collector, okay, this collector is connected to negative potential so that photocurrent is zero. This one we call it as a stopping potential. The word only indicating stopping potential. Okay, stopping potential is defined as the minimum negative energy. Okay, not energy, minimum negative potential given to the collector plate for which the photoelectric current becomes a zero. Okay, photoelectric current becomes a zero. I becomes a zero. Okay, now threshold wavelength. Threshold wavelength means it is exactly opposite to the frequency. So the certain frequency below, okay, there will be no photoelectric effect occurs, right? And with respect to a wavelength, certain wavelength above which, okay, certain wavelength above which there is no photoelectric emission takes place. Okay, these are the important terms. The maximum wavelength up to which photoelectric effect will occur. Now, photoelectric emission. The phenomena of emission of electrons from the surface of a metal when radiation of a suitable frequency, especially we are using UV, okay, is incident on it is called photoelectric emission. Now, next one, okay, next one, explanation, okay, explanation of a photoelectric emission. Now, effect, Leonard observation on photoelectric effect. When ultraviolet radiation we are allowed to fall on an emitter, plate of an evacuated glass tube, enclosing two electrode, the current flows in that external circuit. As soon as the radiation falling on the emitter plate stops, the current in the circuit also stops. What does it mean? So there is a tube, okay? So there will be a small opening. Through that small opening, the intensity of a light or radiation falls on that emitter. So electrons emits. So whenever there is an intensity or a light falling on that particular emitter, okay, so emission of electron takes place. So when you stop that intensity of a light falling or a radiation falling on the emitter, if it stops means there is no photoelectric current. That is the observation made by the Leonard. Okay, now next one, when the ultraviolet radiation falls on the emitter plate, electrons are emitted and these electrons are attracted towards the collector plate. Flow of these electrons in external circuit result in current. Okay, result in current. Electrons will be flowing. Okay, now next one, photoelectric experimental observation. Okay. Now, here you can see with a neat diagram describe an experiment study the photoelectric effect. Now, here this is a, okay, so here they have considered cathode and this is the anode. So this is the emitter, okay. This is emitter. So electrons are emitting and moving towards this plate. This one we call it as a collector. This one we call it as a collector. So whenever this radiation stops fall on this emitter, no, so electrons emission stops, then the deflection in the microampere, or else this ammeter, it will show 0 reading. What does it mean? There is no flow of electrons, hence no current. Got it? Okay. Now, so this is a battery, okay, and this is a quartz window, and through that there is a radiation falling on it. Okay, what type of radiation we are using? Ultraviolet radiation. Okay. Now, this experimental arrangement is to study variation of a photoelectric current. So, dependent factors, okay, intensity of a radiation. So, emission of electrons, okay, after certain frequency, there is a photoelectric emission takes place. This emission of electrons directly depends on a number of electrons, okay, number of electrons. So, number of electrons, it is directly related to a photo, means intensity of a light, okay. More the intensity, more number of electrons emits from the metal surface. Less amount of intensity, then less amount of emission of electrons. Getting your point? Okay, got it? Now, so here intensity, okay, intensity, I means intensity, not a current, okay, intensity is directly proportional to the number of electrons emits, okay, number of electron emission. More intensity, more number of electrons emits from the metal surface. Got it? Now, next one, potential difference between anode as well as cathode. Okay, this one. So, anode as well as cathode. So, initially there will be some amount of current, right? It is starting from here, okay. So, here photocurrent will be there as anode potential, okay. It is not a cathode potential, anode. That means a negative potential they are talking, okay. So, potential difference between the anode as well as the cathode. So, negative potential if we apply, okay, if we keep on increase, the photocurrent will be decreased because it provides or it creates an electric field in a tube, which is opposite to the, okay, it is on the same direction of a flow of electrons, we can say. So, according to the condition, that is the electric field and the force, okay, what is the direction of force acting on electrons in electric field? Opposite to the flow of, opposite to the electric field direction, right? So, here what happens, due to this stopping potential, electrons, it is moving from emitter to collector. Due to this negative potential, the electric field developed so that the force acting on that moving electrons, and it stops reaching that reaching that collector. So, these electrons do not reach to that collector, hence there is no current. Okay, so this current will be 0, right? So, this one we call it as a negative potential or stopping potential, which is represented by Vs. Got it? Got it? Okay, now, next one, frequency of incident radiation. This frequency is directly proportional to the kinetic energy. Okay, what does it mean? See, as frequency increases, kinetic energy of electrons increases, but the number of, for a fixed intensity, number of electrons emit from the metal surface, it is fixed, but the speed of electrons moving from emitter to collector will become faster if we increase the frequency. If we decrease the frequency, the speed of electron will decrease. Okay, getting my point? Okay, speed of electrons will be decreased. Getting my point? Okay, simple. So, intensity, it is responsible for number of electrons emitting from metal surface. And this frequency is the responsible for kinetic energy of electrons, not a number of electrons. Getting my point? Okay, simple. Okay, now let's move on to the next concept. Einstein photoelectric equation. See, the energy, light has an energy, right? Light is nothing but a form of energy. When this light falls on a metal and electrons emission takes place, right? So, entire energy, that light energy falling on the metal surface, this energy divided into two parts. One is work function, another one is kinetic energy. How? If I consider total energy, okay, if I consider total energy E, it is divided into work function and kinetic energy. Work function and kinetic energy. Already we know that what is work function and what is kinetic energy, right? So this kinetic total energy, here I can write in terms of a frequency, this is h naught, and in terms of frequency, the work function it is given by h nu naught plus kinetic energy, it is half mv square. So more the frequency, more is the kinetic energy. Clear? Okay. And this is in terms of a frequency. This is in terms of a frequency. In terms of a wavelength, if I write in terms of a wavelength, C is equal to F lambda, right? C is equal to F lambda. And here we are not talking about an electromagnetic waves. Yes, it is electromagnetic waves only. Okay. So in terms of the speed of a wave, okay, speed of, in terms of a wavelength, okay, we can write V is equal to, okay, F lambda, okay, F lambda. So in terms of a wavelength, okay, frequency can be converted to V divided by lambda, okay, or else C divided by lambda, because it is the electromagnetic waves, right? So frequency that is equal to C divided by lambda. So just substitute the value HC divided by lambda, and here HC divided by lambda naught plus it is half mv square. This is in terms of wavelength. This is in terms of wavelength. Got it? Okay. Next one. Particle nature of the light. Okay, particle nature means this light exhibits both light as well as a wave. Light exhibits as a both a particle as well as a wave nature. So this one, first one, it is a particle nature. Okay, particle nature. So energy of a photon, it is given by h nu, or else that is converted to wavelength, that is hc divided by lambda. And the photon travel with the speed of light. These are the some important properties of a photon. Okay. Okay. Particle nature of the light, that is a photo. Okay, photon. Okay, rest mass of photon is 0. And the next one, the mass of the moving photon is m. Okay, mass of the moving photon, that is h nu divided by c square, or else h divided by lambda c, where lambda is the wavelength, c is the speed of light, and h is the Planck's constant. Got it? Okay. Now next one, fifth one, the momentum of the photon, it is given by mc. Generally, linear momentum, it is given by mv, right? Here we are talking about ultraviolet, that means it is the electromagnetic waves, the speed which is equal to a speed of light. Okay. In terms of a frequency, you can write h nu divided by c square, because multiplying divided by c, and here finally you'll be getting in terms of, okay, in terms of Planck's constant and wavelength, that is p is equal to h divided by lambda. Got it? Okay. Now next one. Next one. So next topic, that is a wave nature. Wave nature of a matter. Okay. Certain phenomena like interference, diffraction, and polarization can be explained by considering the wave optics. Okay. Wave optics, that is a wave nature of light. Okay. Wave nature of light. So what are the phenomena? Like interference, diffraction, polarization, be explained by the considering wave nature. Okay. Now, wave optics as well as ray optics. Okay. Now, here we have certain other phenomena like photoelectric effect, Compton effect can be explained by the considering the light as a particle. Okay, particle. So, Compton effect, okay, and photoelectric effect treated as a light as a particle, where interference, diffraction, polarization treated as a light as a wave. Okay. Now, light exhibits both wave nature as well as a particle nature. That is a dual nature. So, light exhibits both particle nature as well as a wave nature. This behavior we call it as a dual nature of a light. Okay. Now, here we have dual nature, both the nature as well as particle nature. That is a dual nature. Based on this, de Broglie proposed an hypothesis according to which material particle also exhibit a wave nature under suitable condition. Hypothesis, it cannot be true or it can be a false. Okay, that condition we call it as a hypothesis. Okay. Now, the waves associated with a material particle in a motion are called matter waves or de Broglie waves. The de Broglie wave, okay, wavelength is associated. How it is associated? That is h is equal to k, or else you can write p is equal to Yeah, h divided by lambda also you can write. Okay, I'm used to it. That is h divided by lambda. Previously we have derived. Okay, so this relation shows that wavelength of a light. Okay, wavelength of light. So here calculate the de Broglie wavelength of a particle of a mass 0.05 kg moving with a speed of 100 meter per second. Okay, so that is a lambda. Okay, that is mb p divided by. Okay, here you can write lambda. Okay, p divided by h. You can use it. Okay, now see wavelength of a particle of a mass moving with a 100 meter per second. Calculate the de Broglie wavelength. Okay, so de Broglie wavelength, if you see, what is the formula for that? H divided by mb. H divided by mb. So de Broglie wavelength h divided by mb, or else h divided by p also you can write. But in terms of a mass as well as a speed, they have given lambda, that is equal to h value, that is a 6.6 into 10 power minus 34 joule second, and mass, that is a 0.05 kg into speed, that is 100. Okay, if you simplify this, you will be getting your answer. Okay, now the work function of a certain metal is a 4.2 electron volt. Will this metal give a photoelectric emission incident radiation wavelength of 330 nanometer? Work function, it is given by h nu naught, right? So by this we can calculate the frequency, right? So that is a 4.2 divided by h. H value already we know that it is a constant. And relate this one with respect to wavelength. Okay, relate this one with a wavelength. Okay, if it is greater than 330 nanometer, then photoelectric emission takes place. And if it is less than this 330 nanometer, then photoelectric emission do not takes place. Got it? Okay, now next one. Yes, this is about, dual nature, matter and radiation. Okay, let me try this wave optics. Okay, wave optics. Here, first one, we have a time till 10:30, right? 10:30 means 40 minutes we can complete optics also. Okay, we can complete wave optics. Left with only ray optics. Okay, don't mind. Okay, so last 40 minutes, right? Now, wavefront. What is the wavefront? See, when you drop a stone into the water, okay, when you drop a stone into the water, what will happen? The waves will be formed, and those waves will be reaching a bank, right? Yes or no? It will go on, right? So here, that waves, okay, that is high position, low position, high position, low position, high position, and low position. It will come now. They are in a same phase. High position, every particle on a high position will have a same phase. The low position, every particle on a low position have a same phase. Okay, this one we call it as a wavefront. Okay, but how to write in a examination? You see, wavefront is defined as the locus of all such particle which are oscillating in the same phase. Normal to wave, okay, this is the same phase. Normal to the wavefront gives the direction of a propagation of wave. For example, consider a wave. Okay, consider a wave, and at this high position, okay, all the particles are in same phase, and add this same phase, add this same phase, right? And direction to which, okay, for example, here let me consider these are the particle. Okay, these are the particle oscillating in the same phase at a different level, right? So last one acts as a source for the second wavefront. Okay, second wavefront. Simple. Okay, it is the locus of a point. So here diagrams are there. This is for plane one. This is for circular one. And coming to the types of a wavefronts. Okay, spherical wavefront due to point sources. For example, bulb. Okay, if you on the bulb, what will happen? That brightness will move in all the direction, right? When you glow a bulb, the brightness will be in an entire room. That means wave traveled in all the direction. So that is due to point source, right? Now here we can call it as a spherical wavefront, spherical wavefront. It moving like this. How to show this? Like this, okay? It move like this, okay? Like this, okay? Now, next one, plane wavefront. Plane wavefront means this one, okay? Sources are at infinite. Sources are at infinite. So like example, a rays from the sun, okay? It is coming from infinite, right? Coming from infinite. So that kind of particles coming in a wave form, okay? They have a same phase. That phase we call it as a wavefront. So here what will happen? We have a source at an infinity. Then we will be getting a plane wavefront. Cylindrical wavefront, that is a thin rectangular strip or a linear source, like a tube light. Bulb means point source. And if you consider a tube light, then it will be a linear source. Getting my point? Okay. Now, next one, Huygens principle. What does Huygens principle says? Every point on the given wavefront called primary wavefronts. Okay. Every point on the given wavefront. Okay. Every point on the given wavefront. Okay. Given wavefront. A source of a new disturbance. Okay. Acts as a source of a new disturbance. For example, there's a wavefronts, okay? There's a wavefronts, if I consider, okay, if I draw circle, okay, edges, and it become a second wavefront, So here secondary wavelets, and these are called secondary waves, which travels in all direction with the velocity of a light in the medium. Now, surface passing these secondary wavelets tangentially in the forward direction at any instant gives the new wavefront. See, direction if we consider, okay, previous one I have it drawn, no? Previous one, we can consider this one. Perpendicular to it gives the direction of wave propagation. Okay, now, let's move on to the next topic. This is also done, okay? Now, yes, explain refraction on the basis of Huygens wave theory. Refraction, okay? So now, let's try to understand in terms of a wave, not in terms of a light, okay? Now, here what I will do is, let's consider okay, and this one, okay, one second, yeah, and perpendicular to it, okay, this is a wavefront, okay, this one is a wavefront. Now, what will happen? So here, try to take a normal, as you learn, okay, like a reflection of light, a refraction of a light. So now what will happen? This one will bend towards the normal, right? It will bend towards the normal. Okay, like this, right? And here this one, okay, this one, second, and this one, okay, yes. After reaching the surface, okay, again it is also bending towards the normal because it is a denser medium, okay, bending towards the normal, okay. This is a incident wavefront. And what about this? This is a refracted wavefront, okay. This is a refracted wavefront. Now, let's try to consider incident angle, reflected angle, okay. So let's consider this is a incident, okay. This is incident and this is a refraction. Why? This is angle of incidence and this is angle of refraction. This is angle of refraction, and here you can consider angle of, refraction. So let me consider a wavefront, okay. Incident wavefront as a AB. And refracted wavefront A dash and B dash. Okay, A dash and B dash. Now, here you need to understand, okay. So when this first one, okay, first at A, at A. Once it reaches, immediately it is traveling in a denser medium. But what is the time taken by this is B to C? That I can call it as a V1, okay, V1 T, okay. In the same way, V1 T, in the same way, before reaching this point, this ray has traveled some other distance, right? Some other distance. So this one also I can call it as a V2 T, okay. Now, here, so first one, if you see, that is A, B and B dash. A, B and B dash, if you see. So this is acts as a perpendicular and this is a hypotenuse, right? This is a perpendicular, right? This is a perpendicular. And perpendicular, that is a B, B dash, okay? So from triangle, A, B, B dash, if I consider, okay, sine I, we know that perpendicular by base, right? Perpendicular by, not base, it is a hypotenuse, right? What is the perpendicular? That is a V1 or T divided by hypotenuse, that is a B dash, okay? So let's consider this is equation 1. And next one, triangle A, B dash, A dash, okay? And sine R, okay, sine R. Again, it is a perpendicular by hypotenuse. Okay, this acts as a perpendicular, right? Perpendicular. Now, this is perpendicular, okay? This is perpendicular, right? Perpendicular, that is V2 divided by V2 T. Why it is V2? Because it is a rarer medium. If I consider this as a rarer medium, the speed will be different. And if I consider this as a denser medium, speed will be different. So that is the reason, okay? What about hypotenuse? Okay, if this is a perpendicular and hypotenuse will be A dash, right? A dash hypotenuse, let me consider okay, here it should be, okay, here perpendicular, okay, here perpendicular, this should be perpendicular, right? So now, so this is perpendicular and hypotenuse is A and B dash, okay. Now take the ratio, sine I divided by sine R, that is equal to equation 1, V1T divided by AB dash, okay, into, take the reciprocal of this, AB dash divided by V2, okay. First one sine I, V1 divided by A, B dash, okay, sine R, that is the V2 T, A dash, B dash, okay, A, B dash, okay. Now, AB, here you can see, AB dash cancel, and T get cancelled. So finally, V1 divided by V2. So sine I divided by sine R, that is equal to V1 divided by V2. V1 divided by V2. Got it? Okay. So this is about refraction. Same way reflection if you do it, okay. Same way for a reflection. So this is incident plane, okay. Incident plane. So before reaching this only, okay, so let me consider this is a incident wavefront, okay, this is the incident wavefront, okay, this is a incident wavefront, A and B, okay. Now, before reaching this point, this one gets reflected, okay, this one gets reflected, okay, this one gets reflected, got it? Now, gets reflected, and next one, so next one, it reaches, okay, and it is also gets reflected, right, gets reflected and gets reflected, right, gets reflected, and wavefront, okay, wavefront for these I can consider, okay, from here, okay, from here like this, okay. Now, so this is A, B means this is A dash and B dash, right, A dash and B dash, right. Now, here you can see, so speed will remain same, okay, speed remains same. So once it strikes this at a point P, what is the distance traveled from B to B dash? That is, let me consider C t, okay, that is the distance traveled. And here also, before reaching, okay, before reaching b dash, this a has traveled some distance, right? What is the distance traveled? That is also same, c t2, okay. Now, so I'll be writing outside, okay. Okay, did you get it? Okay, did you get it from here? So this will be c t, and here also, okay, this side also ct, right? Speed as well as the time will remain same. Got it? Now, so look at a base means a surface, striking surface, okay. Here you can see how many triangles. So for AB, okay, for AB, so for AB, this is the perpendicular, okay, and for second one, this is the perpendicular, right? So let's consider sine I, okay, sine I, that is the perpendicular by hypotenuse, perpendicular by hypotenuse. If I consider perpendicular, okay, this is perpendicular and this is the base, okay, this is perpendicular, this is hypotenuse. Perpendicular, how much it is? CT, and this one hypotenuse, that is AB dash. Okay, let me consider this is equation 1, and sine R, okay, sine R, again perpendicular, and this is hypotenuse. How? See, this is, if I consider, okay, normals, okay, this is a normal example I'm considering, okay, example I'm considering, and here also, so this is incident angle, and this is, okay, this is, you can consider incident angle, and this one you can consider it as a reflected angle, okay. Now, here also C T and A B dash, because for the second one, this one becomes A B dash becomes, perpendicular for it, and this one, okay, this A dash B dash becomes a, first one, that is a base, okay, base AB, sorry, this is A B dash, okay, A B dash, and a perpendicular, that is a CD, A dash. Got it? And this is equation 2. Now, sine I divided by sine R, that is equal to CT divided by AB into AB divided by CT. Now it will be 1. Now, so can I write the sine I is equal to sine I is equal to sine R for a small angle, for small angle, for small angles, okay, for a small angle. So here you can consider sine I, okay, sine theta becomes theta. In the same way, I is equal to R. That means angle of incidence, that is equal to angle of reflection. Okay, angle of incidence, that is equal to angle of reflection. Okay, so remaining part, please go through, this content part. Okay, so I'll be stopping it here only. Okay, so ray optics, okay, ray optics, interference, you have to, interference, only interference part I have left with it, okay, interference part. So next, okay, next we have to prepare well, okay, your board exams are nearing, and thank you so much for all the students who have participated in this amazing session. So I'm really very sorry that I could not complete, a ray optics part, okay, ray optics part, because of time, okay. It is keep on moving. You guys are asking a derivation part, everything, so I'm doing it. Therefore, what happened? The time extended, okay. So, so reason being, because I have used a lot of time, okay, in explaining your, questions, clarifying your doubts. I hope this session is very helpful for everyone, and I wish you all the very best for your board examination. Okay, students, do not waste your time. Okay, be prepared for everything. So students' life is a golden life. So use every single opportunity as a boon. Okay, that's all for today's session. And if you have any questions, I'll be waiting for 2 minutes. Okay, I'll be waiting for 2 minutes. You can ask questions. I can answer your questions. Okay, and IN Tech Editor, how many pages left? So that a ray optics complete one. Okay, complete chapter, it is left out. Okay. now. Yes, do you have any questions? If you have any questions. Yes. Yes, yes. Iron decadators, yes, I have. Okay. I have experience. Okay. I am Dakshu. Yes. Fine. Okay. I hope, everything is fine except that ray optics. Okay. I'm really sorry for that. Okay. Now, it's time. Whatever it is possible, we have done from our end, and it's your time. Okay. Prepare well and be confident. Attend your examination. Okay. I wish you all the very best. God bless you. Take care. Bye bye. Okay.